Welcome to the deep dive.
Yeah.
We are so glad you could join us today because we've got something that is, well, it's honestly pretty mind-blowing.
Yeah, it really is. It completely upends basically everything we've been told for years.
Exactly. I mean, think about it. For the last, 5 years, every time you read the news, governments, regulators, industry CEOs, they all swore that the future of driving was just a simple, mathematically clean, 100% battery electric future.
Right. It was presented as this absolute inevitability. Like there was no other option.
Yeah, an inevitability. But so we've got this massive stack of sources today. We're talking highly technical slide decks, architectural blueprints, deep dive reports, and all of this is straight from the 47th Vienna International Motor Symposium, which just happened in April 2026.
And behind closed doors in Vienna, the smartest automotive engineers and CTOs on Earth quietly admitted that this binary battery-only dream, it's dead.
Okay, let's unpack this, because our mission today, for you, the listener, is to decode this. They call it the global strategy, and it is entirely rewriting the rule book for the next decade of the auto industry.
It really is a profound reversal. We're moving from what they called the era of technological certainty, that unwavering faith in the BEV-only gospel, into an era of strategic resilience.
Which sounds like corporate speak, but as we'll see, it's actually about hardcore physics. We're going to cover everything from the thermodynamics of new combustion engines to literal geopolitical data walls.
Yeah. But to really understand the hardware, the stuff they're physically building now, we have to look at why this sudden shift happened. Why hit the brakes on the BEV-only strategy?
Right. What went wrong?
Well, the industry hit what the symposium researchers classify as the three walls of reality. These are just, immovable physical and economic constraints. And the first one is infrastructure limits.
Okay, but let me play devil's advocate here. You look around any major city right now, and there are, DC fast chargers popping up in grocery store parking lots, dedicated charging hubs. It looks like the infrastructure is scaling, right? Are they saying that's an illusion?
It's not an illusion exactly, but it's an urban bubble. Like a suburban bubble. It completely fails when you try to extrapolate it to a macro national grid level.
Oh, interesting. Wow.
Yeah, the symposium data models out the reality of non-urban charging corridors. Replacing the global fleet of combustion vehicles with battery electric vehicles, it doesn't just mean pouring concrete and putting up charging pedestals.
Or you need the actual juice.
Exactly. It requires a fundamental ground-up redesign of the high-voltage electrical grid to handle massive, simultaneous megawatt power draws.
So it's like the interstate truck stop example.
Yes, perfectly.
Because if you have a major logistics hub along a freight corridor,
Right.
you might have, I don't know, dozens of heavy-duty trucks refueling at the exact same time.
Right.
And if those are all pulling megawatt-level fast charges simultaneously, you're talking about the power draw of a small city centralized in a single rural zip code.
Precisely. And the sheer cost of laying down the high-voltage transmission lines, upgrading the substations, sourcing the heavy-duty transformers for that specific node, it's economically unviable.
Wow.
Yeah. We are seeing multi-year backlogs just to procure standard grid transformers right now.
So building a high-capacity charging plaza out in a rural corridor where it has to guarantee multi-megawatt delivery instantly no matter what the local grid load is doing, it just doesn't pencil out.
Not without astronomical continuous government subsidies, no.
Yeah.
The grid literally cannot physically or economically scale at the pace required by these 2030 or 2035 political mandates.
That is wild, and that sets up the second wall beautifully. Because let's say you invent a magic wand for copper transmission lines and solve the grid. You still have to build the actual batteries.
Exactly. And that's the second wall the Vienna documents point to, supply chain bottlenecks.
Yeah.
This is where engineering collides directly with global geopolitics.
Oh, hey.
Because a monoculture strategy relying 100% on battery electric vehicles creates this incredibly fragile dependency on a highly concentrated supply chain.
We're talking about like lithium, cobalt, nickel, right?
Yes. And specifically things like neodymium and dysprosium, which you absolutely need for permanent magnet motors.
And the vulnerability there isn't just the mining of the raw ore, right? Though obviously that's a massive hurdle. The real choke point is the refining and processing capacity.
Right, which is hyper-concentrated in just a handful of regions globally. The
Yeah.
CTOs in Vienna realized that transitioning the entire global mobility sector to rely on a single, highly concentrated refining pipeline, it creates an unacceptable level of geopolitical exposure.
Oh, absolutely. A trade war, a regional conflict, or, a targeted embargo could instantly cripple the entire automotive manufacturing base of a continent.
Exactly. If your single powertrain architecture requires a critical mineral that you suddenly cannot import, your factories just freeze.
It just stopped.
They stop. It's an existential risk profile that the boards of these massive legacy automakers simply cannot tolerate anymore. They realized putting all their capital into the battery basket was basically strategic suicide.
Which brings us to the third wall.
Oh.
And this is where the physics truly punish the BEV-only mandate. The symposium calls it operational penalties.
Yes.
You see this glaringly when you step outside the passenger vehicle market and look at heavy-duty commercial transport. I mean, if you fill a commercial truck with massive batteries, you don't have weight left for the actual cargo.
Right. The commercial sector operates on razor-thin margins. It's all dictated by total cost of ownership, or TCO, and payload capacity.
Right.
So when you force a pure battery electric architecture onto a Class 8 long-haul truck, the energy density deficit of current lithium-ion technology becomes glaring. To get the range they need, the battery packs have to be incredibly massive.
It's like a cargo plane that can only carry its own fuel. Because legal road weight limits are strictly enforced, every pound of battery you add is a pound of revenue-generating cargo you have to remove.
Exactly. You end up building a highly advanced cargo vehicle that spends a massive percentage of its energy just hauling its own fuel source around. It absolutely destroys the TCO for a fleet operator.
It makes no financial sense.
None. The physics of energy density are just unforgiving here. A tank of diesel or compressed hydrogen holds vast magnitudes more energy per kilogram than the most advanced battery cells currently in production.
Or even in late-stage development, right?
Right. The experts at the symposium made it definitive. Forcing a passenger car solution onto a heavy-duty commercial problem is a failure of engineering pragmatism.
Okay, so the industry hits the infrastructure wall, the supply chain wall, and the payload penalty wall. But they aren't using this as an excuse to just, roll back emission standards and keep pumping out 1990s-era diesel engines.
No, definitely not.
The pivot here is entirely reliant on a new accounting method for carbon. They're moving away from the old tank-to-wheel metric.
Yes, and what's fascinating here is that this is the philosophical bedrock of the entire symposium. For years, regulations have been written around tank-to-wheel or tailpipe emissions.
Right.
Under that framework, an electric vehicle is zero emission by default simply because it doesn't have an exhaust pipe. But what the Vienna Consensus demands is a universal shift to well-to-wheel life cycle assessments, or WTW-LCA.
Which is just mathematical honesty, because tank-to-wheel is honestly kind of an accounting trick.
It is.
It allows a manufacturer to push the carbon footprint of the vehicle off their own balance sheet and onto the power generation and mining sectors. So when you, the listener, buy a zero-emission car today, it might actually have a massive hidden carbon footprint from the factory.
Exactly. True climate neutrality requires tracking the carbon intensity from the exact moment a critical mineral is blasted out of the rock to the moment the car is recycled. You have to calculate the diesel burned by the mining equipment, the energy consumed in the smelting and refining processes, the carbon footprint of the battery cell manufacturing plant, the global shipping logistics.
All of it.
All of it. And crucially, the carbon intensity of the local electrical grid that actually charges the vehicle over its lifespan.
Right. So if a consumer buys a high-performance EV with a massive, 120 kilowatt-hour battery, and the materials were refined using coal-fired grid power, and then they charge it in a region that relies heavily on fossil fuels.
That vehicle carries a massive carbon debt before the tires even touch the asphalt.
That's crazy. And conversely, if an automaker builds a highly optimized internal combustion engine that runs on synthetically produced zero-carbon e-fuels, its tailpipe will emit carbon dioxide.
Yes, but, and this is the key, because that specific carbon was captured directly from the atmosphere during the fuel synthesis process, the well-to-wheel life cycle assessment might reveal a lower total carbon footprint than the BEV charged on a dirty grid.
Okay, but I can hear the pushback on that already. Like, environmental advocates often argue that well-to-wheel accounting, specifically regarding e-fuels, is just a Trojan horse.
A Trojan horse to keep the fossil fuel industry alive.
Yeah, to extend the life of legacy internal combustion manufacturing.
Well, the engineers at Vienna addressed that skepticism directly. Technology neutrality isn't a step backward. It's a mathematically honest approach to saving the planet.
Right.
It's not about protecting legacy assets. It's about recognizing that the atmosphere is indifferent to local tailpipe regulations. It only reacts to the total volume of greenhouse gases introduced into the system.
So by enforcing wheel-to-wheel assessment, you force every single powertrain batteries, hydrogen, e-fuels, hybrids,
Right.
to compete strictly on their mathematically verifiable carbon reduction.
Exactly. The mandate is no longer build batteries. The mandate is build whatever reduces total life cycle carbon fastest in your specific market.
Okay, so if the industry isn't just building batteries anymore, what exactly are they building? Because that brings us to section 2, the physical hardware.
Right. The strategy to survive this new reality is what the symposium calls the resilient technology portfolio. They are actively hedging their risk via diversification across 3 distinct pillars.
Okay, let's break down these pillars. What's the first one?
The first pillar is advanced BEV and storage. It's critical to state that the pivot away from a BEV-only strategy does not mean the abandonment of electric vehicles.
Sure.
The BEV is just transitioning into a highly specific role, the urban zero-emission and high-performance flagship. And the engineering focus here has shifted from simply adding more cells to optimizing the architecture.
Right, we're seeing the standardization of 800-volt architectures to manage the thermal loads of ultra-fast charging. But the really disruptive shifts in the sources are solid-state batteries and no TP packaging. Let's unpack the thermodynamics of no TP, which stands for no thermal propagation, right?
Yes, no thermal propagation. This is a mandate driven by the catastrophic failure modes of traditional lithium-ion packs.
The fire.
Exactly. If a single cell experiences thermal runaway due to, say, a short circuit or physical puncture, the heat traditionally cascades to adjacent cells. You get a sustained high-temperature fire that is nearly impossible for first responders to extinguish.
It just keeps burning. So how does no TP fix that?
No TP packaging uses advanced phase change materials, aerogel insulators, and highly engineered venting channels.
So the pack is basically designed so that if a cell fundamentally fails and ignites, the thermal energy is isolated.
Right, it's isolated and expelled from the vehicle before it can raise the ambient temperature of the neighboring cells above their critical threshold.
That's brilliant. And then coupling that safety architecture with the transition to solid-state batteries, that fundamentally changes the energy density equation, right?
Oh, absolutely. By replacing the flammable liquid electrolyte with a solid ceramic or polymer separator, you eliminate the primary fuel source for these fires.
Right.
Plus, the solid separator resists the formation of lithium dendrites.
Remind us what those are.
They're microscopic, metallic spikes that grow during fast charging. They can pierce the separator and cause short circuits.
Ah, okay. So defeating dendrite formation allows engineers to use pure lithium metal anodes instead of graphite, which radically increases the volumetric energy density.
Exactly. You get a safer pack that stores vastly more energy in the exact same physical footprint.
Incredible. So that's the future of the BEV pillar. But as we discussed with the commercial sector, the battery cannot solve everything. So what's the second pillar of the resilient portfolio?
The second pillar is zero carbon molecules. This is primarily focused on hydrogen and e-fuels for heavy-duty commercial viability.
Now, the application of hydrogen here isn't just fuel cells, right?
Right.
Because the sources specifically highlight H2 ICE hydrogen internal combustion engines. This seems like an incredibly pragmatic engineering pivot.
It really is. It solves multiple macro problems simultaneously, because a fuel cell is essentially a chemical battery that consumes hydrogen to generate electricity. But fuel cells require incredibly pure hydrogen and utilize expensive platinum group metals for catalysts. They are extremely sensitive to particulate contamination in industrial environments.
Which you would obviously have in like mining or heavy freight.
Exactly. H2 ICE, on the other hand, utilizes the mature, robust architecture of a traditional diesel engine block. It just injects gaseous hydrogen into the cylinder instead of diesel.
That is so smart. You completely eliminate the carbon emissions because there is no carbon in the fuel molecule. You're just emitting water vapor and, managing trace nitrogen oxides from the atmospheric air pulled into the combustion chamber.
Right. But beyond the emissions, this allows major OEMs to utilize their existing multi-billion-dollar foundries, machining lines, and supply chains.
You don't have to write down a century of metallurgical expertise and manufacturing infrastructure.
Exactly. You preserve the industrial base while achieving zero carbon transport. Now, the combustion properties of hydrogen, specifically its extremely high flame speed and wide flammability limits, they do present engineering challenges regarding pre-ignition. Sure.
But the thermal management and injection timing strategies detailed in Vienna prove the viability of H2ICE for continuous high-load applications.
Okay, that leaves us with the third pillar. And this is where I think a lot of industry observers are going to be shocked. Wait, internal combustion engines? I thought they were going to the museum.
I know, right? But the third pillar is ultra-high efficiency internal combustion engines and hybrid electric vehicles. The ICE is being positioned not as a dying legacy technology, but as an active geopolitical hedge.
Okay, explain that. How is a gas engine a geopolitical hedge?
Well, the highly optimized ICE is the ultimate survival mechanism. If global supply chains fracture and you suddenly cannot procure battery cells,
Right.
or if a developing market simply cannot build out a high-voltage grid within the next 2 decades, you absolutely require a highly efficient hybridized internal combustion engine to maintain mobility and lower emissions concurrently. But the regulators aren't going to accept the thermal efficiency of a standard 2020-era gas engine. To justify keeping ICE alive under tightening Euro 7 and EPA regulations, the engineers have to squeeze the absolute limits of physical science.
Yes. And the symposium documents call this microengineering for macro resilience.
Oh, I love that term. And this is where the engineering gets truly breathtaking. The sources detail 3 distinct technological breakthroughs that collectively save the internal combustion architecture.
We must start with the thermodynamic breakthrough presented by Sherry and AVL. It's called the double crank 3-link mechanism.
Okay, to understand the magnitude of this, we have to look at the limitations of the traditional auto or diesel cycle, right? For over a century, the ratio of the compression stroke to the expansion stroke in a standard engine has been physically locked by the geometry of a single crankshaft and connecting rod.
Exactly. The piston travels up to compress the mixture, and it travels down the exact same distance during the power stroke.
And that symmetry is the primary thermodynamic bottleneck.
Right. When the exhaust valve opens at the bottom of the power stroke in a traditional engine, the combustion gases are still under immense pressure and heat. That residual energy, the exhaust enthalpy, is literally blown out the tailpipe. It is wasted work.
Now, engineers have used the Atkinson cycle via variable valve timing to artificially leave the intake valve open longer, effectively shortening the compression stroke relative to expansion. But you are still bound by the physical limits of the single crank architecture.
Right, so Cherry and AVL basically tore up the foundational geometry of the engine block. They completely replaced the single connecting rod with a complex kinematic linkage utilizing 2 separate crankshafts.
Wow, 2 crankshafts for 1 piston.
Yes, this effectively decouples the piston's motion from a simple sinusoidal wave. The mechanism allows the piston to execute a standard compression stroke, but then continue downward for a vastly elongated expansion stroke.
And the documentation cites a 26-to-1 expansion ratio. That is staggering. I mean, a standard high-efficiency engine might push 13-to-1 or 14-to-1.
Exactly. By allowing the piston to travel that much further during the combustion event, the engine extracts almost all of the available heat energy and pressure before the exhaust valve finally opens.
So the gases leaving the cylinder are remarkably cooler and at a much lower pressure because that energy has been converted into mechanical work at the crankshaft.
Right. And the ultimate metric for this is brake thermal efficiency, or BTE. The absolute ceiling for a passenger car engine has hovered around 40 to 42% for years. Most of the fuel energy is lost to heat and friction.
But by implementing this double crank linkage, they shattered the 48% BTE ceiling. Achieving a near 50% thermal efficiency is the equivalent of breaking the sound barrier for an internal combustion engine.
It profoundly alters the carbon calculus of a hybrid vehicle. But thermodynamics is only one front. We also have to look at electromagnetics, specifically the advancements in the e-axle presented by Garrett Motion.
Because as we transition into these ultra-efficient hybrids, the electric motors integrated into the drivetrain are shrinking in size, but they're required to output massive power densities.
Right.
And to achieve that, they have to spin at incredibly high velocities.
Exactly. So Garrett Motion developed an e-axle designed to operate at 35,000 RPM.
35,000.
Yeah. And at those rotational speeds, traditional mechanical ball bearings or oil-lubricated journal bearings experience catastrophic friction and thermal degradation. The sheer centrifugal forces and heat generation just destroy the mechanical tolerances.
And you can't just pump more oil in because the oil itself starts to churn and create parasitic drag. drag.
Exactly. So Garrett Motion adapted aerospace technology, specifically the oil-free foil bearing used in high-altitude turbomachinery.
Okay, how does that work?
A foil bearing operates on the principle of hydrodynamic pressure. As the motor shaft begins to spin, it draws a microscopic layer of air into the gap between the shaft and a flexible metallic foil.
Wait, air, because of the extreme rotational velocity, the air itself acts as an incompressible fluid wedge.
Yes, the metal shaft physically lifts off the foil and rides entirely on a cushion of air. There is zero metal-on-metal contact during operation, zero mechanical friction.
That is insane. So that eliminates the need for complex, heavy oil pumps, reservoirs, and cooling jackets.
Right, and the elimination of the lubrication system plus the reduction in thermal load allowed Garrett Motion to shrink the overall volume of the motor unit by 40%.
But the strategic genius here isn't just weight reduction. Because the motor spins at 35,000 RPM with almost zero frictional loss, it generates high torque and power output with a significantly smaller electromagnetic footprint.
Exactly. And the documents state this specific architecture slashes the requirement for rare earth magnets by 30%.
Which brings us right back to the geopolitical supply chain wall. By solving a deeply complex fluid dynamics problem at the microengineering level, literally hovering a shaft on a wedge of air, you actively reduce your corporate reliance on a vulnerable, highly concentrated critical mineral supply chain. Engineering directly mitigates geopolitical risk.
That is the essence of macro resilience. And the final breakthrough in this section deals with materials science. Bosch presented their third-generation silicon carbide, or SiC technology, for power inverters.
Right, the power inverter is the neurological center of any hybrid or electric powertrain. It converts the direct current stored in the battery into the precisely timed alternating current required to drive the electric motor.
Yes. And inside these inverters are arrays of MOSFETs, microscopic semiconductor switches, that turn on and off thousands of times per second. The efficiency of those switches dictates the total range of the vehicle.
And silicon carbide is a wide bandgap semiconductor, meaning it can handle much higher voltages, temperatures, and switching frequencies than traditional silicon. But even with CSI, you battle two primary enemies, right?
Right. Conduction losses when the switch is open and switching losses during the transition state. Furthermore, when the switch is theoretically off, the massive electric fields required in an 800-volt architecture can induce microscopic electrical leakage across the semiconductor junction.
It's parasitic energy loss.
Exactly. So Bosch engineered a solution called the dual-channel trench MOSFET.
Ah. So instead of a planar structure where the current flows across the flat surface of the chip, they physically etched microscopic trenches down into the silicon carbide substrate. So they built a shield for the chip to stop electrical leakage.
Yes. By embedding the gate structure within these deep trenches, they effectively shield the delicate oxide layers from the highest concentrations of the electric field during the off state.
Right.
This trench architecture drastically lowers the specific on resistance of the chip while simultaneously preventing voltage leakage when the switch is closed.
And the performance metrics are definitive. The trench architecture cuts switching losses by 20%. And when you are managing hundreds of kilowatts of power, a 20% reduction in switching loss translates to massive thermal load reduction.
Exactly. You can downsize the cooling system, extend the vehicle range, or utilize a smaller battery pack to achieve the exact same range metric.
Okay, so synthesize these three breakthroughs. A 26-to-1 expansion ratio engine, a 35,000 RPM air-bearing motor, and shielded trench silicon carbide. By pushing the absolute limits of physics, companies ensure they survive no matter which way the regulatory winds blow.
Exactly. The billions of dollars poured into this microengineering are not for incremental performance gains. They are survival expenditures.
But this introduces a massive financial problem, because R&D is brutally expensive. If a car company has to develop a hyper-advanced battery, a levitating e-axle, and a double-crank combustion engine, how do they not go bankrupt?
While maintaining 3 entirely bespoke engineering pipelines seems like a fast track to bankruptcy, yes.
So how do they afford it? This brings us to Section 3, the highly modular architecture mindset.
Right. The only mechanism to make a diverse, resilient technology portfolio financially viable is through extreme, uncompromising modularity in physical hardware. And the symposium highlighted the Traton Group as the blueprint for this.
So Traton oversees massive commercial truck brands like Scania and Aman. They operate in a sector where TCO is the only metric that matters.
Right. They realized they required battery electric trucks for last-mile urban logistics, internal combustion diesels for rugged, underdeveloped infrastructure regions, and hydrogen fuel cell architectures for zero-emission cross-country freight.
And historically, an OEM would design three separate ladder frames, three distinct cooling architectures, and three unique cab designs to accommodate those disparate powertrains.
Exactly. But Trayton abandoned that. They designed a single, unified commercial chassis architecture.
So they use standardized physical hardpoints, the mounting brackets, the structural load paths, the torsional rigidity of the frame. They are engineered to universally accept a massive diesel block, a hydrogen tank array, or a heavy battery pack without requiring structural modification on the assembly line.
Right, but physical mounting is only the simplest layer. The true complexity lies in standardizing the thermal management interfaces.
Oh, because an internal combustion engine requires high-flow liquid cooling for the block, whereas a battery pack requires precise, low-temperature thermal plates.
And a fuel cell generates massive amounts of localized low-grade heat that must be dissipated rapidly. So Triton engineered universal thermal routing.
Meaning the plumbing connections, the heat exchangers, and the flow rates are standardized at the interface point.
Exactly. And the high-voltage electrical architecture operates on universal communication buses. This allows factories to dynamically switch production lines overnight to hedge against sudden supply chain shocks.
So if a geopolitical crisis halts the export of lithium, preventing the assembly of BEV modules, the factory does not idle. The line managers simply shift production allocations to the high-efficiency ICE or hydrogen modules.
Right. The chassis rolling down the line is identical. The robotic welders and assembly technicians are merely slotting a different powertrain module into the universal hardpoints.
It's the ultimate hedge against supply chain fragility. But here's where it gets really interesting. Because managing the physical hardware is only half the equation. You can standardize the mounting brackets and the cooling hoses, but you are still bolting three fundamentally different machines into the vehicle.
Yes.
An electric motor manages torque vectors entirely differently than a turbocharged diesel engine. If the hardware is infinitely modular, how do you manage the software without writing three completely separate operating systems?
That is the existential software challenge. If an OEM attempts to maintain bespoke code bases for a BEV, an ICE, and an H2 vehicle, the software complexity will compound exponentially.
Right, resulting in massive validation bottlenecks and eventual corporate paralysis.
Exactly. So the solution detailed in the Vienna documents is the transition to the true software-defined vehicle, or SDV. This uses deep abstraction layers to fully decouple the machine from the logic.
Okay, the symposium breaks this architecture down into three critical layers. Let's start at the foundation, layer one.
Layer 1 is designated as commoditized hardware. This encompasses the physical actuators, the radar and lidar sensors, the steering racks, the braking calipers, and crucially, the diverse powertrain modules we just discussed.
So in the SDV paradigm, these physical components are viewed simply as dumb hardware. They execute commands and report state data, but they hold no localized complex logic.
Right, they are just muscles waiting for a neurological signal, which makes Layer 2 the most vital component of the entire architecture.
And this is the middleware, specifically centered around the European initiative known as HAL4SDV.
Yes, HAL stands for Hardware Abstraction Layer. HAL4SDV is the decoupling layer. It sits directly between the disparate, chaotic physical hardware of Layer 1 and the high-level logic of Layer 3.
It's like how an Android operating system can run on a Samsung phone or a Google phone, right?
Yeah.
The app doesn't care what the battery looks like. The HAL4SDV is the translator. It's like a modern software API layer.
That's a perfect analogy. If you are coding a cloud application, you don't write code specific to the exact brand of server hard drive your cloud provider uses. You write to the API, and the API translates your command into the specific machine code.
Right, so the HAL4SDV acts as that universal automotive API. It establishes a standardized digital environment that operates on the principle of write once, run anywhere.
Which is critical for the development of advanced driver assistance systems, or ADAS.
Because if an OEM software division writes a brilliant, highly complex AI algorithm for predictive emergency braking, they cannot afford to write and debug one version of that C++ code for the hybrid vehicle that utilizes mechanical brakes, and a completely different version for the BEV that relies heavily on extreme regenerative motor braking.
Exactly. With the HAL4SDV architecture, the AI algorithm sitting on the top layer simply calculates the physics. It determines that the vehicle must decelerate at 4 meters per second squared to avoid a collision. It sends that exact standardized command down to the HAL.
And the HAL receives the request, queries layer 1, and identifies its current environment. If it is installed in a BEV, the HAL translates the command into a high amperage regenerative braking request to the inverter.
Yeah.
If it is in a hybrid, the HAL calculates the optimal blend of regenerative braking and hydraulic pressure to the mechanical calipers.
Right. So the software engineers operating in Layer 3, the SDV applications layer, they never have to factor in the physical hardware variants. Layer 3 is where the OEM develops its brand differentiation. The AI energy management, the fully automated driving stack, the smart cockpit UX.
The Vienna documents included a stark consultant insight regarding this architecture. They stated unequivocally that without this strict software decoupling, mastering physical hardware diversity will bankrupt the manufacturer.
Yes, the engineering hours required to safely maintain, validate, and push over-the-air updates to separate code bases for every powertrain variant would eradicate profit margins.
So mastering the HAL4 SDV abstraction layer is the absolute prerequisite for deploying a resilient multi-powertrain strategy.
Yeah.
Okay, so you have engineered the perfect vehicle. It sits on a universally modular chassis, runs on an abstracted SDV software stack, and can be powered by ultra-efficient electrons, molecules, or fossil fuels, depending on local conditions. You're technically immune to infrastructure and supply chain shocks.
Yes.
But you still have to legally sell that vehicle in a fractured global market. Which brings us to the final and most strategically complex section of the symposium, the geopolitical collision and Sino-European integration.
Right. And this is a good moment to explicitly state to you, listener, that we are now examining politically charged regulatory landscapes from China and the EU. We are strictly impartial observers here. We are reporting on the strategic realities outlined in the Vienna documents, not endorsing any political viewpoint.
Yes, absolutely impartial. So looking at this purely through the lens of market strategy and industrial engineering, the symposium revealed a massive, slow-motion collision between two fundamentally opposed philosophies regarding the future of mobility.
If we connect this to the bigger picture, we can contrast the two massive philosophies shaping the future. First, the Chinese strategic posture is defined as all ecosystem expansion.
Right, shifting from tech follower to global standard setter. They are using massive domestic scale, rapid software loops, and their absolute dominance over the battery mineral refinement supply chain to drive an aggressive export strategy.
By contrast, the European Union is characterized in the documents as a defensive fortress. Europe possesses an unmatched legacy of high-precision mechanical engineering, but they recognize they are highly vulnerable to the speed and cost-down engineering capabilities of the Chinese ecosystem.
So to protect their domestic industrial base, the EU isn't simply relying on traditional economic tariffs. They are actively erecting incredibly rigorous, highly complex environmental and data compliance trade barriers. Let's analyze both sides of this collision, starting with the detailed breakdown of China Roadmap 3.0.
Right. Roadmap 3.0 is a comprehensive, state-backed industrial policy document that dictates the engineering targets for the Chinese mobility sector over the next 15 years. And the timeline is incredibly aggressive.
The first major milestone is 2028. The roadmap mandates that the total carbon emissions of the entire Chinese automotive industry must peak by this date.
Yes, forcing peak emissions 2 full years ahead of the broader national economic carbon targets. And following the 2028 peak, the 2035 target is perhaps the most revealing regarding their strategic pragmatism.
Oh, this part is fascinating, because by 2035, the mandate requires 100% hybridization of all remaining internal combustion engine vehicles.
Right.
Which means China, the nation that overwhelmingly controls global battery production and currently leads the world in EV adoption, is deliberately not mandating a 100% BEV future in their own roadmap. They are actively projecting that ICE vehicles will still comprise roughly 1/3 of their domestic market in 2035.
Yes, provided they are hybridized. Even the most aggressive EV market is keeping ICE alive. The analysts in Vienna noted that this reflects the geographic and infrastructural reality of China. While the eastern megacities can support massive charging grids, the vast rural western provinces simply cannot.
Right, they require the energy density and robustness of the internal combustion engine. They are preserving ICE out of sheer necessity.
But while they remain pragmatic on the powertrain, they are hyper-aggressive on software. The 2040 target mandates an 80% new energy vehicle market penetration combined with the standardization of Level 4 autonomy across the industry.
Now, Level 4 autonomy dictates that the vehicle operates entirely without human intervention under defined conditions. And achieving this natively within the vehicle requires an array of incredibly expensive hardware: long-range lidar, millimeter wave radar, and massive onboard AI supercomputers.
Exactly. And if you force tens of thousands of dollars of sensor and compute hardware into every single vehicle to achieve level 4, you destroy the affordability required to hit an 80% market penetration scale.
Which is exactly why China is pivoting aggressively to V2X integration. Vehicle to everything, specifically focusing on the vehicle road cloud architecture.
This is a fundamental divergence in engineering philosophy. The Western approach to autonomy has generally focused on edge computing, making the car itself an autonomous genius, capable of independently perceiving and reacting to an unpredictable world.
Right, but the Chinese V2X strategy flips that architecture. Instead of putting all the expensive AI computers inside the car, China is putting the computers in the smart city infrastructure to lower the vehicle cost.
Exactly. They are mounting high-fidelity cameras and LiDAR on traffic lights, lampposts, and highway gantries, all connected via ultra-low latency 5G and early 6G networks. The intersection itself becomes intelligent.
So if a pedestrian steps off a curb around a blind corner, the intersection sensors detect it, process the trajectory in the localized edge cloud, and instantly transmit a predictive braking command to the approaching vehicle.
Right. By offloading the perception and processing payload from the car to the infrastructure, automakers can drastically lower the cost of the vehicle. The car acts more as a receiver of environmental data rather than the sole processor of it.
That is the all-ecosystem expansion:
Yeah.
scale, hybridization, pragmatism, and infrastructure-level software integration. Now we must examine the EU's response. How is the defensive fortress constructed?
The absolute cornerstone of the EU's fortress is the implementation of the Digital Product Passport, or DPP.
Now, on the surface, a passport sounds like a standard bureaucratic requirement.
Yeah.
How does a digital document function as a formidable trade barrier?
Well, the EU mandate stipulates that any battery over 2 kilowatt hours must possess a DPP. And this is not a simple PDF. It is an immutable cryptographic supply chain traceability thread,
Oh.
heavily utilizing blockchain-like architectures. The amount of data required within this cryptographic thread is staggering. If you can't prove where the minerals came from, you can't sell the car in Europe.
So the manufacturer must embed verifiable data proving the exact geographic provenance of every critical mineral: the cobalt, the lithium, the nickel.
Yes. And furthermore, they must cryptographically prove that strict human rights and labor standards were adhered to at the specific mine of origin, and it extends far beyond the mine.
The smelting process, the energy mix at the battery cell assembly plant.
Yes. And provide fully audited, chemically specific, end-of-life recycling protocols.
The implication there is massive. An OEM could engineer a brilliant, highly affordable BEV utilizing a localized supply chain, but if they utilize minerals from an opaque mining operation or process the cathode materials in a facility powered by coal, they will fail to mathematically verify a low-carbon footprint within the DPP.
And if the cryptographic thread is broken or the data fails to meet the strict EU thresholds, that manufacturer is legally barred from introducing that vehicle into the European market. Cryptographic data compliance becomes the ultimate non-negotiable barrier to entry.
Wow. And the EU is layering these walls, right? The sources also detail the implementation of LCA carbon walls and the expanding scope of Euro 7 regulations.
Right. The life cycle assessment carbon walls actively mandate the use of EU-smelted low-carbon steel, forcing global manufacturers to localize their heavy supply chains within Europe to meet the total vehicle carbon thresholds.
And Euro 7 fundamentally redefines emission regulations. It extends beyond tailpipes to tire wear and brake particulates.
Exactly. Because BEs are significantly heavier than their combustion counterparts, they exhibit accelerated tire degradation and can generate substantial particulate pollution. So the EU is mandating advanced brake dust capture mechanisms and highly specific tire compound regulations, which demands a level of mechanical and material precision that legacy European Tier 1 suppliers currently dominate. So, analyzing the geopolitical board, we have China accelerating via massive scale, rapid software iteration, and intelligent infrastructure. And we have Europe fortifying its market with cryptographic supply chain passports, localized low-carbon steel mandates, and hyper-strict particulate regulations. Right.
So are we just looking at two separate automotive universes? Do automakers simply split into two distinct companies building entirely different architectures for the East and the West?
Well, the consensus from the symposium is that a total bifurcation is economically impossible. The global supply chains and capital investments are too deeply intertwined. To survive this collision, the major global OEMs and Tier 1 suppliers are adopting a strategy they define as co-opetition.
Co-opetition. Cooperation and competition executed simultaneously. How does that bridge the Sino-European engineering gap?
Global Tier 1s and OEMs must flawlessly marry the core strengths of both ecosystems. The European industrial base must contribute its unparalleled heritage in thermodynamic research, mechanical precision, and its rigorous capability to develop the cryptographic tracking systems required for the DPP.
Right. And conversely, the Chinese ecosystem contributes its absolute mastery of agile software loops, extreme cost-down engineering, and rapid battery supply chain dominance.
Exactly. The ultimate winners will be the organizations that successfully execute this co-opetition, leveraging the hardware precision and verifiable data compliance of Europe with the software agility and scaling power of China.
So what does this all mean for the listener? We have unpacked an immense density of information from these Vienna Symposium documents today. When we synthesize all of these distinct vectors, what is the ultimate conclusion?
The overarching conclusion is that we are moving into a digital physical resilience flywheel. The cars of the next decade are not just vehicles, they are geopolitical shock absorbers.
A geopolitical shock absorber. That perfectly encapsulates it. The macro-geopolitical environment forces regulatory divergence, which necessitates the engineering of highly modular architectures, which enables the financial viability of a resilient technology portfolio.
Right, allowing the simultaneous deployment of advanced BVs, ultra-efficient ICE, and zero-carbon hydrogen. It's a continuous, necessary feedback loop of resilience.
So for you, the listener, the next time you shop for a car, you aren't just choosing between gas and electric. You are buying into a 10 to 15-year multi-powertrain reality, heavily dictated by data sovereignty and global supply chain tracing. You are looking at a machine designed specifically to survive a highly fractured world.
Indeed. And analyzing the trajectory of this flywheel leaves us with a rather profound strategic question to consider as this decade unfolds.
Right. What is the final thought from Vienna?
In a future where the physical engine is completely decoupled from the software that commands it, and where international trade relies entirely on digital product passports, does the ultimate winner in the automotive race actually build the best machine, or do they simply build the most secure cryptographic data thread?
That is something to think about. Thank you so much for joining us on this deep dive. We'll see you next time.
So I want you to imagine, just for a second, that you are sitting on top of a highly reactive chemical fire. And it's, burning at over 900 degrees Celsius.
Which is an absolutely terrifying amount of heat, just to be clear.
Right. And you are separated from this inferno by just a few millimeters of metal and composite material. But the crazy part is you don't feel a thing. You just calmly pull your car over, step out, and wait.
Yeah, and the fascinating thing is that in 2026, that exact scenario is no longer just some theoretical stress test they do in an underground bunker.
No,
It's actually the baseline engineering requirement. Like, that is the literal architecture currently being stamped out on factory floors right now.
which is wild to think about. Welcome to the deep dive, everyone. Today we are unpacking something really special. Have you ever noticed how our obsession with electric vehicles usually focuses on, well, the flashy stuff?
Oh, totally. It's always about the range, the horsepower, or, how fast it can do 0 to 60.
Exactly. But we completely ignore the hidden foundational architecture that actually makes those numbers possible in the first place. So today we are getting into a highly classified synthesis of intelligence out of the 47th International Vienna Motor Symposium.
And for anyone who doesn't operate in the powertrain space, you really need to understand that Vienna is essentially the Davos of mobility engineering.
It's where the heavy hitters go.
Right. It's where the lead architects from every major OEM and Tier 1 supplier get together to just, establish the physical laws of the next decade of transportation.
And the mandate out of this 2026 symposium was crystal clear. The era of just optimizing one isolated variable at a time is completely mathematically exhausted. We have officially hit a brick wall.
We really have. I mean, you can't just tweak the cathode chemistry in a vacuum anymore. If you, say, add more nickel to increase the specific energy of the battery, you instantly break the thermal management system.
Because it gets way too hot.
Exactly. And then, if you try to upgrade the thermal management system to handle that heat, you end up adding all this parasitic mass, which completely ruins your volumetric packaging inside the car.
It's a domino effect. And then, okay, let's say you miraculously solve the packaging. You immediately realize that the local electrical grid down the street literally cannot deliver the megawatt level current required to charge this thing without melting the plug right out of the socket.
Right, because it's a completely coupled thermodynamic system now. Every single piece relies on the other.
Which means the engineers are being forced into this entirely new paradigm. It's a top-down, system-level deconstruction of how we build cars.
And the intelligence we're looking at with this massive shift into three main pillars. We have the physical manufacturing and process revolution, then the actual breakthroughs in chemistry and structural packaging, and finally the energy integration. So how it all connects to the high voltage grid.
Okay, let's unpack this, because this material literally reads like a sci-fi blueprint that they are actively building today. Let's start with that first pillar, the manufacturing bottleneck.
That's the best place to start.
Because honestly, it doesn't matter what kind of exotic, magical chemistry you invent in a lab, if the physical production process requires these massive 50-meter drying ovens and uses up half the power of a small city just to make one battery.
Exactly. And that brings us directly to Volkswagen Group's PowerCo and what they call their unified cell strategy. This is honestly probably the most aggressive industrial pivot we've seen since the industry moved to modular chassis platforms back in the early 2000s.
Okay, so give us the context here. How was the supply chain operating before this unified cell idea came along?
Well, historically, it was all based on bespoke, custom geometry. You had all these different formats fighting for dominance. There were cylindrical cells, prismatic cells, pouch cells.
It's a total free-for-all.
Completely. An automaker would basically design a car, finalize the aerodynamics, map out the passenger cabin, and then they just look at whatever awkward leftover space they had and force the battery supplier to engineer a custom format to squeeze into it.
Right, or they'd do the exact opposite, which might be even worse. They'd lock in a massive supply contract for some off-the-shelf pouch cells, and then the mechanical engineers would have to totally compromise the vehicle's suspension geometry just to fit this bulky battery housing.
Yeah, it's just this constant, endless turf war between the mechanical packaging engineers and the electrochemists.
Well, it sounds like PowerCo has basically stepped in and ended the war entirely.
Yeah.
The unified cell, or UFC approach, basically says, okay, we are using one single standardized prismatic footprint, and this one box is going to cover 80% of all Volkswagen Group vehicle architectures globally.
Yes, they are strictly locking in the physical dimensions. The X, Y, and Z axes are fixed.
But wait, I have to push back on this a little bit. When I look at the sheer velocity of how fast battery chemistry is changing right now, doesn't permanently lock in the physical size of the battery actually stifle innovation?
It seems like it would, right?
Yeah, I mean, if a supplier suddenly figures out a way to make a cylindrical cell that gives you, say, 10% better packing efficiency, PowerCo literally can't use it. They are married to this specific rectangular box. Aren't they just forcing a square peg into a round hole to save money?
I get why you'd think that, but the strategy is actually designed to do the exact opposite. It's meant to accelerate innovation.
Really? How so?
By entirely decoupling the physical format from the chemistry inside. The unified cell is completely chemically agnostic.
Oh, I see. So the outside box never changes, but whatever active materials you want to stuff inside are totally modular.
That is the absolute brilliance of it. Let's look at their MEB Plus platform as an example.
Right.
Say they want to build an entry-level urban EV. They're trying to hit that really tough 25,000 euro price point, but still offer 450 kilometers of range.
Right, the holy grail of mass adoption.
Exactly. So for that car, they just fill that standardized prismatic box with lithium iron phosphate or maybe even one of the new sodium-ion chemistries. The energy density isn't incredible, but the raw material cost is virtually nothing.
Okay, and because the box is exactly the same size, the chassis engineers don't have to redesign a single mounting bracket on the car.
Zero changes. The high voltage bus, the cooling plates, the physical crash structures, they all stay exactly the same. And then if they want to build a super high performance Audi SUV on that exact same production line, they just drop in a high nickel NMC cell instead.
Wow. So the factory automation, the robots doing the handling, the module assembly, it just keeps running at maximum speed, regardless of what generation of chemistry is inside the casing.
Exactly. It drives these unprecedented economies of scale, which is basically the only way to survive the massive market consolidation happening right now.
That makes total sense. But standardizing the outer box still doesn't fix the underlying thermodynamic nightmare of how we actually make the electrodes that go inside the box.
Yeah.
And I know the symposium documents put a massive emphasis on this new dry coating process.
Yeah, we have to talk about the latent heat of vaporization here to really understand why this dry coating is such a foundational leap.
Let's do it. Walk us through the old way first.
So traditional wet coating is basically an industrial paradox. You start with these perfectly dry, active material powders, your graphite and your lithium metal oxides.
Right, the stuff that actually holds the energy.
Exactly. But to apply those dry powders onto the thin metal current collector foils, you have to mix them with a solvent. And not just any solvent, a highly toxic one called NMP. You mix it all up to create this rheologically stable slurry.
Okay, so you're basically taking dry ingredients and making a giant, watery, highly toxic cake batter just so you can spread it out onto a sheet of copper.
It was a perfect analogy. You run this toxic sludge through a slot die coater and spread it a few microns thick. But the second it's coated, that solvent becomes a massive liability. You obviously cannot put a battery cell together if it's full of wet NMP solvent.
So you have to bake it back out.
Right. So this continuous sheet of wet foil moves into these drying ovens, and these things are frequently 50 meters long,
50 meters.
just for drying.
Yes. You are pumping in massive amounts of endothermic heat to basically boil off the liquid you just intentionally added a minute ago.
That sounds horribly inefficient.
It is. And you have to do it with extreme precision, because if you heat it too fast, you crack the binder matrix or you oxidize the metal foil. And on top of all that, you have to capture and distill the toxic NMP vapor so you don't vent poison into the atmosphere.
So it's just this massive energy-hogging thermodynamic loop where you're spending gigawatt hours of power purely to reverse a step you created yourself. Which is exactly why PowerCo's dry coating rollout is so disruptive. They literally bypass the entire solvent phase. No liquids at all.
So how do they get the powder to stick to the foil if it's not a wet paste?
Instead of a slurry, they use incredibly high shear forces to fibrillate a specialized binder, usually a type of PTFE. This fibrillation process creates this microscopic web-like matrix that physically traps all the dry, active powder particles together.
Oh, wow. So they are effectively calendaring it. They're just rolling this dry, powdery web under immense pressure directly onto the foil.
Exactly. No NMP, no toxic slurry, and most importantly, no evaporation required.
The numbers in the symposium data on this are just staggering. By eliminating that vaporization phase, it reduces the total energy consumption of electrode production by exactly 30%.
And that 30% isn't just a win for their operational budget. It drastically lowers the baseline carbon footprint of the battery itself before the car has even been built.
Right, the embedded carbon is massively reduced. And what about the factories themselves?
Well, it completely alters the capital expenditure equation. Because you are stripping out 50 meters of massive drying ovens and all the expensive solvent recovery systems, the actual physical footprint of the gigafactory shrinks by 15%.
Which is huge. I mean, when you're talking about building these standardized 200 gigawatt-hour mega facilities in places like Salzgitter, Valencia, and St. Thomas, a 15% smaller building means you can construct them way faster and for way less upfront capital.
You're just stamping out identical gigafactories with the same precision as the battery cells they produce.
Okay, so we've fixed the manufacturing bottleneck, we have standardized box, and we have a highly efficient, dry way to coat the electrodes. But what is the ultimate holy grail chemistry we are actually putting inside that unified box?
Well, the consensus presented in Vienna points to a definitive commercial leap for solid-state technology. Specifically, they highlighted the QuantumScape QSE5 cell.
Okay, here's where it gets really interesting to me. The documents describe the QSE5 as having an anode-free reality, which, if you know anything about a standard battery cell, sounds completely impossible.
It definitely breaks the traditional rules. Normally, a lithium-ion cell has a cathode packed with lithium, a liquid electrolyte, and a massive graphite anode that acts as a physical host matrix.
Right, so when you plug your car into charge, the lithium ions leave the cathode, swim across the liquid, and physically embed themselves into the graphite on the other side.
Yes, they intercalate into the graphite structure, and we only use that heavy, bulky graphite for one specific reason: to prevent the lithium from plating as a pure metal.
Because pure lithium metal is highly irregular, right? If you just try to deposit it onto a bare metal plate in a liquid electrolyte, you get dendrites.
Exactly. Dendrites are the enemy of all batteries. They are these sharp, microscopic crystalline structures that grow like needles.
And once they grow long enough, they just pierce right through the porous plastic separator, touch the cathode, and boom.
Boom. You get an instantaneous hard short circuit, followed by catastrophic thermal runaway. So, for decades, we've just accepted the parasitic weight and volume of the graphite anode purely as a cage to keep the lithium well behaved.
But the QuantumScape QSE5 just gets rid of the cage entirely. When this cell rolls off the manufacturing line, there is absolutely no physical anode inside it. It's just a heavily loaded cathode, a solid ceramic separator, and a bare metal current collector.
That's right. No graphite at all.
So wait, if there's no anode to start with, where does the energy actually go when you charge it the very first time? How does it not just instantly form dendrites and blow up the brand new cell?
It all comes down to the underlying physics of that proprietary solid ceramic separator. During that very first formation charge at the factory, the lithium ions migrate out of the cathode, just like normal.
But they aren't swimming through a liquid this time.
Right. They have to pass directly through the solid crystal lattice of the ceramic. And when they finally reach the interface between the ceramic and the bare metal current collector, they plate directly as a perfectly uniform, dense layer of pure lithium metal.
It's essentially manufacturing its own anode in real time, right inside the cell, during that first charge.
Exactly. It creates its own anode in situ. And the reason it doesn't form dendrites is purely due to mechanical force.
Okay, let's break that down.
So the ceramic separator has an incredibly high shear modulus. It is physically tougher than the yield strength of the lithium dendrite trying to grow into it.
Ah, I see. So the yield strength is the physical pressure it takes to snap or bend the dendrite needle. And the shear modulus of the ceramic is its resistance to being pierced.
You've got it. Because the ceramic barrier is literally harder than the microscopic needle trying to penetrate it, the dendrite is just mechanically crushed before it can ever grow.
That is fascinating. So by relying on this super tough ceramic barrier, you can safely harness pure lithium metal, which is the ultimate energy carrier, but you get to completely ditch the dead weight of the graphite.
And the volumetric gains from doing that are just staggering. PowerCo's validation testing confirmed that the QSE5 hits an incredible 844 watt-hours per liter.
Which is a massive leap. But what really caught my eye in the data was the discharge rate. Normally, if you have a cell with ultra-high energy density, it has really high internal resistance, meaning it's kind of sluggish to give that power up.
Right, there's always been a trade-off.
But the data shows this cell can handle a 10C continuous discharge rate.
Which completely breaks the traditional Ragone plot trade-off between specific energy and specific power. A 10C continuous rate is frankly absurd for density this high.
To put 10C into perspective for the listener, that means this cell can safely dump its entire massive energy capacity in exactly 6 minutes. Yeah, we are talking about sustained hypercar-level power output without inducing any fatal thermal degradation. And the charging is just as fast. It can do an extreme fast charge from 10% to 80% in 12 minutes.
And that extreme performance brings us right to the longevity metrics. The historical problem with cycling pure lithium metal has always been Coulombic efficiency.
Because it degrades over time.
Right. Every single time you plate and strip the lithium metal, a tiny microscopic fraction of it reacts with the liquid electrolyte. It creates the solid electrolyte interphase, or SEI, layer, which consumes your active lithium. Eventually, the cell literally dries out and dies.
But because this QuantumScape cell uses a solid ceramic separator, it doesn't react with the lithium metal the way a liquid does, right?
Exactly. It is chemically stable against pure lithium metal.
Yeah.
The intelligence presented in Vienna confirms that it retains over 95% of its original capacity after 1,000 deep cycles.
That's incredible. 1,000 deep cycles on a pack this dense is roughly 500,000 kilometers of driving. And the battery basically still has factory fresh capacity.
It's a generational leap.
But okay, I have a major reservation here. We've known about the theoretical benefits of ceramic solid-state batteries for years, maybe decades. The problem has always been actually manufacturing them at scale.
Yes, manufacturability has been the wall.
Because ceramics are inherently brittle, they get thermal stress fractures when you try to make them in high volumes. So how on earth are they achieving an 80 gigawatt-hour licensing scale without just churning out massive amounts of defective, cracked ceramics?
That was actually the crucial industrial enabler they presented, the proprietary QS Cobra sintering process.
Okay, remind us what sintering actually is.
Sintering is the thermal process where you take a compacted powder and heat it up to just slightly below its melting point. The heat causes the atoms to diffuse across the boundaries of the particles, fusing them all together into a single solid piece.
Like firing a clay pot in a kiln.
Exactly. It's how you make advanced ceramics. But traditionally, it is incredibly slow and highly energy intensive. You have to leave the material in these massive kilns for a very long residence time.
And that's where the defects happen.
Right. Long baking times lead to uneven thermal gradients across the material, which creates microscopic grain boundary defects in the ceramic. And a grain boundary defect is the exact weak point a dendrite will exploit to push through.
So how does this Cobra process fix that?
The Cobra process uses a highly accelerated continuous rapid thermal processing technology. It fundamentally changes the thermodynamics of the sintering phase. It fuses the ceramic precursor materials with absolute uniform density in a fraction of the time.
Wow, so it's super fast, and because it's fast, it completely eliminates those thermal stress fractures that plagued all the earlier solid-state attempts.
Yes. They solve the mechanical fragility problem, which finally enables gigascale roll-to-roll manufacturing of a ceramic separator. That is what makes the anode-free reality possible.
It's the ultimate chemistry, finally commercialized. However, the symposium documents do offer a very grounded reality check here.
They do. Solid state is definitely the future, but it will only capture the very high-end premium segments first.
Right. For the vast majority of the immediate future, like the mass market over the next 5 years, we are still going to be relying on highly evolved liquid-based lithium-ion cells. But to bridge that energy density gap, they are packing these cells with unprecedented levels of nickel.
Which brings us right back to the terrifying scenario you opened the show with, sitting on top of a 900-degree chemical fire.
Yeah, because while nickel delivers incredible specific energy, it creates an absolute nightmare when it comes to thermal stability.
We have to talk about the thermal trilemma. The intelligence profiles this specific cell, the Ferasis P79 NMC90 pouch cell.
An NMC90 means the cathode active material is basically 90% pure nickel, with just a tiny bit of manganese and cobalt thrown in to keep the structure somewhat stable.
Right. And the specific energy on this thing is massive, 314 watt-hours per kilogram. But the trade-off is severe. As you increase the nickel content that high, the activation energy required to trigger a thermal runaway drops drastically.
That's a huge vulnerability.
It is. In a high nickel cell like this, if you get an internal short circuit, maybe from a microscopic manufacturing defect or a really bad mechanical crash, the localized Joule heating causes the internal temperature to spike almost instantly.
And once it hits a certain critical temperature threshold, the highly dilithiated crystal lattice of the cathode physically collapses on itself.
And when that lattice collapses, it releases high-pressure oxygen gas directly into the sealed pouch,
releasing pure oxygen into a liquid electrolyte that is made of highly flammable organic carbonate.
Exactly. So the battery essentially generates its own fuel, its own oxidizer, and its own ignition source, all locked inside a sealed envelope.
And the result is this instantaneous, violent exothermic chain reaction. The data on the P79 cell shows that during a runaway event, peak localized temperatures exceed 900 degrees Celsius.
And remember, in a modern 800-volt cell-to-pack architecture, you might have 200 of these cells packed tightly together.
So how do you stop it? The traditional engineering approach was just static containment, right? Like putting armor around it.
Yes. The thought process was, if cell number 42 goes into thermal runaway, we absolutely cannot let that 900-degree heat propagate over to cell 43.
So the Powertrain architects literally wrapped every single individual cell in these thick, passive aerogel blankets or ceramic composite armor.
But from a vehicle packaging standpoint, that is a catastrophic compromise.
It makes no sense.
Right.
You spend billions of dollars developing this advanced NMC90 chemistry just to gain a 20% bump in specific energy, and then you immediately throw all those gains away because you have to fill up the battery module with static armor that doesn't hold a single electron of power.
Exactly. It's parasitic dead volume. And the data from Vienna shows that this static physical armor consumes between 5 and 10% of the total pack volume. And it adds a significant cost, like 1 to 2 euros per cell.
It's basically the equivalent of trying to safely contain a high explosive detonation by just building thicker and thicker concrete bunker walls around the bomb. Eventually, your bunker walls are so thick that you have no physical room left inside the bunker for anything else.
Which is why Ferasis completely changed their approach. They developed what they call no-TP, or no temperature spread technology.
Okay.
They shifted entirely away from static physical armor and moved to dynamic enthalpy routing.
Okay, let's dissect dynamic enthalpy routing, because the fluid dynamics here are just fascinating. Enthalpy, for those wondering, is just the total heat energy contained in the system.
Right, and instead of trying to bottle up that massive surge of heat in a bunker, they are treating the thermal runaway event like a rocket exhaust plume.
That is such a great analogy because when the cell vents, it isn't just releasing hot air. It is violently ejecting superheated plasma, vaporized electrolyte, and solid particulate matter at an extreme velocity.
So what the no-TP architecture does is incorporate precisely engineered directional venting channels directly into the structural frame of the battery pack itself.
They're building-shaped exhaust manifolds for the fire. The literal millisecond the internal cell pressure breaches the safety valve, all that 900-degree gas is forced down these specific reinforced channels.
And it instantly directs all that thermal mass safely away from the adjacent vulnerable cells.
But just blowing the hot gas away isn't enough, right? The exhaust gas is still way too hot. It would eventually just melt the structural channels anyway.
Exactly. So the real breakthrough is how they coupled that directional exhaust flow with a high conductivity, dual-phase liquid cooling matrix.
Wait, so the cooling system isn't just sitting there passively keeping the battery at a nice room temperature?
No, during a runaway event, the cooling system actively acts as a massive heat sink, specifically for the exhaust gas.
Oh, wow.
Yeah. The immense thermal energy of that venting plasma is instantly transferred into the liquid coolant running through the channels, and the coolant undergoes a rapid phase change. It boils.
And boiling absorbs a massive amount of latent heat.
Precisely. It violently extracts the heat, drastically dropping the temperature of the exhaust gas in real time as it is safely routed out of the pack casing.
So by dynamically extracting that enthalpy the moment it happens, they completely eliminate the need to put those thick, heavy aerogel barriers between every single cell.
And the net result is unprecedented packaging efficiency. They are achieving 250 watt-hours per kilogram at the module level because over 80% of the volume is actual active cell material, not just static armor.
And doing all that, it still easily surpasses those ultra-strict safety regulations, right? Like the UNES R100 Rev.3 and the Chinese GB standards, which strictly mandate zero thermal propagation into the passenger cabin.
Yes, one cell basically sacrifices and destroys itself. It instantly exhausts the plasma safely, and the rest of the battery pack just remains entirely perfectly stable.
It is an absolute masterclass in managing extreme thermodynamics. But, managing the thermal limits naturally leads to rethinking the physical limits of the battery.
How so?
Well, if we no longer need massive static armor to protect the cells from each other, how do we protect the cells from the road? Or maybe the better question is, how do we use the cells to actually protect the car?
Ah, yes. This brings us to a total architectural paradigm shift. We're looking at the BMW Gen 6 large cylindrical cell system.
Which is interesting because for the last 5 years, it seemed like the entire industry consensus was moving entirely away from cylindrical formats.
It was. When you pack a bunch of cylinders together in a box, the tangent points where the circles touch create inherent void spaces. You get those little diamond-shaped gaps of dead air.
Whereas prismatic and pouch cells pack perfectly flush, right? So they naturally yield a higher volumetric density.
That is absolutely true, but only if you view the battery strictly as passive cargo being carried by the car.
Right.
BMW, however, recognized a very distinct mechanical advantage that is native to the geometry of a cylinder. A tightly wound cylindrical cell, when it's encased in a deep-drawn steel can, possesses incredibly high native compressive strength.
Because it's literally a solid steel pillar filled with dense, tightly wound metallic foil.
Exactly. It is remarkably resistant to buckling under severe longitudinal or lateral loads, and the Gen 6 system specifically leverages the 4695 format.
So that's 46 millimeters in diameter and 95 millimeters tall.
Right, and by utilizing this specific geometry, BMW is executing what they call a pack-to-open-body chassis layout.
Okay, let's put this into context for traditional automotive manufacturing. Historically, you build this heavy, rigid steel or aluminum space frame, right? It has massive structural cross members running through the floor just to handle the torsional twisting of the car and to absorb the impact forces if you get in a crash.
Correct. And then once you have that heavy frame, you take a heavy battery module, put it inside its own heavily armored aluminum box, and you bolt the whole thing underneath that chassis.
So you basically have two completely independent structural systems carrying totally redundant mass.
Exactly. So the pack-to-open body concept just eliminates that redundancy entirely. The battery pack no longer has a traditional top cover, and the vehicle chassis no longer has a traditional floor pan.
So the cells themselves transition from being just passive energy storage into becoming active, load-bearing structural members of the car.
Yes. Thousands of these highly rigid 400-600E5 steel cylinders are bonded together using a specialized structural adhesive, which creates this incredibly stiff honeycomb-like matrix.
And then that honeycomb is integrated directly into the open floor of the chassis.
The battery pack literally is the structural floor of the vehicle.
That is wild. So the sheer physical force from a side impact collision isn't just absorbed by the outer door sills. The crash force is transferred directly through the steel casings of the battery cells themselves.
Right. And from a pure engineering perspective, the Euler buckling loads of that specific honeycomb matrix are actually superior to traditional hollow steel crossmembers.
Okay, I understand the structural elegance of it. It's brilliant. But I immediately see a massive, glaring repairability issue here.
You mean regarding cell failure?
Yeah. If you have thousands of individual cells structurally glued into a permanent load-bearing honeycomb, and just one single cell drops a voltage or gets an internal short, you can't exactly just unbolt a module and swap it out. The entire structural floor of the car is compromised.
That is the calculated risk of high-level integration. You are intentionally trading away module-level serviceability in order to achieve system-level optimization.
The manufacturing quality control would have to be absolutely flawless. You are effectively welding the energy storage directly into the unibody of the car.
It does require extreme precision. But the performance metrics that BMW projects kind of justify that risk.
Right.
By eliminating all those redundant structural crossmembers and the heavy module casings, they free up immense internal volume.
The briefing notes say it's a 20% increase in volumetric energy density at the pack level, purely due to the structural integration.
Think about that. You're packing 20% more active energy-holding chemistry into the exact same physical footprint.
Which is how they are projecting a 30% extension in driving range. They're pushing the theoretical boundary toward 900 kilometers on a single charge. That's over 550 miles.
And perhaps even more critically for the actual business model, this deep module integration drastically streamlines the factory assembly line.
Less parts, less steps.
Exactly. Eliminating redundant parts and simplifying how the pack mates to the open body drives a projected 40 to 50% total cost reduction in the eDrive system.
A 50% cost reduction in the powertrain is the absolute holy grail. That is the exact profit margin necessary to finally bring high-performance, long-range EVs into direct price parity with internal combustion engines without having to rely on government subsidies.
It is the ultimate expression of system-level optimization. They completely reinvented the physical architecture of the vehicle just to utilize the native mechanical properties of the battery format itself.
Okay, so let's recap where we are. We've standardized the manufacturing process, we've perfected the anode-free solid-state chemistry, we've dynamically managed the 900-degree thermal runaway, and we have integrated the cells to act as the literal physical skeleton of the car.
We have built the ultimate physical asset.
We really have. But an asset of this magnitude, a pack capable of storing well over 100 kilowatt hours of energy, creates a massive secondary bottleneck. How do you physically interface a battery that powerful with the electrical grid?
And that is the final frontier detailed at the symposium: energy integration and charging topology. Specifically, they are preparing for the leap to megawatt-level charging, or MCS infrastructure.
Because as pack capacities scale up, especially for long-range architectures or heavy-duty transport trucks, a standard 350 kilowatt fast charger just simply isn't fast enough to maintain acceptable logistics turnaround times.
Right. The new MCS standard is designed to push 3.75 megawatts of power.
To conceptualize that for everyone listening, we are looking at an operating voltage of roughly 1,250 volts and a sustained current of 3,000 amps.
And let's really talk about the physical reality of pushing 3,000 amps, because this isn't just a matter of using a thicker cable at the charging station.
No, not at all. When you push that much current through the physical mating interface, meaning the actual copper pins inside the charging plug and the receptacle on the vehicle, you slam headfirst into a brutal thermodynamic limit: extreme joule heating.
It's basic I squared R loss. The heat generated is proportional to the square of the current multiplied by the electrical resistance at the connection.
Let's actually do the math on that. If you are pushing 3,000 amps and your plug interface has a tiny microscopic contact resistance of just 1 single milliohm, the localized heat generated right at that connection point is 9,000 watts.
Which is insane.
You essentially have the thermal output of a literal industrial furnace, highly localized on a piece of copper, the exact size of your thumb.
And if you attempt to manage that kind of heat with standard convective air cooling or even traditional water cooling channels routed through the thick cable casing, it won't work. The thermal boundary layer prevents efficient heat transfer.
The copper pins would experience severe thermal degradation, they'd oxidize, and eventually they would just undergo localized melting. You'd weld the plug to the car.
It's very akin to the thermal management challenges of atmospheric reentry for a spacecraft. You have this massive, highly localized heat flux that absolutely must be dissipated instantly.
So what's the fix? The solution, detailed by Shell and Castrol in the documents, involves breaking that thermal boundary layer entirely through dielectric immersion cooling.
Right. So instead of running a jacket of liquid coolant around the outside of the cables and the contact points, dielectric immersion places the bare electrical conductors and the extreme high-power contact interfaces directly inside a specialized non-conductive fluid.
Wait, so the fluid is literally flowing directly over the bare exposed metal that is actively carrying 1250 volts.
Exactly. And because the fluid is highly dielectric, meaning it's a near-perfect electrical insulator, it doesn't short the circuit.
Okay, that makes sense.
But its thermal conductivity is orders of magnitude higher than air or jacketed water systems. It essentially eliminates the contact thermal resistance by absorbing the heat directly from the source via nuclear boiling or forced convection.
Which ensures that even under a staggering 3,000 amp load, the charging interface remains completely thermally stable. It allows the vehicle to accept a 5C charge rate without the system ever having to thermally derate.
Meaning the charger doesn't have to throttle the power down to a crawl just because things are getting too hot.
Right, but fluid dynamics is only half of the solution they presented. The other half is purely material science. Specifically, advanced powder metallurgy developed by a company called Sinter.
Right, because to reduce that I² R loss, you absolutely must minimize the R. You have to lower the electrical resistance at the physical contact interface.
And when you machine a traditional copper or aluminum pin on a lathe, the microscopic surface of that metal is actually quite rough, isn't it?
It is. So when two machine pins mate together, they only physically touch at a few microscopic high points, which are called asperities.
And that significantly reduces the actual physical surface area that is transferring the current, which naturally drives up the resistance and creates heat.
Exactly. So what Sinter does is utilize a highly optimized powder metallurgy process. Instead of cutting or machining a bulk piece of solid metal, they compress and sinter incredibly precise metallic powder formulations.
Wow. So they can literally engineer the exact porosity and the crystal grain structure of the component itself.
They can engineer a contact surface that geometrically maximizes the microscopic mating area. This drastically lowers the contact resistance under massive mechanical and electrical load. It's fundamentally optimizing the electrical conduction pathway at the atomic level.
So, okay, we now have the physical infrastructure to blast 3.75 megawatts of power into the vehicle safely. But the 2026 paradigm dictates that these massive energy reserves sitting in the car cannot just sit idle in your driveway.
Right. The vehicle must act as a bidirectional node on the electrical grid, vehicle-to-grid or V2G integration.
Which entirely necessitates a complete overhaul of the onboard inverter topology. Let's get into the high-voltage electrical engineering here, because the traditional two-level inverter currently used in almost every EV on the road today is, quite frankly, a really brute force instrument.
It really is. Let's explain what it does. The inverter's primary job is to take the direct current, the DC power from the battery, and turn it into the alternating current, the AC power, needed to spin the traction motors. Or, in the case of V2G, to feed power back into the AC electrical grid.
And a standard two-level inverter does this by basically taking the entire massive high-voltage potential of the battery pack, say 800 volts, and aggressively switching it fully on and fully off thousands of times a second using IGBT or silicon carbide switches.
Yes. It's attempting to approximate a smooth, rolling AC sine wave by rapidly slamming 800 volts of square wave pulses.
Which is incredibly inefficient.
Highly inefficient. That aggressive switching generates massive total harmonic distortion, or THD. It creates high-frequency electrical noise, dangerous voltage spikes, and significant switching losses that manifest as heat.
And to make that jagged power actually usable by the neighborhood grid, you have to run it through these massive heavy inductor filters just to smooth out the waveform. It's like trying to perfectly trace a smooth circle using only a thick, jagged marker.
That's a perfect way to put it. And that's why the intelligence from Vienna details the wide deployment of the modular multilevel converter, or MMC. This was developed by a consortium including Capgemini, Stable Energy, and RPTU.
The MMC topology is just fundamentally elegant. Instead of one massive switch violently modulating the entire 800-volt pack at once, an MMC architecture breaks the battery pack down into multiple, smaller, lower voltage modules.
And each one of these lower voltage modules has its own integrated lower power switching hardware, often utilizing what's called cascaded H-bridge circuits.
Right, so the master controller dynamically links these lower voltage modules in series or parallel, rapidly stepping the voltage up and down in very small, precise increments.
So instead of using one thick, jagged marker, you're drawing the sine wave using thousands of tiny, perfectly precise dots.
Exactly. And the output is a highly synthesized, remarkably pure AC waveform directly from the battery pack itself. Because the voltage steps are so small, the switching losses drop to near zero, and the total harmonic distortion is effectively eliminated.
You no longer need the heavy parasitic harmonic filters weighing the car down.
The efficiency gains for just driving the electric motor are excellent on their own, but the implications for V2G are absolute game changers. Because the MMC controller is actively managing the output of each individual low-voltage module, it performs continuous dynamic active balancing.
And this is the critical systemic shift. In a traditional battery pack, the cells are hardwired together in a fixed, permanent series string.
Which means the entire pack is only ever as strong as its weakest cell. If just one module degrades slightly due to thermal variance or manufacturing tolerance, it acts as a massive bottleneck. It severely limits the capacity and power output of every perfectly healthy cell connected in series with it.
Which is exactly why automakers require extreme, highly expensive cell consistency sorting at the factory. Every single cell must be matched perfectly before assembly.
But the MMC controller changes all of that. It dynamically isolates each module. If it detects that module A is slightly degraded and has a higher internal resistance, it simply draws slightly less current from module A and proportionally increases the draw from a stronger module B to seamlessly synthesize the required AC output.
It dynamically compensates for chemical degradation in real time.
Which means you completely eliminate the need for strict cell consistency sorting at the factory.
And this is really where the entire 2026 ecosystem just clicks together perfectly. If the MMC hardware can dynamically balance totally varying capacities and internal resistances, you are no longer limited to using identical factory-fresh batteries.
Oh, wow. This is the ultimate enabler for second life battery integration.
It is. You can literally physically combine a highly degraded 5-year-old NMC module right alongside a brand new solid-state module and perhaps throw in a cheap LFP module, all into the exact same grid storage system.
And the MMC inverter acts as the orchestrator. It pulls exactly what each totally different module can safely provide, effortlessly weaving them all together to stabilize the local electrical grid.
It fundamentally alters the life cycle economics of global energy storage.
It's just incredible. We started this deep dive looking at a factory floor trying to optimize the physical manufacturing of a chemical box. But when you follow the engineering thread all the way through, from eliminating the massive thermodynamic waste of wet coating ovens to stripping the bulky graphite anode entirely for solid-state deployment,
To actively exhausting 900 degrees of plasma during thermal runaway.
right, to integrating the very casing of the battery into the structural skeleton of the chassis itself, and finally, to utilizing modular multi-level converters to synthesize perfect grid-level AC power.
You see very clearly that the 2026 Vienna Motor Symposium wasn't just outlining a new generation of vehicles. They were outlining the architecture of a continuous, highly integrated global energy ecosystem.
The vehicle is no longer just a localized consumer of energy. It is a fortified, hyper-efficient, structurally integrated mobile power plant. Which leaves us with a final concept to analyze today. If the implementation of modular multi-level converters means we can seamlessly mix heavily degraded chemistries with bleeding-edge cells without any systemic bottleneck, how long until the very concept of a dead battery is completely obsolete?
That's a great question.
I mean, if an MMC controller can extract perfect, useful sine wave utility from a battery functioning at 30% capacity, perhaps the end game isn't recycling the raw materials at all. Perhaps every single cell manufactured from this point forward becomes a permanent, actively balanced node in a decentralized, immortal neighborhood power grid. The battery never truly dies. The MMC just reassigns its purpose.
The physical constraints have been entirely removed. The limitation now is purely how efficiently we can network the storage.
The unseen architecture truly is where the profound leaps are made. Thank you for joining us on this deep dive. Right now, the electric motor inside a standard EV sitting in your driveway, assuming you have one, probably maxes out at, I don't know, maybe 15,000 RPM.
Yeah, 15 to 20,000 is really the ceiling for most consumer stuff today.
Right. But last month, deep inside the Hofburg Palace in Austria, engineers basically gathered behind closed doors and unveiled a motor spinning at 35,000 RPM.
Which is honestly a terrifying speed when you think about the physics involved.
I mean, that is double the speed of a screaming Formula One engine, and the internal components of this thing are suspended entirely on a cushion of air. It's wild. So the big takeaway here, the era of just slapping a bigger battery into a car to get more ranges, well, it's dead.
It really had to die. I mean, we hit a physical wall.
Right.
For the last decade, the auto industry just operated under this fairly blunt philosophy. Like, if you want a car to go further, just pack more lithium-ion cells into the floorboard.
Make the battery heavier.
Exactly. But you eventually reach an inflection point. The sheer mass of the battery pack starts creating this cascading set of problems for the vehicle's rolling resistance, the structural requirements, the suspension.
Yeah, you end up burning a massive percentage of your stored energy just to haul the battery itself around.
Exactly. Diminishing returns.
Which brings us to the mission for today's deep dive. Because if you're listening to this, you are someone who wants the ultimate shortcut to being well-informed.
Yeah.
You want the signal through the noise without needing a PhD in electrical engineering to actually understand it.
Right, we're doing the heavy lifting for you.
Exactly. So today, we are taking you to the absolute bleeding edge of the mobility transition, straight into the intelligence coming out of the 47th International Vienna Motor Symposium from May 2026.
And we should clarify, the Vienna Symposium is, it's not a consumer auto show.
Right, no flashy lights or celebrity spokespeople.
No, not at all. You won't find concept cars here. This is a gathering of over 1,000 senior R&D architects, Tier 1 suppliers, powertrain engineers. I mean, these are the people writing the physical blueprints for the next decade of transportation.
The people actually building the stuff.
Exactly. And the consensus from the floor this year was super clear. The pure EV hype cycle has matured into a demand for what they call a resilient technology portfolio.
Okay, let's unpack this. Because if the battery is no longer the sole focus of the EV transition, the battleground has to shift somewhere else.
It's shifted entirely.
Yeah, looking through the research from the symposium, the entire focus is now on what they're calling extreme electric drives and power electronics. Engineers are shrinking motors, they're tearing out rare earth metals, and completely rethinking how microchips handle heat.
It's all about system-level extreme optimization now.
So let's start with that 35,000 RPM motor I mentioned at the top, because the mechanical implications of spinning a metal cylinder that fast just seem impossible to manage.
Right. Well, to understand why they are pushing the speeds that high in the first place, we have to look at the fundamental physics of an electric motor.
Okay, lay it on us.
The overarching goal right now is to make the entire electric drive system lighter and cheaper.
Which means the physical box containing the motor needs to get smaller.
Right. But, and here's the catch, consumers and commercial fleet operators still demand high power output.
Yeah, I mean, you can't just sell a heavy-duty semi-truck with a tiny motor that has zero pulling power.
Exactly. The math just doesn't work. So the relationship here is governed by a strict equation. Mechanical power is basically the product of torque and rotational speed.
Torque being the twisting force.
Yeah, the actual muscle, the force that gets a heavy load moving from a dead stop. And then rotational speed is just how fast the internal rotor is spinning, measured in RPM.
Okay, so power equals torque times speed.
Right. So if you shrink the physical size of the motor, you are literally removing magnetic material and copper.
Which means less muscle.
Exactly. Less material means less magnetic flux, which means less torque.
Oh, I see. So if your torque drops because you made the motor physically smaller, the only mathematical way to keep your overall power output high is to absolutely crank up the RPM.
That is the trade-off. You have to spin it faster. Now, historically, pushing past 15 or 20,000 RPM was considered just too mechanically volatile for a mass-produced car.
It would just shake itself apart.
Basically, yeah. But the data from Vienna shows the industry has pushed right past that threshold. I mean, GAC's HipTech brand presented their Quark Electric Drive 2.0.
And what does that hit?
That one reliably hits 30,000 RPM. And they are achieving a power density of 13 kilowatts per kilogram.
Okay, wait. Just to visualize that for a second, for everyone listening, for every single kilogram of weight in that motor, it generates 13 kilowatts of power.
Yeah, it's incredible.
I mean, a standard internal combustion engine might sit at around, what, 1 or 2 kilowatts per kilogram?
Yeah, around there. So it's a staggering leap in density.
But you noted in the research that Garrett Motion went even further than GAC.
They did. Garrett introduced a new e-Powertrain lineup. Specifically, they have a 3-in-1 e-axle for passenger cars and a 2-in-1 e-beam for commercial vehicles.
And those operate at the 35,000 RPM mark.
Yes, 35,000 RPM. And by engineering a system that can actually survive those speeds, they reduce the physical volume and the overall weight of the motor system by 40%.
Wow, 40% smaller.
Right. And they also reduce their reliance on sensitive materials like copper and magnetic elements by 30%.
Okay, wait, I have to push back on the mechanics of this, because if I take a solid metal rotor and spin it at 35,000 RPM, the centrifugal forces alone are immense.
Oh, they are.
But more importantly, what is physically holding that spinning rotor in place? Like, traditional electric motors use steel or ceramic ball bearings, right?
Yeah.
Packed with lubricating oil.
Yes, traditional contact bearings.
So at 35,000 RPM, wouldn't the sheer friction heat just cause the oil to boil off? Or turn it to sludge and just tear the bearing apart?
The lubrication breakdown you're describing is exactly the failure mode that capped motor speeds for years.
It's literally the physical limit.
Yeah. At 35,000 RPM, the surface speed of the bearing components generates heat faster than any traditional cooling method can dissipate it.
So the metal expands?
The metal expands, the microscopic tolerances just vanish, and the bearing seizes violently.
Right. So how did Garrett Motion fix it?
They bypassed it entirely. They adapted a technology they've actually spent decades refining for aerospace applications and high-performance turbochargers. It's called the oil-free foil bearing.
Oil-free,
Yeah.
as in there is no liquid lubrication whatsoever between the spinning rotor and the stationary housing.
None. Zero oil.
How is that possible?
The system relies entirely on fluid dynamics, specifically the viscosity of air.
Air viscosity.
Yeah. So in a foil bearing, the spinning shaft is surrounded by a stationary housing, and that housing is lined with a very thin, flexible, corrugated metal foil.
Corrugated, like cardboard.
Visually, a bit like that, yeah. But made from highly specialized, high-temperature alloys, like inconel. Now, when the motor is completely powered down, the rotor actually rests physically on this metal foil.
Wait, that sounds like it would cause massive wear the exact moment the motor starts spinning, just metal grinding on metal.
It absolutely would if it stayed in contact.
Okay.
But they apply a solid lubricant coating, like a microscopic layer of Teflon or molybdenum disulfide, just to handle the friction for the very first few fractions of a second.
Oh, so just for the startup phase.
Exactly. Because as the rotor accelerates, and it accelerates incredibly fast, it drags the surrounding air along its surface.
Because of the boundary layer effect.
Yes. It's pulling ambient air into the microscopic gap between the rotor and the foil.
It's almost like a car tire hydroplaning on a puddle of water on the highway, but with air instead of water.
The physics are highly comparable, actually. It's called hydrodynamic pressure. The rotational motion wedges the air into that confined space, creating a highly pressurized film of air.
And that lifts it.
Yes. Once the rotor reaches a certain threshold speed, that wedge of compressed air becomes incredibly rigid. It literally lifts the rotor completely off the foil.
That is insane.
By the time it hits 35,000 RPM, the rotor is fully suspended. It's riding entirely on a cushion of air. There is zero mechanical contact.
And if there's no mechanical contact, there is no friction.
Exactly.
And with no friction, you don't generate that destructive heat. Plus, you completely eliminate the need for, oil pumps, fluid reservoirs, complex seals, all that stuff that eventually degrades and leaks.
You strip out an enormous amount of ancillary weight and complexity.
So for you, the listener, the practical application of this is massive, particularly if you look at the commercial vehicle sector.
Oh, absolutely. Think about a heavy-duty electric semi-truck. If you can shrink the drive motors by 40% and eliminate all those heavy oil cooling systems,
you significantly reduce the unsprung mass of the vehicle.
right, and unsprung mass is crucial.
Just to define that real quick, unsprung mass is basically everything not supported by the truck's suspension springs. So the wheels, the axles, and in these modern setups, the direct drive motors themselves.
Yeah. Heavy unsprung mass makes a vehicle really difficult to handle. It degrades the ride quality because the suspension just can't react quickly enough to bumps in the road.
Right.
So by drastically lightening that e-beam axle with a high-speed air-bearing motor, commercial fleets get better tire longevity, they get improved handling, and most importantly, they can allocate all that saved weight directly to cargo capacity.
Which fundamentally improves the bottom line, the total cost of ownership.
Exactly. It's a game changer for logistics.
Okay, so we shrink the motor by spinning it faster on a cushion of air. That saves 30% on materials. But that brings us to the second major theme from the Vienna Symposium, and it touches on a vulnerability that goes way beyond just engineering.
The geopolitical elephant in the room.
Right. What if we could build these motors without using rare earth metals at all?
It's a massive push right now.
Yeah.
Supply chain resilience is driving this shift just as much as pure engineering is.
Yeah. Because the standard architecture for high-efficiency EVs over the last decade has been the interior permanent magnet synchronous motor, or IPMSM, right?
Right. And to generate the necessary torque, those motors rely on permanent magnets embedded directly into the spinning rotor itself.
And we are not talking about standard refrigerator magnets here.
No.
To maintain a strong magnetic field at those crazy high operating temperatures without demagnetizing, you have to use specific rare earth elements. We are talking about stuff like neodymium, praseodymium, and often heavy rare earths like dysprosium.
And the massive challenge there is that the mining, refining, and processing of these specific elements are heavily concentrated in very few geographic regions globally.
It's a huge bottleneck.
It is. The extraction process is also notoriously difficult. It's environmentally taxing. Relying on a single, highly centralized global supply chain for the most critical component of your EV transition.
It's a severe strategic risk for automakers.
Massive risk.
Mhm.
Any geopolitical friction, any export restriction, or even sudden price volatility can literally shut down a production line overnight.
Which is exactly why BMW's presentation on their new class platform, specifically their Gen 6 eDrive system, caught so much attention at the symposium.
They made a bold move.
Yeah, they are moving away from the permanent magnet architecture entirely, and they are championing the ESM.
The electrically excited synchronous motor. Or sometimes it's referred to as a wound rotor synchronous motor.
Okay, so let's look at the mechanics of that shift.
Yeah.
If you remove the permanent magnet from the rotor, you basically just have a bare cylinder of metal.
Right.
How do you generate the magnetic field required to interact with the stationary part of the motor and actually create motion?
You have to build an electromagnet. So instead of embedding solid permanent magnets into the rotor, engineers wrap the rotor in tightly wound coils of copper wire. When the motor management system demands torque-like when you press the accelerator, it sends an electrical current through those copper coils, which induces a magnetic field.
And when you cut the power, the magnetic field just vanishes.
Exactly. It's only magnetic when you feed it electricity.
But here's where it gets incredibly complicated from a design standpoint. If I have a rotor spinning at tens of thousands of RPM, and I need to constantly feed electrical current into the copper coils mounted on that spinning object, how do I bridge the physical gap between the stationary battery and the spinning shaft?
That has always been the sticking point. In older industrial motors, they used brushes.
Literal blocks of carbon or graphite, right?
Yeah, these physical brushes would actively press against a slip ring on the spinning rotor to conduct the electricity.
But placing a stationary carbon block against a metal ring spinning at high speeds introduces a host of problems for a modern EV. I mean, the friction alone would wear the carbon brushes down like brake pads.
They would require routine maintenance to replace, which consumers hate.
Right, and as they wear down, they generate fine, conductive carbon dust inside the motor housing.
Which is a nightmare. You absolutely cannot have conductive dust floating around the high-voltage electronics of a sealed EV powertrain. It'll short everything out.
Which is precisely why ESM technology was largely sidelined in favor of permanent magnets for so long, right? The brush mechanism was the weak link.
It was. But at the 2026 symposium, multiple Tier 1 suppliers demonstrated that they have definitively solved this problem through something called contactless inductive excitation.
Contactless, like dropping a smartphone onto a wireless charging pad, just transferring energy without a physical plug?
The underlying principle of magnetic induction is exactly the same as your phone charger.
Yes.
But executed in a highly dynamic rotational environment.
Wow.
ZF presented their I2SM technology, which stands for In-Rotor Inductive Excited Synchronous Motor. And concurrently, Vallejo, working in partnership with MAHLE, introduced their IBE system, utilizing MAHLE's contactless transmitter, or MCT technology.
So how do you efficiently transfer enough power to generate a massive magnetic field across an air gap while the target is spinning that fast?
It's pretty elegant. The system uses two coils. You have a stationary primary coil mounted to the motor housing and a secondary receiver coil mounted to the rotating shaft.
Okay, stationary and spinning.
Right. The vehicle's inverter sends a high-frequency alternating current into the stationary coil. This rapidly changing current generates a fluctuating magnetic field.
Ah, and according to Faraday's law of induction, when you expose a conductor, in this case, that spinning receiver coil, to a fluctuating magnetic field, it induces an electrical current within that conductor.
You nailed it. The current literally jumps the air gap electromagnetically.
That's incredible.
And once the alternating current is induced in the spinning receiver coil, a tiny rectifier integrated directly into the rotor converts it back into direct current. That direct current then flows into the copper windings of the rotor, and boom, you have your electromagnet.
So you have a completely closed wear-free system, no physical contact, no carbon brushes, no maintenance schedule, and no conductive dust. It completely mitigates the historical downsides of the ESM.
And it does so without compromising packaging, which is crucial.
Because transferring energy across an air gap inherently involves some efficiency loss, right? And the induction coils themselves have to take up physical space inside the motor.
They do, but ZF's engineering on their I2SM manages to integrate the exciter so cleanly into the rotor shaft that it actually shortens the overall axial length of the motor by 90 millimeters compared to traditional Brecht designs.
Wait, it's shorter.
It's shorter.
Yeah.
And it reduces energy transmission losses by 15%.
That's brilliant. And Vallejo and MAHLE's IBE system is just as aggressive.
Oh, absolutely. They designed it to seamlessly integrate into modern 800-volt vehicle architectures. And it's capable of pushing 600 newton meters of torque.
That's a lot of power.
It is. We're talking about performance metrics that easily match, and in some driving cycles, actually exceed rare earth permanent magnet motors, specifically at high highway speeds.
Why highway speeds?
Because permanent magnets suffer from what's called back EMF drag.
Right, electromotive force.
Yeah. When a permanent magnet motor spins at very high speeds, the magnets generate a countervoltage that literally resists the motor's own rotation. To overcome this, the system has to use extra energy to artificially weaken the magnetic field, which is highly inefficient.
But with an ESM.
Because the magnetic field is created by software-controlled current, you simply reduce the current to the rotor at high speeds. The magnetic field drops, the drag vanishes, and your highway efficiency spikes.
It's an incredibly elegant solution to a massive geopolitical vulnerability. Just turn off the magnet when you don't need it.
Exactly.
But, and there's always a but, let's look at the secondary consequences of this shift. We've replaced the rare earth magnets with tightly wound copper coils on the rotor.
Right.
But the stationary part of the motor, the stator, is already packed full of copper coils. So we have essentially built a dense box of copper wire. And when you push massive amounts of electricity through copper, you run into the third major hurdle discussed in Vienna.
Extreme thermodynamics.
Yes. Heat. Because as you shrink the physical volume of the motor to save weight and improve packaging, but you demand the same or higher power output, you drastically increase the thermal density.
You are generating way more heat in a much smaller, confined space.
And the physical packaging of that copper is a massive challenge in itself. Like ZF showcased their EVC 800 electric drive system. The specifications are almost hard to believe.
They really are.
The entire drive unit weighs only 74 kilograms, which is a 30% reduction from their previous generation. Yet it delivers 5,200 newton meters of torque to the wheels.
It's an insane ratio.
That works out to a torque density of 70 newton meters per kilogram. How do you physically fit enough copper into a 74-kilogram package to handle that kind of current without it just bursting into flames?
It requires completely abandoning traditional manufacturing methods.
How so?
Well, with the last several years, the gold standard for high-performance EV stators has been something called hairpin winding.
Hairpin, like the hair accessory.
Exactly. Instead of winding thin, flexible round wires, manufacturers use thick, rigid, rectangular copper bars. They physically bend them into the shape of a hairpin, insert them into the slots of the stator's iron core, and then twist and laser weld the ends together.
Oh, because rectangular wire packs together much tighter than round wire, like stacking bricks instead of logs. You get more copper into the exact same slot, which lowers electrical resistance and increases power.
That's the benefit. But the drawback is the geometry of the ends.
What happens at the ends?
When you insert those rigid hairpins into the iron core, the bent ends stick out significantly on both sides of the stator. Engineers refer to this as the end winding overhang.
And I'm guessing that overhang doesn't actually do anything.
It's purely wasted space. It doesn't contribute to the torque-generating magnetic field inside the iron core at all. It just adds dead weight. It increases the total resistance of the circuit because the electricity has to travel further, and it makes the motor physically longer.
Okay, so ZF's solution to this is what they call braided winding technology.
Yes. Rather than using pre-bent rigid hairpins, ZF developed a highly automated manufacturing process that continuously interweaves and braids the copper conductors tightly together as they are being inserted.
Oh, I love the analogy for this. If traditional hairpin winding is like taking thick, rigid wires and awkwardly twisting them together at the end so they bulge outwards in this messy ponytail,
Yeah.
braided winding is like a meticulous, tight French braid. It just pulls all the material completely flush and tight against the structure.
That's a perfect way to visualize it. By braiding the conductors, the end winding overhang is drastically reduced. The copper sits practically flush against the iron core.
And the space savings.
This single packaging innovation allowed ZF to shave 50 millimeters off the total width of the electric motor.
Wow. 2 whole inches.
Yeah. Furthermore, because the physical path the electricity has to travel is now shorter, they reduced the total amount of copper required by 10%.
So less space, lower material cost, lighter weight. But compressing all that copper into an even tighter space definitely exacerbates the heat problem we talked about.
Oh, it makes it much worse.
And this brings us to the absolute bane of electric vehicle performance, thermal derating.
Thermal derating is essentially the vehicle's self-preservation mechanism. The insulation wrapping those copper wires inside the motor can only withstand so much heat before it begins to literally melt.
Which would cause a catastrophic short circuit.
Yes, the car would just die.
So for you listening, if you've ever taken a high-performance EV to a track day, or maybe you've towed a really heavy trailer up a sustained, steep mountain grade, you've likely experienced this firsthand.
Right, the dreaded turtle mode.
Yeah. For the first few minutes, the vehicle delivers massive, effortless power. It feels great. But as you continue to push it, the copper inside the stator rapidly heats up. The vehicle's thermal management software detects this temperature spike, realizes the cooling system can't keep up, and abruptly throttles your power output to prevent a meltdown. Your 500 horsepower car suddenly feels like it has 100 horsepower.
And the limitation there lies in the traditional cooling architecture.
How so?
Well, the standard method for cooling an electric motor right now is a water jacket.
Like a sleeve.
Exactly.
Yeah.
The manufacturer machines a hollow cavity into the outer aluminum housing of the motor, essentially wrapping a sleeve of liquid coolant around the outside of the stator.
Okay, meaning the heat has a really long, difficult path to escape. I mean, the heat is being generated deep inside those tightly packed copper wires. It has to radiate out of the copper, push through the electrical insulation paper, conduct all the way through the thick iron core of the stator, and finally reach the aluminum housing where the liquid coolant can actually carry it away.
Exactly. The iron core acts as a massive thermal bottleneck, has incredibly high thermal resistance.
So if you are generating heat in the copper faster than it can migrate through the iron to the water jacket.
The internal temperature spikes almost instantly, and the software cuts your power.
Right. So ZF solved this in the EVSys 800 by introducing direct liquid cooling technology inside the stator itself.
They completely removed the external water jacket and brought the fluid inside the motor.
Wait. You can't just pump water over high-voltage copper wires. Water conducts electricity. You would instantly short out the entire 800-volt system.
Right. You don't use water. You use a highly engineered synthetic dielectric fluid.
Dielectric meaning non-conductive.
Yes. Dielectric fluids can be in direct physical contact with live electrical components without causing a short circuit. So ZF engineered the braided windings and the stator slots so that this fluid flows directly through the microscopic gaps between the individual copper wires.
Oh, wow. So the cooling medium is physically washing over the exact point where the heat is being generated. There is no thermal bottleneck. You aren't waiting for the heat to slowly bake its way through a solid block of iron. The millisecond the heat is generated by electrical resistance in the copper, the dielectric fluid just absorbs it and flushes it right out of the system.
The impact on performance metrics is profound here. In the industry, we always look at two numbers: peak power and continuous power.
Okay.
Peak power is what the motor can produce for perhaps 10 or 20 seconds before the heat just becomes unmanageable. Continuous power is what the motor can output indefinitely, hour after hour without ever overheating.
Right.
In a traditional water-jacketed motor, the continuous power rating is often only 40 to 50% of the peak power.
Wow, that's a huge drop-off. So a motor rated for 200 kilowatts on a glossy brochure might only be able to sustain 100 kilowatts when you're actually climbing a mountain.
Exactly. It's a bit of a marketing trick. But with direct stator cooling, ZF dramatically closed that gap. The thermal extraction is so incredibly efficient that the continuous power jumps to over 75% of the peak power.
That is a massive leap.
In the EV6 800, a motor with a peak output of 275 kilowatts can sustain a continuous output of 206 kilowatts indefinitely.
Which completely rewrites the real-world capability of the vehicle. I mean, you can run lap after lap on a track or haul a massive payload up a grade in a truck, and the vehicle simply will not heat soak and derate.
It changes everything.
But managing all of this extreme hardware, I mean, spinning air bearings at 35,000 RPM, inducing magnetic fields wirelessly across an air gap, pumping dielectric fluid through braided copper, that requires an incredibly sophisticated level of control.
It really does. Which brings us to the fourth and arguably most critical area of focus from the Vienna Symposium: power semiconductors and X-in-1 integration.
Because none of the mechanical innovations function without the brain of the system, right? The traction inverter. It's feeding them the exact precise amount of electricity thousands of times per second. So let's start with the microchips inside that inverter. As the industry has shifted to 800-volt electrical architectures to enable faster charging and lower current, they've transitioned away from standard silicon chips to silicon carbide, or SiC.
Silicon carbide is what we call a wide bandgap semiconductor material.
Name it.
Compared to standard silicon, it can withstand much higher voltages, it can operate at much higher temperatures, and it can switch on and off significantly faster with much less energy loss.
Okay.
However, as we push system-level optimization, simply using SiC is no longer enough. We are now microengineering the physical three-dimensional architecture of the SoC chips themselves.
And Bosch presented a really cool deep dive into this with their third-generation SiC MOSFET, highlighting something they call a dual-channel trench architecture. But to understand why this matters, we really need to understand what a MOSFET actually does inside the vehicle.
Right. A MOSFET, a metal oxide semiconductor field effect transistor, is fundamentally just a microscopic switch.
Just on or off.
Yeah. The battery provides direct current, or DC, but the motor requires alternating current, or AC, to spin. So the traction inverter acts as the translator. It uses banks of these MOSFET switches, rapidly opening and closing thousands or tens of thousands of times per second, to literally chop the DC voltage into a simulated AC wave.
So you have these microscopic switches opening and closing at unimaginable speeds, handling 800 volts of electricity. What was the flaw in the earlier generations of these switches?
The previous generation of SiC-MOS chips utilized a planar architecture, meaning the functional layers of the transistor were built flat across the horizontal surface of the silicon carbide wafer.
Okay, flat layers.
The vulnerability in this design emerges when the switch is in the off state. Even though current isn't flowing, the 800 volts from the battery creates a massive electrical pressure, an electric field pushing against the closed switch.
Oh, I see. It's totally analogous to a massive concrete dam holding back a reservoir. Even when the floodgates are completely closed and no water's actually flowing, the sheer hydrostatic pressure of millions of gallons of water is constantly pressing against the concrete.
That's a perfect analogy. And in a planar MOSFET, that electrical pressure pushes directly against a highly fragile microscopic layer of the chip called the gate oxide.
That sounds bad.
It is. Over time, under the immense stress of an 800-volt system, this electric field bombards and degrades the gate oxide layer, which can ultimately lead to the chip failing and the vehicle just losing power entirely.
So how does a dual-channel trench architecture solve the pressure problem?
Well, instead of building the switch flat on the surface, Bosch uses advanced plasma etching techniques, which, by the way, is incredibly difficult because silicon carbide is almost as hard as a diamond.
Wow.
They use this plasma to dig deep, microscopic trenches vertically down into the material. And the crucial innovation is what they place at the bottom of these trenches, a heavily doped P-type shield.
Let's define that. What does a P-type shield actually do to the electric field?
By doping the silicon carbide at the bottom of the trench with specific chemical elements, they alter its electrical properties. They create an area with a deficit of electrons, often called holes.
Okay.
When the switch is off and that massive electric field builds up, this P-type shield effectively grabs and reshapes the electric field lines. It pulls the highest concentration of electrical stress away from the fragile gate oxide near the surface and absorbs the brunt of the pressure deep within the trench.
Wow. So going back to the dam analogy, It's like engineering a deep secondary spillway or pressure relief channel at the very base of the concrete wall. It continuously diverts the most intense stress away from the most vulnerable parts of the structure.
Exactly. It dramatically increases the durability and the lifespan of the chip.
That's amazing.
But the trench architecture also provides a massive performance benefit when the switch is on.
Ooh.
Yeah. In a slat planar chip, the electrons have to squeeze through a relatively narrow horizontal channel. But by digging a vertical trench, you physically widen the pathway.
So when you open the floodgates, the trench provides a massive, smooth channel for the water to rush down, meaning there is just less resistance to the flow.
In semiconductor physics, this is measured as RDS, or the on-state resistance. By lowering the resistance, much less energy is wasted as heat during the switching process. Bosch's third-generation trench architecture achieves a 20% overall performance boost in the inverter's efficiency.
20%. And because the trench design makes each individual chip so much more efficient at handling power, you can physically shrink the overall size of the microchip itself.
Which is a critical economic factor here. Silicon carbide wafers are hugely expensive and very difficult to manufacture. If you can make the chip smaller, you can print significantly more chips on a single wafer.
Which increases the yield.
Increases yield, drives down the per-unit cost, and ultimately accelerates the democratization of advanced 800-volt architectures beyond just ultra-luxury supercars.
So we have this brilliant, hyper-efficient brain in the trench, MOSFETs, and we have the raw mechanical capability of the 35,000 RPM air-bearing motors. The final piece of the puzzle from the symposium is how the industry is physically forcing these components together.
Right. This is the move toward X-in-1 integration.
Yeah, because in the first generation of EVs, the architecture was highly distributed. You had the electric motor in one heavy metal housing. You had the reduction gearbox in another. The traction inverter was often a separate box mounted somewhere else in the chassis entirely.
And connecting all these disparate boxes were thick, heavy, highly shielded orange, high-voltage cables.
And those external cables are a massive liability.
Liability.
They add physical weight, they are expensive to manufacture, they introduce electrical resistance, which bleeds off efficiency, and they act like giant antennas that can generate electromagnetic interference, completely disrupting the vehicle's other sensitive electronics.
Right, so the engineering mandate from Vienna is clear. Eliminate the cables, eliminate the external housings, smash everything into a single, unified module.
X-in-1.
Yes. We discussed Garrett's 3-in-1 e-axle earlier, which integrates the motor, the inverter, and the gearbox into one cast aluminum housing. But companies like BorgWarner presented 7-in-1 systems.
Yeah, 7-in-1.
Yeah, integrating the motor, the inverter, the gearbox, the power delivery module, the DC-DC converter, the onboard charger, and even the thermal management plumbing into a single block.
But tightly packing the motor, the high-heat power electronics, and the cooling systems into a single dense box creates a terrifying level of complexity.
Yeah.
I mean, if you have a motor spinning at 35,000 RPM, sitting literally millimeters away from a silicon carbide inverter, a failure in one component instantly cascades into the others.
It absolutely does.
Yeah. If the software driving the dielectric liquid cooling pump miscalculates the thermal load for even half a second, the SISA chips could overheat, which throws off the delicate timing of the wireless induction exciter, which causes the motor to lose synchronization and just tear itself apart.
Which is exactly why this level of extreme physical integration demands an equally extreme level of digital control. This is where the concept of the software-defined vehicle, or SDV, becomes absolutely essential. The mechanical hardware is now fully reliant on the microprocessor orchestrating it.
Which explains the presence of semiconductor companies like STMicroelectronics at a Powertrain symposium. They were highlighting their stellar P3E MCU.
Yes, the microcontroller unit designed specifically to manage these complex X-in-1 systems. The Stellar P3E basically acts as the central nervous system. Because the margins for error in a 35,000 RPM tightly packed system are virtually zero, this MCU is engineered to meet ACLD standards.
ACL being the Automotive Safety Integrity Level D, which is the absolute highest classification for functional safety in the industry.
Right. It dictates that the chip must have extensive built-in redundancies, error-correcting codes, and fail-safes, so that a single random hardware fault cannot cause a catastrophic vehicle-level failure.
Makes sense.
Furthermore, by centralizing the control of the inverter, the thermal management, and the motor into a single, high-powered, software-defined domain controller, automakers can continuously refine the physics of the vehicle long after it leaves the dealership.
Over-the-air, or OTA, Updates. But we're not just talking about updating the navigation map or changing the colors on the infotainment screen here.
No, no. We are talking about deep powertrain level optimization.
Wow.
If an automaker's engineering team analyzes fleet data and discovers a slightly more efficient algorithm for how the dual-channel trench MOSFETs should sequence their switching during extreme cold weather to preserve battery life, they don't have to recall the vehicle.
Or just push an update.
They compile the code, send it via cellular network to the Stellar MCU while the vehicle is parked in your garage overnight, and the next morning, the physical efficiency of that 7-in-1 drive axle has actually improved.
The hardware is locked, but the software defining how that hardware behaves is infinitely malleable.
Exactly. It is the ultimate fusion.
Let's take a victory lap here and summarize the sheer scope of what we've covered today, because the transition from the old paradigm to this 2026 standard is massive. For you, the listener, just think about the blocks we just stacked. We move from heavy, bulky motors to compact units spinning at 35,000 RPM, kept alive not by oil, but by riding on a compressed wedge of aerodynamic pressure.
Incredible engineering.
We watch the industry neutralize a massive geopolitical supply chain risk by replacing rare earth magnets with ruined copper coils, powered wirelessly across an air gap through magnetic induction. We explored how engineers are French braiding copper wire and pumping dielectric fluid directly through the high-voltage stators to just completely shatter the thermal limitations of continuous power. And we zoomed all the way down to the microscopic level to see how plasma-etched trenches and P-type shields in silicon carbide chips are rewriting the rules of electrical efficiency and heat management, all orchestrated by ultra-fast, over-the-air, updatable microcontrollers. So what does this all mean?
When you look at all of these innovations collectively, the primary takeaway from the Vienna Motor Symposium becomes undeniable. The era of single variable optimization is definitively over.
You can't just fix one thing anymore.
No, you cannot build the electric vehicle of the future by simply waiting for a magical battery chemistry to solve the range and weight equation. The 2026 paradigm demands a holistic, tightly coupled, system-level approach.
Right.
The extreme EV is a symphony. It's thermodynamics, material science, fluid dynamics, and software logic, all perfectly synchronized. If you attempt to push the boundaries of one component like spinning a motor to 35,000 RPM without fundamentally redesigning the bearings, the cooling, and the silicon managing it, the system just tears itself apart.
The automotive companies that will dominate the next decade are the ones that actually recognize this reality. It is no longer just about who can source the most lithium. It is about who has the deepest mastery of cross-domain integration, seamlessly blending mechanical engineering, electrical physics, and digital architecture into a single, flawless entity.
The complexity has shifted entirely from the chemistry of the cell to the architecture of the entire powertrain.
I want to leave you with a final, provocative thought to mull over, building on the geopolitics of those rare earth-free motors we discussed. We explored how advanced microengineering like the electrically excited synchronous motor, contactless induction, and hyperfast software control is completely replacing our reliance on physical rare earth metals mined from the earth.
Right, substituting software and design for raw materials.
If that is the trajectory of the industry, if human ingenuity and complex code can effectively replace physical, geographically constrained resources, does the future of global automotive dominance depend more on who owns the cleverest patents rather than who controls the deepest minds? It is a transition from resource-based leverage to knowledge-based leverage, and it has the potential to completely flip the geopolitical script of the last century.
It completely redefines what a strategic resource actually is in the 21st century.
And exploring those deep systemic shifts is exactly why we do these deep dives. To give you the insight behind the headlines, thank you for joining us today and letting us be your shortcut to understanding the absolute frontier of mobility. Remember, no matter how much we think we know, the technology is always evolving, the physics are always being pushed, and there is always more to learn. Keep questioning the world around you. Next time you pull up to a gas station and, fill your car, I really want you to just look at the numbers ticking up on the pump. Let's say you put $100 into the tank.
Right, which is pretty easy to do these days.
Yeah, exactly. Now, prepare to be a little depressed because about 60 of those dollars do absolutely nothing to move you down the road.
Yep, just completely wasted.
I mean, that $60 is entirely wasted as heat, just radiating off your engine block, or noise, and, hot air shooting out of your tailpipe.
It's kind of wild when you actually think about it in dollar amounts.
It really is. And for over a century, mechanical engineers have just sort of accepted that massive waste as an unbreakable law of physics. Like a literal concrete ceiling on how efficient a gasoline engine could ever be.
Right, but that ceiling is exactly what we're talking about today.
Yeah, because what if I told you we have our hands on a stack of confidential symposium notes that prove that concrete ceiling has just been completely smashed?
I mean, it's a fundamental rewriting of the rule book.
Mm.
We're looking at an engineering landscape that has shifted from, predictable, slow iterations to a phase of radical, almost aggressive innovation.
Welcome to the deep dive. Today we are taking you right to the bleeding edge of what is physically possible. We've got highly technical engineering white papers, strategic industry roadmaps, and presentation notes straight from the 47th International Vienna Motor Symposium.
It's some seriously heavy reading, but it is so fascinating.
Oh, absolutely. And the overarching mission for this deep dive, we are unpacking the ultimate thermodynamics and high-performance power technologies that were unveiled at this symposium. We're talking about the actual hardware that is going to be in the cars you drive in the very near future.
And to really understand the gravity of these documents, I mean, you have to look at the broader context of the automotive industry over the last, say, 10 years.
Right, the whole EV push.
Exactly. The prevailing narrative has been incredibly singular. Like, the pure battery electric vehicle, the EV is the only future. Full stop.
That's all anyone talks about.
Right. But the intelligence from the Vienna Motor Symposium makes it very clear that the industry has moved past that singular narrative. They've entered this highly pragmatic era.
Yeah, I saw the term they used in the papers, the era of resilient technology portfolios.
Yes, resilient technology portfolios, meaning the internal combustion engine, the ICE, is not just rolling over and playing dead.
No, it is fighting back with some truly mind-bending physics. So just to give you a tease of what we are getting into today, we're going to look at engines that, historically speaking, physically shouldn't even work.
They really shouldn't. It's crazy.
And we are going to examine high-performance turbochargers that are deliberately missing their most important safety valves.
That part is just wild to me.
I know, right? And we'll break down transmission clutches that act like one-way electrical diodes.
What stands out in these papers is that we aren't just talking about, tweaking a software map to gain a fraction of a mile per gallon.
No, not at all.
We are witnessing the absolute physical limits of thermodynamics being pushed completely past their breaking point. And they're doing it by merging raw, hardcore mechanical engineering with high-voltage electrification.
It is a complete paradigm shift in how we extract kinetic energy from liquid fuel. So let's start with that $60 of wasted gas I mentioned earlier. We really need to talk about the thermal ceiling.
Okay, yeah, let's get into it.
When you put liquid fuel in a car, how much of the chemical energy locked inside that liquid is actually converted into mechanical turning force?
Well, for a very long time, the physical ceiling for a mass-produced spark ignition passenger car engine was considered to be around 41 to 43%.
Okay.
That is a metric called brake thermal efficiency, or BTE. And for context, Toyota held the global crown for BTE for a remarkably long time with their dynamic force engines.
Right. So even in a highly optimized Toyota engine, nearly 60% of the energy is just lost. Where does it actually go? Like physically?
It is lost primarily as exhaust enthalpy.
Exhaust enthalpy. Okay, break that down for us.
Well, it's basically the thermodynamic potential of the heat and pressure that just simply escapes down the exhaust pipe. You're just blowing it out the back of the car.
Wow. Okay.
And then you have cooling losses where the radiator has to pull heat away so the metal doesn't literal melt. And finally, you've got parasitic mechanical friction from all the moving parts just rubbing against each other.
So just pistons and gears fighting themselves?
Exactly.
Yeah.
The laws of thermodynamics, specifically the limits of the Otto cycle that these engines run on, dictated that you simply couldn't extract much more than that 43% without the engine, fundamentally destroying itself under the pressure.
Right. Until the 2026 Vienna Motor Symposium.
Yes. This is where it gets good.
Because we are looking at a joint presentation from the Chinese automaker Chery and the Austrian engineering firm AVL, and they unveiled a dedicated hybrid engine, or DHE, that had an unbelievable 48% brake thermal efficiency.
It is a monumental leap. I mean, to put that in perspective, gaining just 0.1% in BTE usually takes an automaker millions of dollars in R&D.
Just for 0.1%.
Yes. So to jump from 43 to 48 is astronomical. It's unheard of. And to truly appreciate how they pulled this off, we have to look at the combustion chemistry they chose. They achieved this at what automotive engineers call lambda equals 1.
Yeah, I see that term all over these papers. Lambda equals 1. What does that actually mean for the person behind the wheel?
Okay, so lambda is the Greek letter used to represent the ratio of air to fuel inside the cylinder.
Got it.
So lambda equals 1 means you have the exact mathematically perfect stoichiometric mixture.
Stoichiometric, meaning balanced.
Exactly balanced.
Yeah.
Every single molecule of hydrocarbon fuel has exactly enough oxygen molecules to bond with and burn completely. There is no excess oxygen, and there's no unburned fuel left over.
But wait, haven't experimental lab engines hit high efficiencies before? I thought I read about prototypes hitting like 45% years ago. Yeah.
They have, yeah. But almost always by using something called ultra-lean burn.
Lean burn. Okay, meaning what?
That means pumping in way more air than fuel. So your lambda number is much higher than 1, maybe 1.5 or 2.
Okay, so a lot of extra air.
Right. And lean burn is fantastic for extracting efficiency, but it creates a massive, almost insurmountable real-world problem. It produces a huge amount of nitrogen oxides, or NOx.
Because when you have all that extra oxygen and the intense heat of the engine, the nitrogen in the air just starts burning too.
Precisely. It literally burns the air itself. And NOx is a heavily regulated, super toxic pollutant. So to clean up NOx from an ultra-lean burn engine, you have to install incredibly expensive, heavy, and complex exhaust after-treatment systems. You might be familiar with selective catalytic reduction, or SCR.
Oh, is that the system where you have to constantly buy those jugs of blue diesel exhaust fluid and pour it into a separate tank?
That's the one, yeah.
I hate dealing with that stuff.
Everyone does. It injects urea into the exhaust to neutralize the NOx. But that adds weight, complexity, and high maintenance costs.
So it ruins the point of an efficient, cheap passenger car.
Exactly. But by achieving 48% BTE at lambda equals 1, Sherry and AVL completely bypass that necessity. A lambda equals 1 exhaust profile works perfectly with a standard, relatively cheap, conventional 3-way catalytic converter.
Oh, wow.
Yeah. So they achieved world-beating, hyper-lean-like efficiency while completely avoiding the expensive aftertreatment. And they easily met the ultra-strict Euro 7 emissions regulations.
Okay, I understand the chemistry side. But you can't just pour standard gasoline into a standard engine, declare it lambda equals 1, and magically get a 48% efficiency rating.
I wish you could, but no.
Right, so how do you physically force the metal to do that?
Well, you have to completely reinvent the fundamental kinematics of the engine. I mean, they literally had to abandon the traditional slider crank mechanism. And that's been the basis of the internal combustion engine since Nicholas Otto invented it back in the 19th century.
This slider crank, okay, just so we are all visualizing the same thing, that is the standard setup where the piston goes up and down in a straight line, right?
Yep, straight up and down.
And it's connected to a rod, which turns a crankshaft at the bottom, like your legs pedaling a bicycle.
That's a perfect analogy, yes.
Yeah.
And the inherent limitation of a standard slider crank is its symmetry.
Symmetry, okay.
The distance the piston travels upward to compress the fuel and air mixture is exactly the same physical distance it travels downward when the spark plug fires and the mixture explodes.
Symmetrical strokes. What goes up 4 inches must come down 4 inches.
Right. And thermodynamicists have known for decades that this symmetry is a trap.
A trap? How so?
Well, to get more efficiency, you want a massive expansion stroke. You want that exploding gas to push the piston down as far as physically possible to extract every last joule of kinetic energy before you open the exhaust valve.
Okay, that makes sense. Just ride the explosion as long as possible.
Exactly. But in a symmetrical slider crank engine, if you design it to have a massive expansion stroke, you're forced to have a massive compression stroke.
Ooh. And if you compress a gasoline mixture too much, it gets too hot and explodes on its own before the spark plug even fires.
Exactly. That is called engine knock, or pre-ignition.
And that's bad.
It's catastrophic. It creates a shock wave that collides with the piston while it's still moving upward. It will shatter piston rings and literally destroy an engine in a matter of seconds.
Yikes. So, historically, how did car companies try to fake a longer expansion stroke without blowing up the engine?
They used valve timing tricks, specifically the Miller or Atkinson cycles.
I've heard of the Atkinson cycle in hybrids before.
Yeah, Toyota uses a lot. Basically, they use the camshaft to hold the intake valve open a little too long as the piston starts coming up.
So it spits a little bit of the air back out into the intake manifold.
Yep. It effectively lowers the actual compression ratio, avoiding the knock, while keeping the physical expansion ratio the same. But doing that starves the engine of air at low speeds, which absolutely ruins your low-end torque.
So the engine feels completely gutless when you step on the gas from a stoplight.
Exactly. It's efficient, but terrible to drive without an electric motor helping out.
So looking at the AVL and Sherry white papers, they looked at this symmetrical trap and decided to just, break the symmetry entirely?
Yes, they threw it out the window.
They created what they call a double crank three-link mechanism. And I've been studying the diagrams in the papers, and it looks incredibly strange. There's an offset crankcase, extra pivot points, additional linkages.
It physically decouples the strokes. The mechanical path the piston takes is no longer a simple circle.
Neat. Really?
Yeah. The piston literally travels a shorter distance on the way up than it does on the way down.
Okay, let's use an analogy here. Think of a slingshot.
Okay, I like that.
Imagine you pull the slingshot band back just a few inches. That is your short compression stroke. You aren't squeezing the fuel air mixture too hard so it doesn't overheat and cause that engine knock you talked about.
Right, nice and safe.
But when you let go of the pouch, because of this complex three-link mechanism, the band doesn't just return to its starting position, it somehow snaps forward 3 entire feet.
Wow.
And that is your massive expansion stroke.
That visual works perfectly.
Yeah.
And the mathematical numbers they achieved with this are staggering. Because they decoupled the strokes, they achieved a geometric expansion ratio of 26-1.
26-1. Wait, most normal cars sitting in our listeners' driveways are maybe 10-1?
Usually between 10-1 and 12-1. Yeah.
So this is more than double.
Way more. At 26-1, the expanding gas pushes the piston so incredibly far down the cylinder wall that by the time the exhaust valve finally opens, almost all of the heat and pressure, the exhaust enthalpy has been absorbed.
Converted into physical mechanical turning force?
Exactly. The gas exiting the cylinder is relatively cool and at a much lower pressure. You have literally squeezed every usable drop of energy out of the explosion.
Okay, hold on. I need to push back on this a little bit.
Sure, go for it.
If you have an expansion ratio of 26-1, even if you decouple the compression stroke to avoid the knock, the raw mechanical forces, the pressures and temperatures inside that cylinder when the spark plug fires, shouldn't the engine block just melt?
It's an intense environment for sure.
I mean, you are essentially detonating a bomb that wants to keep expanding forever inside an aluminum tube.
You've identified the exact engineering hurdle that makes this so difficult to pull off in the real world. To prevent the engine from melting, and to strictly control the violence of that combustion, they pump an unheard of amount of exhaust gas back into the cylinder.
Exhaust gas, like from a tailpipe?
Yes, we are talking about a 35% exhaust gas recirculation, or EGR rate.
Wait, 35% of the fresh air the engine breathes in is actually its own dead exhaust?
Yes. And there's a very specific thermodynamic reason for that.
Okay, explain that because it sounds crazy.
Exhaust gases, particularly carbon dioxide and water vapor, are polyatomic molecules. Because of their specific molecular structure, they have incredibly high specific heat capacities.
Meaning they can absorb a massive amount of thermal energy without their own temperature rising very much.
Right, they act like thermal sponges.
Sponges, that's a great way to put it.
When the spark plug fires and the fuel begins to burn, these exhaust gases instantly absorb the latent heat of the combustion. This drops the peak temperature inside the cylinder drastically.
So it's basically a chemical fire extinguisher running inside the engine.
Pretty much. And by keeping the core temperature down, it completely suppresses auto-ignition and knock, even under the extreme pressures required to push a piston down a 26-1 expansion stroke.
But wait, if you stuff the cylinder with 35% dead, unreactive exhaust gas, how do you even get the fresh fuel to catch fire?
That's the million-dollar question.
Because it sounds like trying to light a wet match in the middle of a hurricane.
It is an incredibly hostile environment. It actively resists combustion. So to solve this, they implemented a 600-bar direct fuel injection system.
600 bar, okay. That is roughly 8,700 pounds per square inch of fuel pressure.
It's massive.
To put that in perspective for you listening, the pressure at the very bottom of the Mariana Trench in the ocean is around 1,000 bar. They are injecting gasoline at over half the pressure of the deepest point on Earth.
It is violent pressure.
Yeah.
And when fuel is blasted through the tiny holes of the injector tip at 600 bar, it shatters into microscopic droplets. The engineering notes state they reduced the solder mean diameter of the droplets to near nanoscale.
Wait, solder mean diameter, let's keep it in English for a second. Are we basically just talking about how fat the fuel droplets are?
Basically, yes. It's a mathematical way of measuring the average size of a droplet based on its volume and surface area. By making the droplets microscopically tiny, their surface area to volume ratio skyrockets. And because so much surface area is exposed to the hot air in the cylinder, the liquid fuel vaporizes instantly.
And when a liquid turns into a gas, it absorbs heat, like sweat evaporating off your skin on a hot day to cool you down.
Exactly. That vaporization pulls even more heat out of the cylinder charge, again, fighting the engine knock. But more importantly, blasting fuel in at that extreme pressure creates intense physical turbulence.
Right, because of the sheer force of the spray.
Yes. Engineers call it turbulent kinetic energy, or TKE. It whips the inside of the cylinder into a literal vortex. So when the spark finally does fire, the flame isn't just slowly spreading.
It gets caught in the hurricane.
Exactly. It's caught in this hurricane and carried through the highly diluted mixture incredibly fast, ensuring a complete burn before knock can even begin to form.
The sources also note they had to use APS plasma spray and DLC coatings on the cylinder walls just to keep the friction down. What exactly is a plasma spray?
So APS stands for atmospheric plasma spray. They basically take a metal wire, melt it using an incredibly hot plasma torch, and spray the molten particles directly under the inside of the aluminum cylinder walls.
That sounds like science fiction.
It's pretty close. It creates an ultra-thin, hyper-durable iron lining. And then they apply DLC, or diamond-like carbon, to the piston rings.
Diamond-like, like actual diamonds.
At an atomic level, yeah, DLC shares some of the lattice structure of a diamond, which makes it incredibly hard and incredibly slick. It allows the piston to survive the violent forces of that 26-to-1 stroke without tearing the cylinder walls apart.
Okay, so we have this absolute masterpiece of thermodynamics, asymmetric linkages, 600-bar injectors, and plasma-sprayed walls. But the Sherry white paper claims this engine actually costs 8% less to manufacture than their previous generation engine.
I know, it sounds impossible.
How on earth are they justifying that number? There is zero mathematical way. A double-crank, 3-link, plasma-coated engine is cheaper to build than a standard 4-cylinder.
It does sound contradictory, but the cost reduction comes from a combination of supply chain scale and the elimination of auxiliary systems.
Okay, explain it.
Well, because this is a dedicated hybrid engine, it doesn't need a traditional starter motor, an alternator, or even a complex multi-speed gearbox. The electric motors in the hybrid system handle all of that.
Oh, so they just delete all those parts from the bill of materials.
Precisely. Furthermore, the Chinese automotive supply chain has matured to the point where technologies like 600-bar injectors and APS coating, which were, aerospace grade a decade ago, are now commoditized and mass-produced.
So they offset the cost of the complex crank mechanism by stripping away everything else the engine no longer needs to do.
Exactly.
That is fascinating. So you have a hurricane of 35% dead exhaust gas, keeping the engine from melting, and you're using ocean trench pressure to whip it into a frenzy. That solves the temperature problem, but doesn't it create a massive new one?
It does.
Because how do you reliably spark a fire inside a hurricane? Which, perfectly bridges us to the next massive innovation from the symposium.
Yes, ignition in high EGR environments is a critical failure point for modern engines. Traditional spark plugs have been the standard for over a century.
Right.
They operate by sending high voltage down a ceramic insulator, creating a tiny electrical arc between two small metal points.
And that tiny little arc is supposed to ignite the fuel.
Right. And under normal conditions, it works fine. But in a heavily diluted cylinder, like we just talked about, the tiny arc just doesn't have the thermal energy to reliably ignite the mixture.
The spark is just too weak.
Yeah, the flame propagation, the speed at which the microscopic fireball spreads out from the spark plug across the top of the piston is simply too slow.
Let's visualize that for a second. It's like dropping a single match into a damp forest. The fire might catch, but it's going to spread very, very slowly.
And in an engine, if the flame spreads too slowly, the unburned fuel and air at the far edges of the cylinder get compressed and heated by the advancing flame front for too long. Eventually, the heat and pressure become too great, and those far edges auto-ignite. You get engine knock.
Or worse, the tiny spark just blows out in the 600-bar turbulence and you get a total misfire.
Exactly. And a misfire means unburned fuel gets dumped into the exhaust, ruining your efficiency and eventually destroying the catalytic converter.
So how do we fix the spark plug? because we are looking at a hardware solution presented by Bosch called passive pre-chamber ignition.
This is a really cool piece of tech.
Looking at the diagrams provided in the symposium notes, it looks radically different. Imagine your standard spark plug, but instead of the exposed little metal hook at the bottom, it looks like someone welded a tiny metal dome or like a little cage with microscopic holes in it completely covering the tip.
Yeah, that tiny dome is the pre-chamber. It is a highly engineered microenvironment. And to understand the physics, you have to know that the volume inside that tiny cage makes up only 2 to 5% of the total volume of the combustion chamber.
Okay, so walk us through the sequence of events. The piston is coming up, compressing that highly diluted 35% EGR mixture.
Right. And as the piston rises on the compression stroke, the immense pressure physically forces a small amount of that air, fuel, and exhaust mixture through the tiny nozzles and into the pre-chamber.
So it's squeezing the gas inside the cage.
Exactly. So now you have this tiny restricted cage filled with the mixture, and your spark plug electrode is sitting directly in the center of it.
And then the spark plug fires.
Yes. When it fires inside this tiny enclosed cage, the pressure inside the pre-chamber spikes violently and almost instantly. It creates a highly contained, localized explosion.
And that explosion has nowhere to go but out those tiny holes in the cage.
Exactly. And this is where the magic happens. The phenomenon that results is called volumetric ignition.
Volumetric ignition.
The explosion inside the pre-chamber forces the burning mixture out through the tiny nozzles at supersonic speeds. These become high-temperature, highly reactive plasma jets shooting deep into the main cylinder.
Whoa. So instead of a slow flame spreading out from one tiny point at the top of the cylinder, our match in the forest, you're shooting 6 or 7 supersonic flamethrowers into every corner of the cylinder at the exact same millisecond.
That is precisely what it looks like on high-speed thermal cameras.
Yeah.
You get multiple points of the cylinder catching fire simultaneously.
That's incredible.
And the sheer kinetic energy of those plasma jets creates massive turbulence of its own. It results in an incredibly fast, highly stable burn ripping through the mixture before knock and form, even if the fuel is heavily diluted with dead exhaust gas.
Bosch noted in their presentation that this passive pre-chamber technology is so effective that it allows standard D-segment passenger cars like, think of your average midsize family sedan, to reach 41% BTE without needing the crazy asymmetric linkages we talked about with Chery.
Right, it's a massive upgrade just from changing the spark plugs.
But that sounds like an absolute cheat code for internal combustion. You just unscrew the old spark plug, screw in these new pre-chamber plugs, shoot plasma jets, and immediately gain massive efficiency.
I know, it sounds too good to be true.
So I have to ask, if this is so revolutionary, why aren't we seeing these pre-chamber spark plugs on every single car rolling off the assembly line right now? Where is the catch?
Well, the catch is the reality of human driving behavior, specifically low engine loads and cold starts.
Okay, why is that a problem?
This entire system relies on the rising piston to physically force fresh mixture into the cage, and in doing so, push the old burned exhaust gas from the previous combustion cycle out. That flushing process is called scavenging.
So you need enough pressure to flush the toilet, basically.
That's a crude but very accurate way to put it. When you are accelerating onto a highway, cylinder pressures are high and scavenging is perfect. The cage gets flushed clean.
Right.
But think about when you are idling at a stoplight or just gently cruising at 20 miles an hour through a school zone. Those are low engine loads.
The engine is barely working.
Right. The throttle is barely open, and there isn't a lot of pressure inside the cylinder. There isn't enough physical force to properly scavenge that tiny pre-chamber. So it gets choked with residual dead exhaust gas from the last cycle.
Oh, and if the cage is full of dead exhaust gas, the next time the spark plug fires, it won't ignite anything.
Precisely. You get random, unpredictable misfires at low speeds, which makes the car feel jerky and throws check engine lights.
Nobody wants a brand new car that stutters at stoplights.
Exactly. So automotive software engineers are currently performing a brutal, delicate balancing act. To keep the catalytic converters hot enough to meet emissions during a cold start, and to prevent these low-load misfires, they have to run extreme ignition timing compromises.
So it's all managed by code.
It is a constant software battle between keeping the pre-chamber clean, keeping the emissions legal, and maintaining that high fuel efficiency. It is definitely not a simple plug-and-play solution.
So far, we've been looking at extreme thermodynamics designed to squeeze every last drop of efficiency out of commuter hybrids, trying to make the daily drive to the grocery store as mathematically perfect as possible.
Right, the practical stuff.
But what happens when you take these exact same physical principles, extracting every single joule of exhaust enthalpy, and you apply them purely to go violently fast. Let's talk about Porsche.
Oh, it's fascinating. Because it represents a completely different philosophy, yet it uses the exact same underlying physics.
We are looking at the specifications for the 2026 Porsche 911 Turbo S, the 992.2 generation. It features a brand new 3.6-liter flat-six engine.
A beautiful engine.
The power numbers are staggering, 701 horsepower and 590 pound-feet of torque. But what makes this car historically significant isn't just that it's a bigger engine. It is designated as a T-hybrid, a performance hybrid.
And the way Porsche achieved that performance is by completely rethinking how a turbocharger functions in a high-stress application.
I was looking through the schematics for this new engine, and Porsche did something that seems, frankly, insane. They completely removed the wastegate from the turbocharger.
Yeah, for anyone familiar with how turbocharged engines have been built for the last 40 years, removing the wastegate sounds like a recipe for catastrophic engine failure.
Let's break down why that is for a second. Think of a turbocharger's wastegate, like the safety spillway, on a massive hydroelectric dam.
Okay, good analogy.
As an engine revs higher, it produces more hot exhaust gas. That exhaust gas spins a turbine wheel, which spins a compressor wheel, which forces more air into the engine. More air means a bigger explosion, which makes even more exhaust gas, which spins the turbo even faster.
It's a positive feedback loop.
Exactly. If the pressure gets too high, the engine will blow its cylinder head clean off. So engineers invented the wastegate. It is the safety spillway. When the pressure hits a designated red line, a valve opens, venting the excess exhaust gas around the turbo, slowing it down and keeping the dam from bursting.
Makes sense.
But Porsche just took wet cement and filled in the spillway. There is no wastegate. Every single drop of 1,000 degrees Celsius exhaust gas must go through the turbine blades, no matter how fast the engine is spinning.
Right. And under normal circumstances, that means the turbo shaft would overspin, the bearings would melt, and the turbine wheel would disintegrate into
It
shrapnel.
would just explode.
Basically, yeah.
Yeah.
But Porsche solved this with what they called the e-turbo, a bypass valve-free electric turbocharger.
Okay, so how does it work?
What they did was integrate a high-speed brushless electric motor directly onto the central shaft that connects the exhaust turbine to the intake compressor.
Wait, so you have the hot exhaust wheel on one side, the cold intake air wheel on the other side, and an electric motor sandwiched right in the middle, all on the exact same spinning stick.
Yes, and this single electric motor solves two massive historical problems with turbochargers. The first is turbo lag.
Turbo lag is the worst.
It really is. At low RPMs, when you stomp your foot on the gas pedal, there isn't enough exhaust gas flowing yet to spin the turbo. You usually have to wait a second or two for power to build up.
You press the gas, count to 2, and then you get thrown into the seat.
Right. But in the T-hybrid, the moment your foot touches the pedal, the hybrid battery dumps electrical current into that center motor. It spins the compressor up to 100,000 RPM instantly. Zero turbo lag.
You get the instant shove into your seat like an EV, but with the mechanical scream of a flat-six engine behind you. That's amazing.
Yeah.
But what about the high RPM problem? How does the electric motor stop the turbo from exploding now that the wastegate is gone?
This is the absolute genius of the system. At high RPMs, when the engine is screaming at 7,000 RPM and all that exhaust gas is threatening to overspin the turbo, the electric motor completely switches its function in a millisecond.
What does it do?
It stops acting as a motor and becomes a generator. It applies massive electromagnetic resistance to the shaft.
Wait, it acts like a regenerative brake?
Exactly. It uses electromagnetic force to physically drag the turbine shaft down to a safe speed, preventing it from exploding. And in the process of applying that braking force, it harvests all of that excess exhaust enthalpy, that massive kinetic and thermal energy, and converts it into high-voltage electricity, sending it right back to the battery pack.
It is literally eating the fire and turning it into voltage. That is brilliant.
It's elegant, right?
But it has to be an absolute nightmare for the metallurgists building the physical parts.
Oh, it is an extreme engineering risk. Think about the thermal stress involved here. Because there is no wastegate allowing the hottest gases to bypass the housing, the turbine wheel and the central bearings take the full, unrelenting brunt of 1,000 degrees Celsius exhaust heat constantly.
You cannot use standard steel or aluminum for that. It would liquefy.
Not a chance. The symposium sources mentioned they had to turn to next-generation materials, specifically a superalloy called VDM alloy C264.
What makes this metal so special?
Well, VDM alloy C264 is a nickel-chromium-cobalt superalloy. The reason you use nickel and cobalt is because of their atomic lattice structure.
Okay, getting into the chemistry again.
Just a little. At temperatures where traditional steel begins to experience creep, which is the metallurgical term for metal slowly stretching and deforming under heat and centrifugal force, the atomic bonds in a nickel-cobalt alloy remain completely rigid.
And so it won't warp.
Right. These materials are pushed to the absolute limits of material science. I mean, they're operating in environments closer to the inside of a jet engine than a traditional car.
And it's not just the heat from the exhaust, right?
Yeah.
I imagine putting an electric motor in the middle of a 100,000 RPM shaft creates its own thermal problems.
Absolutely. The system has to battle what is known as brushless drag and back EMF.
Let me stop you there. What is back EMF?
It's in for back electromotive force. When you spin the magnets of an electric motor at over 100,000 RPMs, the magnetic fields heavily resist spinning that fast. They push back against the rotation. That immense magnetic resistance generates severe electrical heat right in the center of the turboshaft, compounding the heat coming from the exhaust. The liquid cooling channels required to keep this e-turbo from melting are incredibly intricate.
I want to pivot slightly because there is a really interesting debate hiding in these Porsche specifications. Everyone in the EV world right now says 800-volt electrical architectures are the gold standard.
Yeah, that's the current industry buzzword.
They allow for faster charging, thinner wiring harnesses, and better thermal management. And Porsche practically pioneered 800-volt systems years ago with the Taycan electric car.
They did.
But for their flagship, the absolute pinnacle of their engineering, the 911T hybrid, they chose to put a 400-volt system in it. Why would a company obsessed with the cutting edge use an ostensibly lesser electrical architecture?
That is a fantastic question, and it really highlights the principle of system-level optimization rather than just chasing big numbers on a spec sheet.
Okay, unpack that.
It all comes down to the size, weight, and internal chemistry of the battery pack. The 911T hybrid isn't a plug-in hybrid with a massive battery. It has a tiny, ultra-compact 1.9 kilowatt-hour liquid-cooled battery.
To put that in perspective for you listening, a typical fully electric vehicle has a battery pack around 80 or 100 kilowatt hours. 1.9 is practically a lawnmower battery in comparison.
It is very small.
Yeah.
Now let's look at the electrical engineering. To generate 800 volts, you need to wire a specific large number of individual battery cells together in a series circuit.
Think of stacking AA batteries end-to-end in a flashlight.
Exactly. Because the 911's total battery capacity is so small, if you tried to slice it up into enough tiny cells to reach 800 volts in series, the internal resistance to the battery pack would absolutely skyrocket.
Because you have too many physical connections pushing current between tiny cells.
Exactly. And high internal resistance generates heat, which means you lose power. Furthermore, an 800-volt system requires significantly thicker, heavier electrical insulation around all the cables to prevent arcing.
Oh, and adding weight to a 911 is a cardinal sin.
It would add pointless weight to a sports car where every single ounce is heavily scrutinized. Porsche's engineers ran the math and realized a 400-volt system perfectly matches the maximum discharge and charge capability of a 1.9 kilowatt-hour pack.
Ah, so it's perfectly balanced.
Right. It gives them the exact electrical flow they need to instantly spool the turbo and power the transmission motor while keeping the physical weight of the car as incredibly low as possible. It is a masterclass in using the right tool for the job rather than just the biggest tool available.
That makes total sense. You don't use a fire hose to fill a teacup.
Yeah.
Okay, so we've covered a massive amount of ground so far. We've looked at engines that manipulate geometry to achieve 48% efficiency. We've got pre-chamber spark plugs shooting supersonic plasma jets. We've got wastegate-free turbos using magnetic resistance to harvest exhaust fire into electricity.
It's a lot of tech.
It is. But if you connect this to the bigger picture, none of that matters if that hard-earned, highly engineered power is lost before it ever touches the asphalt.
Oh, absolutely. The drivetrain is the unsung hero of efficiency. You can generate all the thermodynamic perfection in the world at the engine block. But if the transmission wastes it through friction, your efficiency just plummets.
Let's talk about cutting the dead weight. The final section of these symposium notes focuses heavily on the elimination of parasitic losses in hybrid drivetrains.
In complex hybrid systems, especially ones like we've been discussing, which might have a combustion engine, an e-turbo motor, a transmission motor, and maybe an axle motor power is constantly being handed off.
It's a juggling act.
Very much so. The vehicle's computers are deciding, millisecond by millisecond, whether to use the battery, the gas engine, or a combination of both. To physically connect and disconnect these different power sources to the wheels, traditional transmissions use wet multi-plate clutches.
And these clutches are the hidden enemy. Let's try another analogy. Think about the car sitting in your driveway right now. Or better yet, imagine you are riding a bicycle downhill.
Coasting downhill is the best part of biking.
Exactly. You're picking up speed, gravity is doing the work, and you just want to coast and catch your breath. But imagine your pedals are rigidly attached to the wheels like on a child's tricycle.
Oh, that sounds awful.
You can't coast. Your legs are forced to spin wildly, just trying to keep up with the speed of the wheel. That is parasitic drag. You are burning energy, moving your legs for absolutely no reason.
It's a great way to visualize mechanical drag.
Traditional wet clutches inside transmissions try to fix this by separating the engine from the wheels when you want to coast or drive in pure electric mode, but they aren't perfect. A wet clutch is a stack of alternating metal friction plates.
Right.
When they disengage, they pull apart slightly, but they are still submerged in a bath of heavy transmission oil. It is like a brake pad hovering a millimeter over a spinning rotor. The thick fluid between the plates still catches and drags. It is constantly sapping a little bit of kinetic energy.
Automotive engineers call this viscous drag, or gear churning loss. In a normal gas car, you might not really notice it. But in a highly optimized hybrid, those small viscous losses compound into a massive hit to fuel economy and pure electric range.
So how do we fix it?
Well, to combat this, the symposium highlighted critical innovations from an engineering firm called Automotive, specifically their torque management solutions. They introduced hardware called the mechanical diode, or MD, and its active evolution, the controllable mechanical diode, the CMD.
A mechanical diode. In electronics, a diode is a one-way valve for electricity. It lets current flow forward, but blocks it from going backward. How does that translate into a physical mechanical transmission part?
They use something called planar ratchet geometry.
Planar ratchet, okay.
Think of it like a highly sophisticated, incredibly strong gear with struts or teeth that only catch in one specific direction. When the vehicle system needs to transfer massive torque from the gas engine to the wheels, the struts in the planar ratchet pop up and lock into place solidly.
So it grabs on.
Yeah. It creates a direct, mechanical, hard connection. There is zero slip, and zero power is lost to fluid dynamics.
But what happens when you let off the gas pedal or when the electric motor takes over?
When the wheel starts spinning faster than the engine, the overrunning condition, like our bicycle going downhill, the struts instantly lay flat and retract.
Oh, they just fold away.
Exactly. The two sides of the clutch, completely and physically separate. Because there are no fluid-coupled friction plates rubbing together, the dragging friction drops to virtually zero.
And Amstead took this concept even further with the ultimate evolution, the DCC, or dynamic controllable clutch. What makes the DCC different from the standard mechanical diode?
The standard mechanical diode is passive. It reacts purely to the rotational speed. The DCC is an active, electronically commanded system.
Okay, meaning the computer controls it.
Right. When a hybrid car's computer decides to switch into pure EV mode, or when you step on the brakes and the car starts using regenerative braking to charge the battery, the DCC fires an actuator. It physically, completely severs the mechanical connection to the internal combustion engine and the heavy transmission components.
And it does this fast.
It happens in a fraction of a millisecond.
So it's not just disengaging a fluid clutch. It is physically dropping the mechanical link so the electric motor is spinning freely, completely unburdened by the dead weight of the gas engine or the drag of gears whipping through heavy oil.
Exactly. It completely zeroes out parasitic drag. This is absolutely crucial for regenerative braking.
Why specifically for regen?
When you hit the brake pedals in a hybrid, you want every single ounce of the car's forward kinetic energy to travel backward through the drivetrain, spin the electric motor, turn it into electricity, and go straight into the battery.
Right, you don't want to waste any of that momentum.
But if your wheels are also being forced to spin the dead weight of an engine block through a dragging clutch, you are throwing away energy as heat. The DCC ensures that the path from the wheel to the battery is entirely frictionless.
So if I'm playing devil's advocate here, what does this all mean for the consumer? Why should you, the person listening to this deep dive, care about planar ratchets and mechanical diodes inside a transmission housing?
Because this is the definition of system-level optimization. In a highly electrified vehicle, removing mechanical friction isn't just about saving a fraction of a mile per gallon. It creates a massive cascade effect.
A cascade effect. Tell me more.
If your drivetrain has zero parasitic drag, Your electric motors don't have to work as hard to move the physical mass of the car.
Makes sense.
If the motors don't work as hard, they draw less electrical current. If they draw less current, you can use a smaller, lighter battery pack to achieve the exact same driving range.
And a smaller battery means less overall vehicle weight, which means better handling, better braking distances, and a smaller, cheaper liquid cooling system.
Exactly. Squeezing parasitic drag out of the transmission literally cascades through the entire architecture of the vehicle. It makes the car lighter, faster, significantly cheaper to manufacture, and vastly more efficient.
It's the butterfly effect of engineering. You fix a tiny drag in the clutch, and suddenly you can shrink the battery pack by 10%. That is incredible.
It beautifully showcases how interdependent every single component is in these 2026 vehicle architectures. You cannot just slap a battery into an old gas car chassis anymore. The engine, the turbocharger, the spark plugs, the transmission clutches, they all have to be designed simultaneously as a single, breathing, hyper-optimized organism.
Let's pull all of this together. We started this deep dive looking for the ultimate physical limits of thermodynamics. We saw Sherry and AVL completely break the symmetry of the internal combustion engine using that crazy slingshot 3-link mechanism to absorb massive expansion and hitting an impossible 48% efficiency.
A true engineering marvel.
We looked at Bosch shooting supersonic plasma jets out of tiny metal cages just to light fires inside literal hurricanes of exhaust gas. We watched Porsche cement their wastegates shut, forcing electric motors to use magnetic resistance to harvest the fire of a screaming flat-six engine.
Harvesting fire. I love that phrasing.
And finally, we saw Amstead Automotive using planar mechanical diodes to physically sever the parasitic drag that has been haunting transmissions for over a century.
The overarching takeaway from reading through the hundreds of pages of the Vienna Motor Symposium notes is undeniable.
Yeah.
The internal combustion engine is not fading away quietly into the night. It has been fundamentally re-engineered from the atomic level up. It has become a highly sophisticated, hyper-efficient node in a much larger, highly intelligent, electrified network.
Which leaves us with a pretty massive industry-defining question.
It does.
If we connect everything we've unpacked today to the macro-level industry trends.
Right, the EV push versus these resilient ICE portfolios.
Exactly. We are seeing mechanical engineering and thermodynamics pushed to absolute record-breaking limits, aided by the surgical application of high-voltage electrification. If legacy automakers can make liquid fuel architectures this brutally efficient, this powerful, and this clean, we have to ask ourselves a very provocative question.
It's the question every automaker is quietly asking right now.
Is the global transition to pure 100% battery electric vehicles truly a scientific and economic inevitability? Or will these extreme thermodynamic hybrids, these masterpieces of mechanical engineering, carve out a permanent, highly resilient existence alongside EVs for decades to come?
It's a great question. Are we looking at a temporary bridge technology, or have we just witnessed the birth of a permanent, dominant alternative?
That is a thought to chew on, because right now, the diagnostic landscape of automotive tech is murky, and the ceiling we thought was concrete just got blown wide open. It turns out that ceiling wasn't the roof, it was just the floor for the next level of engineering. Thank you for joining us on this deep dive. Keep asking questions, keep looking beneath the surface, and remember that the physical limits of our world are often just waiting for the right engineer to come along and break them. We'll catch you on the next one. Imagine you're running the engineering division of a massive global logistics giant.
Right.
And the year is 2026. For the better part of the last, 10 years, the prevailing narrative from basically every consulting firm and policymaker was that the future of heavy-duty transport was unequivocally entirely battery electric.
Yeah, that was the only acceptable answer for a long time.
Exactly. You were told to prepare for these megawatt charging depots and fleets of pure electric Class 8 trucks. But as you stare at the operational spreadsheets and the route maps for moving, say, 80,000 pounds of freight across the Australian outback or the American Midwest,
The math just falls apart.
it really does.
Yeah.
The sheer unforgiving physics of battery density are just staring right back at you.
Because when you try to replace a diesel tank with a lithium-ion battery pack that's capable of, 1,000-kilometer range, that battery becomes so massively heavy.
Right. It consumes a staggering percentage of your legal gross vehicle weight limit. So you end up paying your drivers to haul batteries instead of paying freight.
Which is a profound engineering and economic bottleneck. I mean, you're hitting a thermodynamic wall where the prescribed solution for decarbonization fundamentally breaks the economic model of your entire business.
Yeah, you literally can't afford to run the trucks.
We've spent the last decade watching the automotive industry try to force a passenger car solution onto the heavy-duty sector. And, scaling up a battery pack that works beautifully for a lightweight commuter vehicle.
Like a daily driver.
Right. Trying to use that to move 40 tons of cargo continuously over long distances introduces severe diminishing returns.
Because the energy density of even the best solid-state lithium cells simply cannot compete with the gravimetric energy density of chemical fuels.
Exactly. You reach a point where the mass of the energy storage medium just completely cannibalizes the payload.
Well, welcome to the deep dive. We are talking directly to you, the engineers, the fleet operators, the supply chain architects who are actually living in this reality right now.
Because the industry is not just sitting idle while the payload math fails.
No, they aren't. Today, we're unpacking a highly detailed stack of technical papers, engineering reports, and white papers, straight out of the 2026 47th International Vienna Motor Symposium.
It's a huge event.
Huge. And the central thesis coming out of Vienna this year is that the internal combustion engine, the very technology everyone assumed was destined for a museum, is actually undergoing a violent, high-tech, zero-emission renaissance.
It's fascinating. We are seeing hydrogen power and advanced alternative fuels move incredibly fast from proof of concept into hardened, mass-produced commercial reality.
And the overarching theme of the Vienna Symposium this year, the reports call it a pivot toward a resilient technology portfolio.
Right. The engineering community has largely discarded that binary assumption that decarbonizing global transport means exclusively adopting battery electric drivetrains.
That one-size-fits-all mentality is basically dead.
It really is. It's been replaced by a highly pragmatic approach.
Yeah.
Because when you look at the macro landscape detailed in these reports, the original equipment manufacturers, the OEMs, they're confronting a really fractured reality.
Oh, absolutely. I mean, we have severe ongoing supply chain bottlenecks for critical minerals, right? Lithium, cobalt, nickel.
Yeah, and unprecedented geopolitical shifts that affect material sourcing. Plus, perhaps most importantly, the regulatory environment is just completely fragmented.
Europe is super aggressive with its 2035 zero greenhouse gas mandates, but then major markets in Asia and South America are building entirely different infrastructure roadmaps.
Right, roadmaps centered around hydrogen and advanced biofuels instead of just the grid.
Because you can't design a single electric power crane architecture in Stuttgart or Detroit and just expect it to survive the operational realities of a mining operation in Chile.
Or a logging route in northern Canada. Yeah.
Huh?
The grid infrastructure to support multi-megawatt charging simply does not exist in those regions.
And it may never exist there. I think Hyundai captured this sentiment perfectly at the symposium. They introduced this engineering philosophy they call the culture of humility.
I love that term.
Me too. It's the idea that rather than dictating a singular technological mandate from the top down, the engineering sector has to acknowledge the diverse, messy, and vastly different energy infrastructures around the globe.
And that culture of humility is forcing manufacturers to adopt extreme modularity. I mean, they have to build platforms that can run on whatever low-carbon energy vector makes sense for that specific local market.
Because total cost of ownership, or TCO, is the ultimate arbiter here.
Always. For a commercial fleet, TCO dictates survival.
Yeah, if a fleet operator can't maintain payload capacity, turnaround times, and infrastructure compatibility, the technology fails. Doesn't matter how great its carbon footprint is.
Which brings us to why hydrogen internal combustion engines, or H2 ICE, basically dominated the Vienna proceedings.
Right, because wait, I think some people might ask, aren't we going backward by just burning things again?
It sounds like it, but the transition costs for H2 ICE are vastly lower than battery electric platforms because OEMs get to leverage billions of dollars of existing sunk capital.
They don't have to abandon their global foundry networks.
Exactly. Or their engine block casting plants. And furthermore, the global logistics industry already possesses this massive network of technicians who are intimately familiar with servicing reciprocating piston engines.
So H2 ICE preserves the payload capacity, maintains the rapid refueling times that fleets desperately rely on, and uses the existing manufacturing base.
It's a win-win. Looking at the mass production platforms detailed in the sources, Cummins is executing this modularity strategy flawlessly.
Yeah, with their new HEL-M platform, that stands for higher efficiency, lower emissions, multiple fuels. The architecture is just brilliant from a manufacturing economics perspective.
Because they've engineered a universal engine block.
Right, so below the head gasket, the block itself, the crankcase, the gear train, the connecting rods, the engine is identical regardless of the fuel it's going to burn.
It's the exact same casting. So if a customer in California needs zero emissions, they just bolt on a hydrogen-specific cylinder head and injection system.
But if a customer in a developing market lacks hydrogen infrastructure, they just bolt on an advanced diesel head instead.
Right, and the core engine rolls off the exact same assembly line. That kind of fuel-agnostic architecture fundamentally de-risks the transition for both the manufacturer and the fleet operator.
And the performance metrics prove this isn't just some compromise. Volvo presented data on their new 17-liter, 780-horsepower hydrogen
The
engine.
one utilizing low-pressure direct injection, or LPDI.
Yeah. The torque curve on this engine is astounding. We're talking 3,000 newton meters of peak torque available at just 1,000 RPM.
Which demonstrates definitively that burning hydrogen can replicate, and honestly in some metrics even exceed, the low-end grunt and continuous power delivery of traditional heavy-duty diesel engines.
It's incredible. But having a universal engine block is a massive win for the foundries. Hydrogen, though, is fundamentally dissimilar to diesel at a chemical level.
Oh, completely. I mean, it's the lightest, smallest molecule in the universe, and it is violently explosive.
Right, so taking a conventional internal combustion process and simply feeding it hydrogen introduces massive thermodynamic hurdles.
Yeah, if an engineer attempts to inject hydrogen gas into the intake manifold using standard port fuel injection, or PFI, the engine essentially tears itself apart.
Literally. Because PFI with hydrogen is structurally flawed for two main thermodynamic reasons, right? First is the issue of volumetric efficiency.
Yeah, hydrogen is an incredibly low-density gas. So when you inject it into the intake port, that hydrogen physically displaces the air.
It takes up too much room.
Exactly. In a heavy-duty application, you can lose up to 30% of the intake air volume just to the fuel gas itself.
Wow. And because an engine relies on the mass of oxygen entering the cylinder to generate power, displacing that oxygen with fuel drastically caps the specific power output of the engine.
Right, so you end up with a large, heavy engine producing very little usable torque.
You're just starving the engine of the oxygen it needs to create the combustion event.
Exactly. But the reports emphasize that the power loss is actually secondary to the catastrophic risk of backfiring.
Because hydrogen's minimum ignition energy is microscopic, right? We are talking about 0.02 millijoules.
To put that in perspective, a static shock from walking across a carpet contains orders of magnitude more energy than it takes to ignite a hydrogen-air mixture.
That's terrifying.
It is. Combine that microscopic ignition energy with hydrogen's massively high laminar flame speed.
So it burns incredibly fast.
Yes. As this highly combustible mixture of hydrogen and air is drawn past the intake valves and into the hot combustion chamber, any residual heat source will trigger it.
Like a microscopic deposit of carbon glowing on the piston crown.
Or even an exhaust valve that hasn't fully cooled down. It will instantly ignite the charge. And because the intake valve is still open during this stroke, the explosion propagates backward.
Violently blowing out through the intake manifold.
Exactly. This backfire destroys intake components. Alternatively, if the mixture manages to enter the cylinder and the valve closes, it will often pre-ignite during the compression stroke.
Long before the piston reaches top dead center.
Right. And that creates an opposing pressure wave that hits the rising piston, creating devastating mechanical stresses. It'll just shatter connecting rods and piston rings.
So to make a PFI hydrogen system survive, engineers have to run the mixture incredibly lean, vastly more air than fuel, and drop the compression ratio to lower the cylinder temperatures.
But dropping the compression ratio fundamentally ruins your thermal efficiency.
Yep.
You end up with a thermally crippled engine.
Which brings us to the thermodynamic breakthrough detailed at the symposium. They're completely abandoning PFI. We are looking at the commercialization of HPDI.
High-pressure direct injection.
Right. If PFI is akin to filling a room with highly volatile gas, throwing a match, and hoping the ensuing explosion pushes the piston smoothly.
Which it won't.
Right. HPDI is a paradigm shift. HPDI waits until the compression stroke is fully complete and then utilizes a microsecond-timed high-pressure laser beam of fuel to dictate exactly where, when, and how the combustion occurs.
It's brilliant. The alliance between Westport, the heavy-duty truck manufacturer Scania, and the Austrian engineering firm AVL has perfected this HPDI system.
And it solves the volumetric and ignition hurdles simultaneously, doesn't it?
It does. In an HPDI architecture, the engine breathes in pure, unmixed ambient air during the intake stroke.
So there's absolutely no fuel present in the cylinder initially.
Exactly. Zero risk of pre-ignition or backfire. The engine can compress that pure air to extreme pressures, allowing engineers to maintain the high compression ratios that make traditional diesel engines so efficient.
Because the piston compresses the air, generating immense heat, just like a standard compression ignition diesel cycle.
Right, but hydrogen's auto-ignition temperature is remarkably high, around 500 degrees Celsius.
So just compressing the air often isn't enough to guarantee a stable, uniform ignition of hydrogen gas when it is finally introduced.
And that is exactly where the Westport dual concentric needle injector is utilized. It is a masterclass in fluid dynamics and precision machining.
It's essentially a highly complex nozzle within a nozzle, right?
Yeah. Just milliseconds before the piston reaches top dead center, the inner needle lifts and injects a microscopic pilot charge of traditional diesel fuel or a renewable alternative like hydrotreated vegetable oil, HVO.
And this pilot injection represents only, 1 to 3% of the total fuel energy for that combustion cycle?
Exactly. Because it's diesel, it auto-ignites instantly in the highly compressed, superheated air.
Creating a stable, controlled plasma core, like a liquid spark plug,
A
essentially.
liquid spark plug, exactly. And the moment the diesel pilot ignites, the outer concentric needle lifts and pure hydrogen gas is blasted directly into that burning core.
But because the cylinder is already under massive compression, injecting gas into that environment requires violent force. The reports specify hydrogen injection pressures between 250 and 440 bar.
We are talking about forcing gas into a cylinder at over 6,300 pounds per square inch.
That is insane.
But that extreme injection pressure is vital. The hydrogen hits the burning pilot flame and ignites instantaneously.
But importantly, it doesn't explode all at once.
Right. It burns in a highly controlled diffusion flame. The rate of combustion is strictly dictated by the rate at which the injector sprays the hydrogen into the cylinder.
So the engineers are fully separating the air compression phase from the fuel introduction phase.
Yes. This yields the immense high compression efficiency of a diesel cycle without the carbon emissions.
And the efficiency data Scania published using this HPDI system completely rewrites the baseline for heavy-duty internal combustion.
Oh, absolutely.
I mean, the absolute theoretical ceiling for the most advanced, highly optimized heavy-duty diesel engines has hovered around 50 to 51% brake thermal efficiency, or BTE.
Meaning half the energy in the fuel reaches the flywheel, while the rest is lost to friction, pumping losses, and exhaust heat.
Right. But Scania's 13-liter HPDI hydrogen engine achieved 52.5% BTE.
It's staggering. Burning hydrogen at 440 bar is definitively more thermodynamically efficient than burning diesel.
Pushing an internal combustion engine past 52% BTE is a monumental achievement. But the Vienna Symposium laid out a conceptual roadmap that pushes the physics even further.
Yeah, AVL presented theoretical models aiming for what engineers consider the absolute holy grail of thermodynamics, 60% brake thermal efficiency.
60%. To understand how that's even mathematically possible, we have to look at the working fluid inside the engine. Currently, that working fluid is ambient air.
Which is roughly 78% nitrogen and 21% oxygen.
Right. And when you compress and heat air, the nitrogen is essentially an active participant in the thermal physics, but it does a terrible job of contributing to the mechanical work.
Because nitrogen is a diatomic gas. When it absorbs the immense heat energy from the hydrogen combustion, much of that energy goes into making the nitrogen molecules vibrate and rotate.
Rather than expanding outward to push the piston down.
Exactly. It has a relatively low specific heat ratio, meaning it requires a lot of thermal energy just to raise its temperature.
Energy that is ultimately just wasted out the exhaust pipe.
And beyond the thermodynamic inefficiency, the nitrogen in ambient air presents a severe emissions hurdle.
Ah, NOx.
Right. Under the extreme localized temperatures of a hydrogen diffusion flame, atmospheric nitrogen reacts with atmospheric oxygen to form nitrogen oxides, or NOx.
Which is a severely harmful criteria pollutant. So AVL's radical proposal, the argon closed loop cycle, just eliminates nitrogen entirely.
Completely. Instead of breathing atmospheric air, the engine operates as a sealed hermetic loop where the working fluid is pure argon gas.
Argon. a monatomic noble gas.
Yes, because it consists of single atoms rather than bonded pairs, it doesn't have internal vibrational or rotational modes to absorb heat.
So all the thermal energy dumped into argon by the burning hydrogen translates directly into kinetic energy translational velocity.
Exactly. Its specific heat ratio is much higher than air's. When the hydrogen ignites, the argon expands violently, transferring vastly more physical force against the piston during the expansion stroke.
It extracts the absolute maximum possible mechanical work out of the combustion heat.
The argon closed-loop cycle pushes the expansion work to the absolute physical limits dictated by the Carnot cycle.
The engine is supplied with pure oxygen and pure hydrogen, which are injected into this sealed argon environment.
The combustion occurs, the argon expands massively, pushing the piston down. But the most profound implication of this cycle is the chemical byproducts.
Right, because if you burn pure hydrogen and pure oxygen in an inert atmosphere of argon, the only chemical reaction occurring is two atoms of hydrogen bonding with one atom of oxygen.
Which means the exhaust gas is pure H2O, superheated water vapor, and hot argon.
There is zero nitrogen present anywhere in the system, meaning NUMX formation is physically impossible.
And zero carbon, meaning zero CO2 or particulate matter.
So the system routes this exhaust mixture through a condenser. The water vapor condenses into liquid water and is drained away, and the pure argon is looped directly back into the intake manifold to begin the cycle again.
It's elegant. Now, taking a closed-loop argon cycle from an AVL laboratory model to a commercial Class 8 truck vibrating down a highway presents staggering engineering challenges.
Right, like blow-by gas management, argon purity maintenance, and the parasitic losses of carrying pure oxygen tanks.
But the foundational physics are unequivocally sound. The pathway to a 60% efficient, zero-emission internal combustion engine has been clearly charted.
It's an incredible glimpse into the future of thermodynamics. But to implement the HPDI systems that are rolling off assembly lines right now, fleet operators face an immediate, massive logistical barrier.
Fuel storage.
Exactly. Operating an HPDI injector requires feeding it hydrogen gas at 440 bar. To achieve that kind of fuel delivery on a mobile platform that needs to travel 1,000 kilometers between refueling stops, you run headfirst into the density problem.
Storing hydrogen is arguably harder than burning it. Hydrogen's low volumetric energy density is the Achilles heel of the entire ecosystem.
The passenger vehicle market has largely standardized around Type 5 carbon fiber tanks storing compressed hydrogen gas at 700 bar.
But for a heavy-duty semi-truck, 700 bar gas is woefully insufficient. At that pressure, hydrogen only achieves a density of roughly 40 grams per liter.
So to carry enough energy to move an 80,000-pound rig across the country, the truck would require a massive array of high-pressure cylinders.
These tanks would consume the entire rear chassis. It destroys the aerodynamic profile of the tractor and severely cuts into the physical volume available for the cargo trailer.
Right, the volume penalty makes compressed gas a total non-starter for long-haul logistics.
Which is why the reports from the symposium point to liquid hydrogen, or LH2, as the mandatory storage vector.
But liquefying hydrogen requires driving the temperature down to an agonizing minus 253 degrees Celsius.
That is 20 degrees above absolute zero.
But when you chill hydrogen into a cryogenic liquid, its density leaps from 40 grams per liter to 71 grams per liter.
And this density shift allows engineers to package the required energy into settle tanks that fit neatly within the exact same footprint as traditional diesel tanks.
Companies like Forvia and SAG have engineered highly sophisticated cryogenic LH2 tanks for commercial application.
These tanks utilize multi-layer vacuum-jacketed insulation, essentially aerospace-grade thermos bottles.
But maintaining a fluid at 20 Kelvin in a terrestrial environment while a truck is parked on hot asphalt in the middle of summer introduces the critical issue of boil-off gas, or BOG.
Because no matter how advanced the vacuum insulation is, thermal energy will inevitably leak across the pressure vessel boundary.
So during a truck's dormancy period, say, over a long weekend when the engine isn't drawing fuel, that ambient heat leak causes the liquid hydrogen inside the tank to boil.
And as it transitions from a liquid back into a gas, the volume expands massively and the internal pressure of the tank begins to rise.
If that pressure reaches the structural yield limits of the vessel, the system has no choice but to open a mechanical relief valve and vent the hydrogen directly into the atmosphere.
Just to prevent a catastrophic rupture.
But fleet operators cannot tolerate a fuel system that literally evaporates their profit margins while the truck is parked.
Exactly. Mitigating BOG without adding heavy, power-hungry active refrigeration systems to the truck requires a breakthrough in passive material science.
And the Vienna reports detail the integration of metal organic frameworks, or MOFs, directly into the internal architecture of the cryogenic tanks.
MOFs are fascinating. They are highly crystalline structures composed of metal ions coordinated to organic ligands.
They form a microscopic, three-dimensional lattice that is incredibly porous.
To visualize this, picture an atomic-scale molecular scaffolding, where the vast majority of the structure is empty space.
Like a sponge.
Yeah, an atomic sponge. When the liquid hydrogen inevitably boils off into a gas, it doesn't just pressurize the empty headspace of the tank.
The hydrogen molecules encounter this massive internal surface area of the MOF.
And through weak intermolecular forces, specifically van der Waals forces, the hydrogen molecules are pulled against the lattice and held in place. This process is called physisorption.
Physisorption allows the MOF to trap an immense volume of hydrogen gas within its microscopic pores.
The specific material highlighted in the reports, NiM-DC, features exposed nickel sites that create high binding enthalpies for hydrogen.
So by absorbing the gas, the MOF effectively hides the hydrogen molecules from the bulk gas phase.
Right, which dramatically suppresses the overall pressure rise inside the tank. The critical metric here is the hydrogen recovery capability ratio, the HRCR.
And the engineering data demonstrates that utilizing these specific MOF beds improves the HRCR by 68%.
That 68% improvement is the difference between venting expensive fuel after 2 days versus parking the truck for a week and a half with zero fuel loss.
That's massive, and the beauty of physisorption is that it's completely reversible based on pressure.
Exactly. When the driver starts the truck and the engine begins drawing fuel out of the tank, the internal pressure drops.
The van der Waals forces are overcome, and the MOF naturally releases the trapped hydrogen gas back into the system to be utilized.
But even with the pressure stabilized, moving a cryogenic fluid at minus 253 degrees out of the tank and boosting it to the 440 bar required by the HPDI injectors is a severe mechanical challenge.
Right, because Bosch Rexroth showcased their dedicated cryopump designs at the symposium. Pumping a liquid this cold introduces the risk of cavitation.
If the mechanical action of the pump imparts even a small amount of frictional heat into the liquid hydrogen, it will boil directly on the impeller blades.
And those collapsing gas bubbles create microshock waves that pit and destroy the hardened steel of the pump.
So the cryopump utilizes highly specialized geometries and materials to move the hydrogen while it is in a supercritical state, minimizing thermal energy transfer and reducing the parasitic load on the engine.
Operating ultra-high pressure pumps and relying on molecular scaffolding to manage fluids at near absolute zero on a vibrating commercial vehicle is undeniably complex.
It's incredibly complex. And this complexity has driven a significant faction of the engineering community to question if there is a superior chemical carrier for hydrogen.
A carrier that remains liquid at manageable temperatures, which brings the entire symposium to the heavy-duty alternative vector, liquid ammonia, NH3.
Ammonia offers a massive logistical advantage. An ammonia molecule consists of one nitrogen atom bonded to 3 hydrogen atoms. It is entirely devoid of carbon.
So when burned, the primary byproducts are water and nitrogen gas. But its physical properties are what make it so attractive to logistics CEOs, right?
Absolutely. Ammonia liquefies at a very mild minus 33 degrees Celsius, or it can be stored as a liquid at room temperature under just 8.6 bar of pressure.
8.6 bar is trivial. You can store liquid ammonia in the exact same mild steel pressure vessels currently used to transport propane.
And because ammonia is the foundational ingredient for global agriculture and synthetic fertilizers, humanity has spent the last century building a massive global infrastructure for it.
We already have deepwater ports, pipeline networks, and millions of tons of dedicated storage facilities engineered specifically for handling liquid ammonia.
The distribution problem is essentially already solved.
But utilizing ammonia as an internal combustion fuel introduces severe chemical hurdles. Ammonia is highly recalcitrant.
It has an exceptionally slow laminar flame speed and a very narrow flammability limit.
So if you inject ammonia into a standard cylinder and attempt to ignite it with a spark plug, the flame front moves so sluggishly that the exhaust valve will open before the combustion is complete.
The engine will suffer massive power loss, and unburned ammonia will be pushed out the exhaust.
Which is unacceptable because ammonia gas is highly toxic to human biology.
So to force ammonia to release its energy, engineers have to create extreme thermodynamic environments. Aiken University and the engineering firm FEV published joint experimental data at the symposium detailing a 2.13-liter engine heavily modified for ammonia combustion.
To overcome the slow reaction kinetics, they pushed the compression ratio to a staggering 23-to-1.
They are compressing the air to such a violent degree that the internal cylinder temperatures skyrocket prior to fuel injection.
But even at a 23-to-1 compression ratio, ammonia won't reliably auto-ignite.
Right. The Aiken FEV architecture utilizes a dual-fuel pilot strategy directly analogous to the Westport HPDI hydrogen system.
They inject a tiny microdose of diesel fuel to act as the ignition source.
The diesel ignites under the extreme 23-to-1 compression, creating a high-energy plasma environment that forcefully cracks the ammonia molecules and accelerates the combustion process to a usable speed.
And the data on this pilot-ignited ammonia cycle is deeply impressive. They managed to achieve a 98% ammonia energy share.
Meaning only 2% of the combustion energy was sourced from the carbon-emitting diesel pilot.
Furthermore, they recorded thermal efficiencies approaching 50%. A heavy-duty engine running on agricultural fertilizer can actually rival the efficiency of a state-of-the-art diesel block.
The efficiency is verified, but burning ammonia introduces a critical environmental liability.
N2O, right.
Yes. While you eliminate CO2, incomplete ammonia combustion, or localized cold spots within the cylinder, can lead to the nitrogen atoms bonding with oxygen instead of pairing off harmlessly as N2 gas.
Specifically, the engine is at risk of emitting nitrous oxide, N2O, which is a greenhouse gas with a global warming potential nearly 300 times greater than carbon dioxide over a 100-year timescale.
So if an ammonia-powered truck emits even fractional amounts of N2O, it completely negates the climate benefits of using a zero-carbon fuel.
The chemical kinetics must be controlled with absolute precision.
The engine management software and the selective catalytic reduction, the SCR aftertreatment systems, have to monitor exhaust temperatures and inject urea at exact stoichiometric ratios.
Just to break down any NOx or N2O back into harmless atmospheric nitrogen and water before it reaches the tailpipe.
We are seeing the internal combustion engine evolve into a highly regulated chemical processing plant.
Whether the fuel is cryogenic hydrogen or high-compression ammonia, the pressures and temperatures are pushing metallurgy to its absolute limits.
And when you introduce hydrogen gas into these extreme pressure environments, you trigger an invisible, catastrophic war at the atomic level.
Right. This is the challenge of hydrogen embrittlement and dry gas tribology. The sources from the Vienna Symposium dedicate immense space to hydrogen embrittlement.
It is the silent killer of H2ICE architectures.
Because hydrogen is an H2 molecule, but under the extreme 440 bar pressures and localized heat generated inside an HPDI fuel injector or a high-pressure fuel rail, those diatomic molecules dissociate.
They break apart into single solitary hydrogen atoms, effectively just single protons with an electron.
And because a single hydrogen atom is the smallest physical entity in the universe, it doesn't respect the surface boundaries of solid metal.
No, it doesn't. The hydrogen atoms physically diffuse directly into the crystalline lattice structure of the high-strength steel used to forge the engine components.
Like atomic termites.
Exactly. They migrate to the interstitial spaces between the iron atoms and congregate at microscopic structural defects, voids, and the grain boundaries of the alloy.
So once these solitary hydrogen atoms gather in a microscopic void deep inside the steel, they find each other and recombine back into H2 gas.
But they are trapped inside the solid metal. As more atoms diffuse in and recombine, the internal pressure of that trapped gas begins to skyrocket, completely independent of the external pressure in the fuel line.
The steel is literally being inflated from the inside out.
And this internal pressure severely compromises the ductility of the metal. The steel loses its ability to yield or flex under load. It becomes fundamentally brittle.
So a high-strength steel fuel injector component that was engineered to operate flawlessly for millions of cycles will suddenly, without any warning, suffer a catastrophic fatigue fracture.
The metal will simply shatter under the cyclic loading of the 440 bar injection pulses.
But engineers can't change the physical size of a hydrogen atom, and they can't change the crystalline nature of steel. So to make an H2ICE survive, they have to apply nanoscale armor.
The Swiss surface engineering firm Ion Bond presented their breakthrough mitigation strategies, utilizing diamond-like carbon or DLC coatings.
They utilize physical vapor deposition and chemical vapor deposition to apply protective layers that are microscopically thin, yet fundamentally alter the surface chemistry of the engine internals.
DLC coatings are a fascinating application of material science. The coating is an amorphous matrix of carbon atoms that features both sp2 and sp3 hybridized bonds.
The sp3 bonds are the exact same tetrahedral atomic structures found in natural diamonds, giving the coating extreme hardness and structural integrity.
This dense sp3 matrix creates an impenetrable physical barricade. The permeability of the ion bond tribobond coating is measured at 10 to the negative 15th power.
Wow. It effectively seals the metal lattice, preventing the solitary hydrogen atoms from ever making contact with the vulnerable steel underneath.
It stops the embrittlement entirely. But the DLC coating has a vital secondary function that addresses another catastrophic reality of hydrogen fuel.
Hydrogen is an entirely dry gas.
Exactly. Traditional liquid fuels like advanced diesel or heavy fuel oil are inherently viscous. As they are pumped through the extremely tight clearances of fuel rails and injector plungers, they act as their own lubricant.
Maintaining a microscopic hydrodynamic film that keeps the metal parts from grinding against each other.
But hydrogen provides zero lubricity. If you attempt to actuate a bare steel fuel injector needle at 440 bar while immersed in dry hydrogen gas, the metal-on-metal friction will generate massive localized heat,
leading to galling and eventual seizure within minutes.
This is where the sp2 hybridized carbon bonds in the DLC coating become critical. The sp2 bonds are the planar structures found in graphite. They provide inherent solid-state self-lubrication.
So the DLC coating drops the friction coefficient of the internal injector components to below 0.05.
It creates an incredibly slippery surface that allows the valves, plungers, and needles to slide against each other for millions of cycles under extreme load, entirely without liquid lubrication.
The nanoscale coating solves both the atomic diffusion of embrittlement and the tribological nightmare of dry gas injection simultaneously.
However, coating the fuel delivery system does not protect the crankcase.
The oil.
The combustion of hydrogen fundamentally alters the chemical environment of the engine oil. When hydrogen and oxygen burn, the primary exhaust product is superheated water vapor.
And in any reciprocating piston engine, a percentage of the high-pressure combustion gases will inevitably slip past the piston rings and travel down into the crankcase. This is known as blow-by.
In a traditional diesel engine, blow-by introduces soot and unburned hydrocarbons into the oil. In an H2ICE, you are blasting massive volumes of superheated steam directly into the oil pan.
Focus Lubricants detailed the sheer scale of this lubrication crisis. When that steam hits the relatively cooler engine oil, it condenses back into liquid water.
And the mechanical churning of the crankshaft then aggressively whips that liquid water and the lubricating oil together.
Now, oil and water naturally repel each other, but under high mechanical shear, they form an emulsion. The engine oil degrades into a thick, milky sludge.
Like a milkshake.
Yeah. This emulsion dramatically alters the kinematic viscosity of the oil. It loses its film strength, meaning it can no longer maintain the crucial hydrodynamic wedge inside the main journal bearings.
The bearings make metal-to-metal contact with the spinning crankshaft, and the engine rapidly destroys itself.
So to combat this, chemical engineers at Fuchs had to completely reformulate the baseline chemistry of heavy-duty engine oil. They engineered specific anti-emulsification additive packages.
These utilize highly specialized surfactants that alter the surface tension of the water droplets, forcing the water to rapidly separate out of the oil suspension.
So it can be evaporated off by the crankcase ventilation system, preserving the oil's viscosity.
But water separation is only half the battle. They also had to address the extreme sensitivity of the hydrogen combustion process.
Right, because in a heavy-duty engine, microscopic droplets of engine oil will occasionally splash up past the oil control rings and enter the combustion chamber.
And traditional diesel engine oils are packed with metallic additives, calcium and magnesium detergents that leave behind an ash residue when burned.
If an ash-heavy oil droplet enters a hydrogen combustion chamber, that metallic ash acts as a highly active catalyst.
It will instantly trigger low-speed pre-ignition, or LSPI.
The oil droplet itself will cause the hydrogen gas to prematurely explode before the piston reaches the top of its stroke, inducing the massive pressure spikes that shatter connecting rods.
The engine oil literally becomes the trigger for an engine-destroying knock event.
This forced the development of entirely new ashless or severely low-ash oil formulations. Fuchs utilizes over-based phenate detergents that are chemically designed to neutralize the acidic byproducts formed by the blow-by gases.
But they do so without introducing the metallic catalysts that trigger LSPI. It is a brilliant example of how changing a single variable in an engine, the fuel source, forces engineers to reinvent the chemistry of every single fluid, coating, and alloy in the entire mechanical ecosystem.
Synthesizing the data presented across the entirety of the Vienna Motor Symposium, a very clear narrative emerges for the future of heavy-duty transport.
The transition away from fossil fuels is not going to be a monolithic shift toward massive lithium-ion batteries.
The sheer physics of moving 80,000 pounds of cargo efficiently dictate that we must maintain the energy density and payload capabilities of the internal combustion engine.
But the engine itself is undergoing a radical metamorphosis.
We are witnessing the integration of technologies that sound like science fiction into commercial, mass-produced platforms.
From the microsecond precision of high-pressure direct injection, utilizing dual concentric needles to establish a diffusion flame, to the deployment of metal-organic frameworks manipulating van der Waals forces to hold cryogenic fluids in a state of suspended animation.
We are watching metallurgists use physical vapor deposition to coat engine internals with synthetic diamonds to hold back the atomic diffusion of the smallest element in the universe.
The internal combustion engine is not a dinosaur waiting for extinction. It is an incredibly adaptable, highly resilient technology platform that is evolving to meet the demands of a zero-carbon economy.
And this evolution leads to a fundamental shift in how we perceive mechanical engineering and environmental impact. For over a century, the defining characteristic of the combustion engine has been pollution.
We associate the roar of a heavy-duty truck with a plume of black soot, nitrogen oxides, and carbon dioxide.
We have been conditioned to view the tailpipe as a source of environmental degradation. But the technologies discussed today, specifically architectures like the argon closed-loop cycle or the highly catalyzed ammonia platforms, are rewriting that relationship.
When you achieve perfect hydrogen combustion, the chemical reality is that the exhaust gas is fundamentally cleaner than the ambient air the engine breathed in.
It forces a philosophical question about the machines we build. If a massive 80,000-pound Class 8 truck is rolling down the highway generating 3,000 newton-meters of torque, and the only compound exiting the exhaust stack is chemically pure water,
The vehicle is no longer a polluter.
it is effectively a mobile mechanical air purifier. If the internal combustion engine can be engineered to leave the atmosphere cleaner than it found it, it changes the entire calculus of how we power global logistics. Keep examining the data, keep challenging the consensus, and keep analyzing the physics behind the headlines. Thank you for joining the deep dive.
Imagine, right, you are driving, say, 70 miles an hour down this really steep, winding mountain pass.
Oh, terrifying.
Yeah, exactly. And you press the brake pedal. Now, in a legacy car, like something built maybe 10, 15 years ago, you're triggering a very simple, very mechanical chain reaction.
Right, the physics are totally direct.
Exactly. You push a lever, hydraulic fluid run through a physical line, it pushes a caliper, and then the brake pad physically clamps down on the spinning metal rotor, and, well, the car slows down.
It's totally deterministic.
Right. You apply force A, and you get result B every single time.
Yeah, it's a completely closed loop of mechanical certainty, which, we find really comforting because when we're hurtling down a highway wrapped in like 2 tons of metal, we really want those underlying systems to be absolute.
We want them visible.
Visible, predictable, exactly. No guesswork.
But the reality of modern automotive design it's completely shattered that mechanical certainty.
Oh, completely. It's a whole new world.
Because in a cutting-edge software-defined vehicle, or an SDV, that brake press isn't just a physical lever anymore. It's a digital suggestion.
A suggestion, that is a great way to put it.
Right. And that suggestion gets intercepted by this massive neural network. It's processed alongside, thousands of other data points from radar, cameras, LiDAR.
Yeah, all in a fraction of a millisecond.
And then the computer makes a probabilistic guess about the absolute safest way to apply stopping force. Which, honestly, begs an incredibly terrifying question for you, the listener.
It really does.
How do you guarantee your car stops when the brain operating it is, at its core, a guessing machine?
That tension right there between the probabilistic nature of artificial intelligence and the super rigid, life and death deterministic safety we need on the road, that is the defining engineering crisis of our era.
Well, welcome to another deep dive. Today, our mission is to explore this just radical mutation happening in the automotive industry. We're looking at a landscape where cars, they're no longer treated as mechanical machines that just happen to have some software slapped on board.
Not at all. They are rolling data centers.
Literally data centers on wheels.
Yeah.
And to understand this, we're unpacking 2 massive, highly technical sources today.
From the 2026 International Vienna Motor Symposium,
So
right?
looks like we've got a strategic blueprint and this insanely dense research report covering the absolute vanguard of SDVs and AI.
And what makes these symposium documents so compelling is that, well, we aren't looking at consumer-facing marketing brochures here. Like, this isn't a glossy ad.
No PR spin.
Right, no spin. These are the raw, unvarnished blueprints that the top engineers on the planet are using to literally rewire our transportation infrastructure from the inside out.
We are looking at next-generation architecture, microscopic system security, and AI-driven R&D. And for you listening, whether you work in the tech space, the auto industry, or you're just someone who, like me, sits behind the dashboard of an EV and wonders what unseen digital scaffolding is keeping you alive on your commute.
Which is a very valid thing to wonder about.
Totally. We are going to break down exactly how this massive technological friction is being solved. But before we get into taming an AI brain, I feel like we have to talk about the physical body of the car first.
Yeah, you really have to start with the hardware.
Because you can't just take an advanced high-bandwidth neural network and drop it into the legacy wiring of a 2015 sedan.
No, the physics simply will not allow it. The plumbing is entirely wrong.
Right. So to understand why, talk to us about how traditional cars were built over the last, say, few decades.
So traditionally, the industry used what's called a distributed architecture. Basically, whenever automakers wanted to add a new feature to a car, say anti-lock brakes or power windows, adaptive cruise control, seat heaters, whatever, they didn't integrate it into one main computer.
They just sort of bolted it on.
Pretty much. They would just slap a brand new, completely isolated microcomputer into the car to handle that one specific task.
And these are the electronic control units, right? The ECUs.
Exactly. ECUs. And the symposium sources point out that modern legacy cars are basically crawling with them. We're talking over 100 individual isolated ECUs just scattered throughout the chassis.
Over 100. So it's like 100 little fiefdoms all operating completely independently.
Yeah, 100 little fiefdoms. And the way they talk to each other is through these incredibly old static routing protocols called CAN and LIN.
Okay, hold on. Slow down there, because that is definite acronym soup. What are CAN and LIN, and why are they a problem for modern AI?
Fair enough. So CAN stands for Controller Area Network, and LIN is Local Interconnect Network. Think of them as the automotive equivalent of, like, dial-up internet.
Oh, wow, that old.
Yeah. They were designed back in the 1980s and 90s to send tiny, super simple messages, basically just an on-off switch, like roll down window or turn on headlight.
Just tiny blips of data.
Exactly. They operate at incredibly low bandwidths. We're talking measured in kilobits per second. Now, contrast that with the needs of a modern autonomous driving AI.
Which needs, what, gigabytes?
Gigabytes of high-definition camera and LiDAR data every single second.
So trying to run a modern AI on an old CAN bus is essentially like trying to stream a 4K movie through a 1995 dial-up modem.
The system would just choke and crash. Actually, it wouldn't even be a crash. It would just be a catastrophic failure to even transmit.
You couldn't hand to the pipeline.
Right. Plus, just physically wiring 100 different computers together requires a wiring harness that looks like a massive plate of spaghetti.
I can imagine.
In some luxury cars, the copper wiring alone can weigh over 150 pounds.
Wait, really? Just the wire?
Just the copper wire, and it can stretch for miles. It's heavy, it's fragmented, it's hardware-bound, and it entirely lacks the edge computing power needed to process advanced neural networks.
So it sounds like the engineers at Vienna had to propose a pretty brutal simplification.
They did. They are tearing out those 100 tiny brains and moving to what they call the 4SDV zonal intelligence architecture.
Okay, 4SDV zonal intelligence architecture. Walk us through this map. How do you consolidate 100 random ECUs?
Well, you divide the vehicle into physical geographical zones rather than dividing it by function.
Okay, so locations, not tasks.
Exactly. Typically, this is mapped out as 4 primary quadrants. Zone 1 is the front, which physically manages everything nearby, so the powertrain, the front radar, headlights. Zone 2 is the right cabin, managing the passenger side infotainment and climate. Zone 3 is the left cabin, handling the driver's steering and instrument cluster. And then Zone 4 is the rear, dealing with the rear chassis, taillights, rear cameras.
Okay, so I have 4 regional managers now instead of 100 interns.
That's a great way to look at it.
But how do they actually talk to each other without recreating that 150-pound spaghetti wiring problem?
They ditched the old CAN and LIN copper wires entirely.
Oh, completely gone.
Gone. and they replace them with a massive high-bandwidth Ethernet backbone that connects all 4 zones to a single central compute hub, the main brain.
An Ethernet backbone, like in an office building.
Basically. But when the blueprint says high bandwidth, they mean data transfer speeds of 50 to 90 gigabits per second.
Wait, 90 gigabits per second? That is wild. I mean, most people's home fiber optic internet is, what, 1 gigabit per second?
Right.
So the car essentially has an enterprise-grade server network running through the floorboards.
It has to. It absolutely has to. But here is the critical engineering bottleneck. Even with a 90 gigabit backbone, if you take every single raw data point from 4 high-definition cameras, 3 LiDARs, the radar, and 100 other sensors,
Which is a tidal wave of data.
a literal tidal wave. And if you dump all of that raw data simultaneously into the central compute hub, that central brain will get totally overwhelmed.
Right. It's the classic data center problem. You just have too much noise and not enough signal.
Exactly, which is why the zonal control units, those regional managers, as you called them, they're just dumb routers passing data along.
They actually do some thinking.
Yeah, they feature integrated neural processing units, or NPUs. They act as edge AI.
Okay, so edge meaning they're operating at the physical edge of the network right next to the sensor, rather than, all the way back at the central hub.
Right. The edge AI acts as a highly intelligent filter.
Give me an example of how that works in real time.
Sure. Let's say the front camera in zone 1 is recording video at 60 frames per second. The local NPU analyzes that raw video right there, in real time. It sees a mailbox, it sees a cloud, maybe a parked car.
Stuff that doesn't really matter.
Right. It doesn't bother sending any of that boring, useless pixel data to the central brain. It just discards it.
Saves the bandwidth.
Exactly. But the moment a child steps off a curb into the street, the NPU isolates that specific object, turns it into a tiny, highly compressed packet of critical insight.
Like pedestrian detected at coordinates XY.
Exactly. And it fires only that insight down the Ethernet backbone to the central brain.
Okay, so it's filtering the noise so the central brain only has to make decisions on the most urgent, compressed intelligence. But I gotta ask, if we are sending life or death data packets like a pedestrian stepping into the road, how does the network guarantee the data doesn't get stuck in traffic?
What do you mean?
Well, because I've been on Ethernet networks. Sometimes there's a lag, right? You click a link and it hangs for a second. If the break now packet hangs for a second in a car going 70, someone dies.
You've hit on a massive concern. This is exactly where the blueprint outlines what they call the golden triangle of network protocols.
The golden triangle.
Right. To ensure absolute reliability over this Ethernet backbone, they layer 3 highly advanced software protocols on top of each other. The first one is called DDS.
Okay, what does DDS actually do?
It stands for Data Distribution Service. It uses a publish-subscribe model with very strict quality of service guarantees.
Publish, subscribe. Like a newsletter.
Kind of. Instead of a sensor trying to figure out exactly where to send its data, it just publishes it to the network, and the systems that need it subscribe to it. DDS basically guarantees that the data gets to the right subscriber without dropping any packets.
Okay, but getting there safely isn't enough, right? It has to get there on time.
Exactly. And that's the second pillar of the triangle. TSN, or time-sensitive networking.
Time sensitive.
Yeah. Normal Ethernet is what we call best effort. It sends packets when the line is clear. TSN forces the network to adhere to a master synchronized clock, accurate down to the nanosecond.
Wow, nanoseconds.
It uses very strict traffic shaping. Think of it like an ambulance lane on a crowded highway.
Oh, I see.
TSN clears the lane so that critical safety data, like an emergency braking command, bypasses all other data traffic and arrives with microsecond deterministic latency.
So it never gets stuck behind, say, an infotainment packet requesting a Spotify song from the cloud.
Precisely. Safety always gets the VIP lane.
Okay, so DDS for routing, TSN for absolute speed was the third pillar.
Zenoh. Z-E-N-O-H. It's a protocol designed to connect this incredibly fast internal car network seamlessly to the cloud and to robotic operating systems.
So it reaches outside the car.
Right. It allows the car to talk to external infrastructure without losing any of that internal efficiency we just built.
Okay, let me push back on this entire philosophy for a second, though. Because consolidating everything into 4 zones and a single central brain sounds incredibly elegant on paper.
Right.
But aren't we just creating a massive, terrifying, single point of failure? I mean, in the old days, if my radio ECU died, my radio stopped working, but my brakes still had their own computer.
Right.
If this new central compute hub glitches or overheats, doesn't my entire car just shut down at highway speeds?
It's definitely the most common criticism of centralized architecture. And the symposium sources spend a massive amount of time outlining the solution, which is fail operational safety systems.
Fail operational, meaning the system is designed so that when it breaks, it doesn't just stop. It keeps working in a degraded state.
Think of a commercial airplane. If a jet loses an engine mid-flight, it doesn't immediately fall out of the sky, right?
Right, it can glide or fly on one engine.
Exactly. It is designed to fly on one engine long enough to land safely. The 4SDV architecture builds in that exact same redundancy. Remember those zonal control units? The ones with their own edge AI?
Yeah, the regional managers.
Right. They have independent compute power and redundant safety logic baked directly into their silicon. So if the central compute hub completely crashes like a total blackout, the local ECUs instantly realize the main brain is gone.
Oh, they know it died.
They know immediately. And Zone 1, which manages the front, can autonomously execute an emergency braking maneuver. Zone 3, managing the steering, has enough independent intelligence to steer the car smoothly to the shoulder.
Really? Just on their own?
Yeah, they don't need the central brain to execute a safe stop.
So the zones act as a decentralized safety net, catching the car if the main brain fails. That's actually brilliant. But, building this robust hardware pipeline only reveals a much more complicated, almost philosophical problem when it comes to the software running inside it.
The AI itself.
Exactly, because the central brain is using AI to make high-stakes decisions. And that brings us to the existential wall of certification. Like we asked at the top of the show, how on earth do you certify a guessing machine?
It really is an existential crisis for the regulators. To understand the panic, look at the old standard ISO 26262.
ISO 26262.
Yeah, for decades, this was the absolute Bible for automotive functional safety, but was built entirely around deterministic code.
Deterministic code meaning like traditional programming. If this happens, do that.
Exactly. If the radar detects an object 10 feet away, apply 50% brake pressure.
Yeah.
Human regulators could physically read the code line by line.
They could test it in a lab.
They could test it. They could mathematically prove that there were no bugs in the logic.
But a modern deep neural network isn't written like that at all. No programmer sits down and types, if pedestrian, then brake.
No, a neural network is basically a black box. It consists of billions of artificial neurons with weighted connections. It isn't programmed, it is trained.
On massive amounts of data.
Right, until it learns to recognize patterns itself. You cannot open up an AI model, point to a specific line of code, and say, here is the logic for recognizing a stop sign.
Because the logic is distributed across millions of abstract numerical weights.
Exactly, it's emergent. So if a regulator asks, hey, why did the car turn left instead of right? The engineer's honest answer is often, we don't entirely know. The pattern recognition just strongly suggested left was safer.
I mean, that must terrify regulators. You can't put a government stamp of approval on a black box that you can't read.
And yet they have to, because AI is the only way to achieve advanced autonomy. The rigid if-then code just can't handle the complexity of the real world.
So how did Vienna solve this?
The solution presented at the symposium is the ISO PS 8800 AI-driven safety standard.
ISO PS 8800.
Yes. This is a monumental historical shift in engineering. It moves the entire industry away from deterministic code validation, where you check if the code have a bug, to probabilistic data validation.
So checking if the data is sound rather than checking the code itself.
Right. The whole premise is, if the AI is simply a reflection of its training data, then the only way to certify the AI is to relentlessly interrogate the data it was trained on.
That makes a lot of sense.
So they outline this data-centric V model consisting of 5 incredibly strict layers: the training dataset, the validation dataset, the test dataset, the production dataset, and finally, the field monitoring dataset.
So you aren't debugging code anymore. You're basically debugging massive libraries of human experience.
That's exactly what it is.
Let's focus on that last layer for a second. The field monitoring dataset. The sources refer to this as the data flywheel. How does that actually work in practice for the person driving the car?
So It creates a continuous closed-loop telemetry system. Let's say you buy a 2026 SDV and you drive it in a very strange, totally unprecedented environment.
Give me an example.
Maybe a highly unusual temporary construction zone in the middle of a dense blizzard in Austria.
Okay, extremely specific, very messy.
Very messy. The car's AI is struggling. It hasn't seen the specific pattern of traffic cones and snow before.
It's uncertain.
Right, its confidence level drops. The field monitoring system detects this uncertainty. It then automatically records the sensor data from that specific encounter and beams it back to the automaker's cloud server.
Just that specific weird event.
Yes. The automaker's supercomputers then take your blizzard construction zone and add it to the master training dataset. They retrain the master AI model so it now understands that exact scenario.
Oh, wow.
They validate it, and then they beam the updated, smarter AI back down to your car and every other car on the road via an over-the-air update.
That's the flywheel. The more the cars drive, the more weird edge cases they encounter, the more data they send back, the smarter the AI gets, which makes the cars drive better. It's a continuous cycle of evolution.
Exact.
But, and this is a massive but for me, the flywheel takes time. The AI has to encounter the weird situation, beam it back, learn, and update. What happens in the moment? When I am driving through that weird blizzard construction zone today, and the AI gets confused today, how do we prevent the car from doing something fatal while it's still waiting for that update?
That is the multi-billion-dollar question. How do you deploy an imperfect, probabilistic AI legally and safely right now?
Right.
The symposium blueprint details a mechanism called the safety cage architecture, and honestly, it is a masterpiece of pragmatic engineering.
How do you build a cage for math?
You isolate the unpredictable elements. Inside the central computer, you have the primary channel. That's your advanced high-dimensional neural network. It's brilliant, it can handle complex traffic, but it's probabilistic and, well, prone to hallucination if it gets confused.
Right.
So you physically and logically wrap that primary channel inside a deterministic supervisor.
The supervisor being an old-school, rigid, if-then computer.
Yes, a classical microcontroller unit. It doesn't know how to navigate complex traffic at all, but it knows the absolute laws of physics and safety. Do not hit object in front of car. Stay between the lines.
So it's basically like having a teenage prodigy behind the wheel. The teenager has superhuman reflexes and can navigate chaotic city streets brilliantly most of the time.
Right.
But because they lack life experience, they are prone to occasionally making a wildly irrational decision. To counter this, there is a grizzled, totally unyielding driving instructor sitting in the passenger seat.
I love this. Yes.
And the instructor has their own set of emergency brake pedals. They let the teenager do all the driving, but the absolute millisecond the teenager tries to do something structurally unsafe, the instructor stomps on the brakes and takes the wheel.
That is a phenomenal analogy. The teenager is the AI and the instructor is the deterministic supervisor. But the real genius of the system is how the instructor knows the teenager is confused.
How does it know?
The mechanism is called the out-of-distribution, or OOD detector.
OOD, out of distribution, meaning the data the car is seeing right now is outside the distribution of data the AI was originally trained on.
Exactly. And the OOD detector calculates this confusion in real time using a mathematical concept called the Mahalanobis distance.
Okay, we definitely need to slow down and unpack this, because Mahalanobis distance sounds like a coordinate in deep space. What is this math, and how does it save my life?
Fair point. To understand Mahalanobis distance, you first have to contrast it with normal, everyday distance, which is called Euclidean distance.
Euclidean, like standard geometry.
Right. If I ask you the distance between two dots on a piece of paper, you just draw a straight line with a ruler. That's Euclidean. But data in an AI doesn't exist as simple dots. It exists as dense clusters or clouds of statistical probability.
A distribution.
Right. Let's say the AI was trained entirely on images of clear, sunny California highways. The cloud of its training data is very tight around characteristics like high contrast, visible lane lines, dry asphalt.
Okay, I'm picturing the cloud.
Now, you drive into that Austrian blizzard. The data coming from your sensors is whiteout conditions, zero lane lines, icy reflections.
So the OD detector plots the current sensor data and sees how far it is from the center of that sunny California training cloud.
Yes, but here is why Mahalanobis is brilliant. It doesn't just measure a straight line to the center of the cloud. It measures distance in terms of standard deviations, accounting for the shape and variance of the data.
What do you mean?
It basically asks, Statistically speaking, what are the odds that this blizzard data actually belongs to the sunny California data set?
And the math returns an answer of basically 0. The distance is massive.
It's a massive Mahalanobis distance. The OD detector instantly fires a red flag to the deterministic supervisor. It essentially yells, "The AI is completely out of its depth. The scenario we are in is statistically alien to everything it knows."
Wow. And what happens next? Does the car just freeze?
The moment that threshold is crossed, the supervisor physically locks the AI out of the steering and braking controls,
Just cuts it off completely.
overrides the primary channel entirely, and triggers what they call a graceful degradation to a safe state.
Graceful degradation. What does that actually look like for the driver?
Well, it depends on the severity, but typically the rigid supervisor takes over, flashes massive warnings across the dashboard demanding the human driver take the wheel immediately.
Right. Take over now.
Yeah, while simultaneously executing a smooth, deterministic deceleration to bring the car to a halt on the shoulder using the safest, simplest path available, the AI is officially caged before it can make a fatal guess.
That is mathematically beautiful. We let the AI be brilliant, but the moment it encounters the unknown, we quantify its ignorance and lock it down.
Exactly.
We've successfully protected the car from its own internal brain. But, decentralizing the architecture, relying on OTA cloud updates, feeding the data flywheel, haven't we just built a massive rolling attack surface for external threats? Because by connecting the car to the world so seamlessly, it feels like we've just invited every hacker on the planet into the dashboard.
You've hit on the exact terror keeping automotive executives awake at night right now. If you thought the safety regulations surrounding the AI were strict, the new legal mandates surrounding cybersecurity are downright draconian.
Really?
Oh yeah, the symposium devoted a huge amount of focus to navigating the EU NIS2 directive.
We've actually talked about NIS2 on the show before, but usually in the context of critical infrastructure, like, power grids or water treatment plants.
Yeah.
How does it apply to cars?
Under NIS2, a connected, software-defined vehicle is now classified essentially as critical network infrastructure. Wow.
And the directive forcefully shifts cybersecurity from being just an IT problem to being a board-level, vehicle-critical legal mandate.
So it's no longer just the chief information security officer dealing with a breach in a back room. The CEO and the board of directors are now legally on the hook.
Personally and legally liable. If an automaker suffers a breach and the regulators find they were negligent, the executives can face massive personal penalties.
Personal penalties.
Yes, and the company can be fined up to 2% of its total global turnover.
Which for a giant automaker is billions of dollars.
Exactly. But the most stressful part of NIS2 is the ticking clock. The directive mandates an absolute 24, 72-hour reporting window.
Walk me through that timeline. Let's say a hacker breaches the car's network. The clock starts. What happens?
The automaker has exactly 24 hours to provide an early warning report to the national cybersecurity authorities. They have to declare, "We've been hit, and here is our initial assessment of the threat."
Just 24 hours to realize it and report it. Right. Then they have exactly 72 hours from the moment of discovery to provide a comprehensive, detailed incident report outlining the vector of attack, the compromised systems, and their exact mitigation strategy.
Okay, 72 hours is absolutely nothing in a corporate investigation.
Nothing.
Usually it takes companies weeks just to figure out what server got compromised. But here is my pushback on this entire directive.
Let's hear it.
A modern car is an amalgamation of parts from thousands of different companies scattered across the globe. You have the automaker, the OEM, but then you have Tier 1 suppliers making the major systems, Tier 2 suppliers making subcomponents, and, Tier 3 suppliers writing tiny snippets of code for a windshield wiper sensor in a factory halfway around the world.
Right.
How can the automaker possibly guarantee the security of every single line of code from all those different people?
You are describing what cybersecurity experts call the supply chain cascade or the bottom turtle problem.
Yeah, the bottom turtle problem. I like that.
Because under NIS2, the OEM cannot pass the blame. They are legally responsible for the security of their entire supply chain all the way down to that Tier 3 wiper sensor.
That sounds like a complete administrative nightmare. If a giant company like Volkswagen or Toyota has to manually vet every single line of open source code used by a third-party vendor making a seatbelt sensor, it would grind innovation to an absolute halt. The bureaucracy alone would take years.
It is a staggering administrative burden. Because hackers are smart. They don't try to brute force the central firewall of a major automaker.
No, they look for the side door.
They look for the weakest link. They look for an unpatched vulnerability in some obscure open source library used by the company that makes the Bluetooth module for the infotainment system.
And they use that tiny, forgotten backdoor to get into the car's entire network.
Exactly. So to survive this legal mandate without totally stopping production, the industry is standardizing two automated tools, SBOMs and VSOCs.
Okay, let's translate those. What is an SBOM? SBOM.
Software bill of materials. Think of it as an exhaustive, machine-readable ingredients list for the entire car.
An ingredients list.
Yeah, it documents every single piece of proprietary code, every open source library, every single version number, across every component from every supplier.
Wow.
It creates a massive, infinitely searchable database of the car's complete digital DNA.
And how does the VSOC use that? And what is a VSOC?
The Vehicle Security Operations Center. It's an automated command center. Let's say a security researcher discovers a new critical zero-day vulnerability in an obscure open-source audio compression library.
Right.
The VSOC doesn't need to call thousands of suppliers and ask, hey, do you guys use this code?
They just search the database.
It instantly queries the fleet's SBM. Within seconds, it identifies exactly which cars, down to the specific VIN number, have that vulnerable code in their infotainment unit.
And then what?
It automatically queues an over-the-air patch to secure the vulnerability before a hacker can even exploit it.
Okay, that covers patching vulnerabilities. That's preventative. But let's assume the worst-case scenario.
Okay.
Let's say the VSOC is too slow. A hacker successfully exploits a vulnerability in a third-party music app and gains access to the infotainment system inside Zone 2 of our architecture.
Right, they're in the right cabin zone.
They are inside the car's internal network. What stops them from just sending a malicious command across that 90 gigabit Ethernet backbone to the Zone 1 braking system?
The answer to that is the death of implicit trust.
Implicit trust.
In legacy networks, once you were inside the firewall, you were trusted. It was a hard outer shell with a soft, chewy center. If the radio wanted to talk to the brakes, the network just allowed it.
Because it assumed if you're inside, you belong there.
Exactly. To fix this, the Symposium blueprint outlines a strict zero-trust architecture relying on microsegmentation, specifically using frameworks called SPIFE and SPIRE.
SPIFE and SPIRE. Explain the mechanics of this microsegmentation. How do you compartmentalize a unified network?
Think of a military submarine. It's not just one big open tube, right?
No, it has doors.
It is divided into multiple compartments, separated by thick, waterproof bulkheads. If a torpedo breaches the forward torpedo room, the water rushes in, but the crew seals the bulkheads. The flooding is completely contained to that one microsegment.
And the rest of the submarine survives.
Exactly. So even if the hacker breaches the infotainment system, they are trapped in that compartment. The bulkheads are sealed.
How does the network actually seal a bulkhead, digitally speaking?
The zero-trust architecture blocks all lateral movement, meaning sideways movement across the network. It assumes a breach is inevitable, so it focuses purely on containment. And the way it seals those bulkheads is through cryptographic identity.
Cryptographic identity.
Under the SPIFE framework, every single workload, every app, every sensor is issued an SVID, a speed verifiable identity document.
It's like a cryptographic, highly secure digital passport.
Yes, exactly like a passport. And every time one system wants to talk to another, it has to present its passport.
Okay, so let's go back to our hacker.
Right. Your hacker compromises the infotainment unit. They try to send a command across the network saying, slam on the brakes.
Okay.
The command reaches the Zone 1 control unit. Zone 1 acts like a border guard. It looks at the command and says, okay, show me your passport. Do you have cryptographic authorization to request a braking event?
And because the infotainment system is only authorized to manage audio and climate, its passport doesn't have the necessary cryptographic keys for braking.
Exactly. Zone 1 instantly rejects the command, drops the packet entirely, and alerts the VSOC that an unauthorized lateral movement attempt just occurred.
That's incredible.
The hacker is completely neutralized, trapped inside the radio, while the car just continues safely down the highway.
Man, it really is a masterclass in defensive engineering. We've rebuilt the physical nervous system with the zonal architecture. We've tamed the probabilistic AI with ISOPACE 8800 and that mathematical Mahalanobis safety cage.
Right.
We've launched out the external hackers with zero-trust submarine bulkheads. The car is structurally sound, legally safe, and secure. But now we face a totally different physics problem. How do developers actually squeeze performance and range out of these vehicles?
Yeah, now you have to make the car actually good at being a car.
Right.
You're touching on the fundamental paradox of the modern electric vehicle here. Efficiency requires intelligence, but intelligence requires energy.
Explain that paradox. How do those fight each other?
Well, to get the absolute maximum range out of a battery and to perfectly balance the thermal load of the electric motors so they don't overheat, you need incredibly advanced, highly complex neural networks constantly predicting thermal dynamics and adjusting power delivery literally millisecond by millisecond.
So you just put a smart AI in the car to manage the battery. Problem solved.
You can't. That's what they call the ECU black box compute limit.
Why can't you?
Massive, brilliant AI models require massive, power-hungry computer chips to run. If you put a server rack in the trunk of your EV to calculate perfect energy efficiency, the server rack itself will drain the battery faster than the efficiency gains can save it.
Right. It defeats the whole purpose.
Exactly. The edge compute power inside the car is strictly limited by thermal constraints and energy draw.
So you need the intelligence of a supercomputer, but you only have the power budget of, like, a smartphone. How did this symposium solve this?
With a really ingenious two-step pipeline using PGNNs.
VGMNs.
Physically guided neural networks, they basically separated the learning from the executing.
Okay, walk me through the first step, the learning phase.
Step 1 happens off-board in massive climate-controlled cloud server farms. Automakers train a massive high-dimensional PGNN. They feed it decades of raw physics data, thermodynamic equations, and battery chemistry models.
So it essentially becomes a super genius about the physical limits of the car. It understands exactly how the battery degrades at varying temperatures and power draw.
Yes, it can predict perfectly how the car will behave under any stress. But again, this PGNN is way, way too big and complex to ever fit into the car's limited edge ECU.
Right, the server rack problem.
So step 2 is this incredible mathematical magic trick. They use an AI extraction and reverse calibration dimensional reduction algorithm.
Okay, that's a very dense string of words. Dimensional reduction algorithm. Break that down for me. What does it actually do?
Imagine the massive PGNN understands the car's physics across 50 different dimensions or variables: temperature, humidity, voltage, tire pressure, driver history, you name it.
Okay, 50 variables.
The algorithm crushes that 50-dimensional complexity down into its most basic, essential correlations. It extracts the final answers from the AI without keeping the massive logic needed to reach those answers.
It distills it.
It distills it down into an explicit lookup table, an LUT.
What does a lookup table look like in practice? Is it just code?
It is basically a massive multi-dimensional spreadsheet. Instead of the car's ECU running complex calculus equations in real time to figure out how much power to send to the motor, it just checks the sensors, looks at the spreadsheet, and finds the pre-calculated answer.
Ah, okay. I actually have an analogy for this.
Let's hear it.
It's like a university physics student cramming for an insanely complex final exam. They spend a week in the massive university library, reading dozens of heavy textbooks, calculating complex formulas on massive chalkboards.
Which is the cloud training.
Right, that is the cloud training.
Yeah.
But for the actual exam inside the testing room, they aren't allowed to bring all those books in. They only get to bring one tiny, highly optimized index card. A cheat sheet.
A cheat sheet, exactly.
The lookup table is the cheat sheet. It contains all the brilliant answers distilled down with absolutely none of the bulk.
That is precisely what they're doing. The heavy, energy-draining calculation is done entirely offline. The car only carries the lightweight insights, and the results of this dimensional reduction are staggering.
Tell me.
The symposium research highlights a specific data point from real-world testing. This method results in a 17% increase in predictive accuracy for real-time hierarchical predictive control.
A 17% increase in accuracy. What does that actually mean for the driver on the road?
It means the car is 17% better at guessing the exact perfect amount of electricity to route to the motors and cooling systems based on the road ahead.
Which translates to what?
Well, in the automotive world, a 1% efficiency gain is a massive victory. 17% translates to significantly more range on a single charge. It means less battery degradation over the life of the vehicle and way better thermal management.
That's huge.
And they achieved it purely through smarter software extraction, without adding a single extra piece of silicon to the onboard compute limits.
That is the definition of doing more with less. But, you know, hearing you describe these PGNNs, the dimensional reduction algorithms, the microsegmented zero-trust bulkheads, it brings up a very practical question for me.
Sure, what's that?
Who is actually building this?
Ah.
Because the interconnected complexity here feels like it has vastly surpassed the limits of a human brain. Like, No team of engineers can sit in a room and manually type out the code for millions of variables across 4 SDV zones while perfectly balancing thermal physics. It's just too much.
You're absolutely right. Human engineers cannot code this fast enough, nor can they hold that much multidimensional complexity in their heads at once. The creation process itself has reached a tipping point.
Which brings us to the next major pillar of this symposium. AI building AI, or what they call agentic AI engineering.
We are fundamentally re-engineering the act of engineering itself.
The sources outline an agentic AI maturity model, kind of mapping how AI takes over the development process. Where are we starting, and what is the end game here?
It's a 5-level progression. Level 1 is where a lot of software developers are right now, actually. Copilots.
Copilot.
Yeah, these are AI tools that help a human write code faster. It's essentially advanced autocomplete. The human is fully in control. The AI just saves them keystrokes.
Okay, so helpful but not revolutionary.
Right. But level 2 introduces task agents. These are AI agents that can autonomously execute single-domain tasks.
Like what?
For example, an engineer might ask the AI to run a massive vulnerability check on a specific ECU software. The AI goes off, runs the tests, and reports back.
Still requires human direction and hand-holding, though.
It does. But level 3 is where the disruption really begins. Multi-agent workflows. At this stage, human intervention drops significantly. Different specialized AI agents begin handing off work to each other asynchronously.
Give me an example of an AI workflow.
Imagine an AI requirements agent analyzes consumer data and writes the technical specifications for a new motor.
Okay.
It then autonomously hands that spec sheet over to a coding agent, which writes the underlying RTL code, the register transfer level logic that bridges software and hardware.
Just writes it itself.
Yeah. And then the coding agent hands its draft to an AI testing agent, which bombards it with virtual simulations. They iterate and refine the code entirely amongst themselves before a human ever even looks at it.
So the AIs are literally having team meetings in the background. What does level 4 look like?
The cognitive layer. This is where AI begins resolving complex, contradictory multiphysics conflicts.
Contradictory physics.
Designing a car is all about compromise. If you make the car more aerodynamic, you restrict airflow, which ruins the thermal cooling of the battery.
Oh, right. You fix one thing, you break another.
Exactly. Usually, aerodynamics engineers and thermal engineers spend months arguing in conference rooms to find a compromise. At level 4, the cognitive AI dynamically balances these competing constraints autonomously, finding the mathematically perfect middle ground in minutes.
Which leads us to the ultimate goal, level 5.
Level 5 is autonomous pathfinding, architecture derivation based entirely on boundary KPIs.
KPI meaning key performance indicator, like cost, weight, range.
So you just feed the AI the constraints.
Exactly. A human executive inputs the boundaries. I want an electric motor that costs less than $500 to manufacture, fits into a volume of 10 liters, and achieves 95% energy efficiency. Go.
And the AI just invents it.
It autonomously invents the architecture to meet those goals.
But the symposium sources don't just talk about this theoretically, right? They highlight a concrete, real-world example of this pathfinding. Yes, using a tool developed by T. Graz, the OP tool optimization of electric drives. This isn't science fiction, it is operational right now.
How does it work?
The OP tool uses evolutionary AI algorithms. Instead of a human engineer drawing a single CAD model and testing it, the OP tool evaluates millions of radically different design variants in 24 hours.
Millions.
It rapidly mutates the designs, crossbreeding the most successful ones, until it maps out what is known as the Pareto front.
The Pareto front. I want to make sure the listener understands this because it sounds crucial. What exactly is the AI mapping there?
Imagine a 3D graph. The x-axis is hardware manufacturing cost. The y-axis is package volume, so how big the motor is. The z-axis is energy efficiency.
Okay, I see the graph.
As an automaker, you want the absolute lowest cost, the smallest volume, and the highest efficiency.
But the laws of physics and economics dictate you can't have all three perfectly. Yeah. Like, if you want high efficiency in a tiny package, you have to use incredibly expensive rare earth magnets, so the cost just skyrockets.
Exactly. The Pareto front is the curve on that graph that represents the absolute mathematical limit of the best possible compromises. It is the edge of what is physically possible.
Oh, I see.
Any design behind the curve is suboptimal. Any design past the curve violates the laws of physics. The AI runs millions of simulations to find this exact curve.
And it doesn't just hand the engineers a graph, right?
No, that is the magic of level 5. The OPIA tool outputs fully validated 3D CAD models directly from that optimal design envelope. It hands the human manufacturing team a completely finished, ready-to-build schematic for a motor that it invented overnight.
Okay, I have to step in here and ask the obvious, very uncomfortable question.
I think I know what's coming.
If an AI can pathfind multi-physics conflicts, argue with itself over thermal dynamics, evaluate millions of design mutations, and churn out a perfectly validated 3D CAD model in 24 hours,
Yeah.
what happens to the human engineer? Are we looking at a near future where the next generation of cars is entirely conceptualized, engineered, and designed by autonomous machines, with humans just, watching from the sidelines?
It is a profound shift, but the experts at Vienna frame this not as replacing the human, but as fundamentally elevating their role. The AI breaks what they call the human compute bottleneck.
Meaning, we're just too slow.
Humans are incredibly slow at manual calculation. We spend months drawing CAD lines or running simulations on dead-end designs.
We get bogged down in the manual labor of engineering.
Exactly. Agentic AI removes that manual labor. Human engineers will shift from being draftsmen to being strategic directors. They will set the boundary KPIs. They will define the safety constraints of the deterministic cage. They will focus on the user experience and the high-level architecture.
So the AI simply does the heavy lifting of exploring the million dead-end design paths so the human doesn't have to.
Right, so the human becomes the conductor, and the AI is the orchestra playing the instruments.
Okay, that is a comforting thought. But it leads me to one massive, glaring physical reality.
Which is?
You can use agentic AI to simulate millions of motor variants in the cloud. You can mathematically validate the safety cages, but eventually, all that virtual code has to interact with physical reality. The electricity has to meet the axle.
It does.
How do you safely test these aggressive AI-designed software updates before you beam them via an OTA update to a customer's car sitting in their driveway?
You've hit the final, most dangerous bottleneck in the entire development cycle, bridging the virtual and the physical. Because traditional automotive testing methods are completely inadequate for 800-volt software-defined vehicles.
For decades, automakers used something called hill testing, right? Hardware in the loop. Why doesn't that work anymore?
Traditional hill was a low-voltage simulation. You would take a physical ECU, put it on a test bench, and plug it into a computer. The computer would run a simulation of the car, feeding the ECU fake low-voltage sensor data, and see how the ECU reacted.
That sounds safe.
It was safe, cheap, and really effective for 12-volt legacy cars.
But modern EVs don't run on 12 volts.
They run on high-voltage silicon carbide systems, pushing 800 volts and hundreds of amps. And here is the brutal reality of physics. When you push that much extreme power through an electrical system, it behaves violently.
Violently.
Yes. It creates massive electromagnetic interference, or EMI. It creates brutal thermal spikes. It creates high-frequency electrical resonances.
Noise. Extreme physical noise that a clean computer simulation just can't replicate.
Exactly. You could have a piece of software that runs flawlessly on a 12-volt hill simulator in the lab, but the moment you install that software in a real car, the sheer electromagnetic noise of an 800-volt inverter switching on causes the silicon to glitch, and the software totally crashes.
So you have to test it on physical hardware with real high voltage.
You do.
But how do you do that continuously without putting a test driver in physical danger every single time you update the code?
The symposium detailed a fascinating solution developed by AVL. They call it the copper car. It is the ultimate physical reality check.
What is a copper car?
It is a physical level regression testing rig. Imagine taking the entire electrical skeleton of a car, the high voltage cables, the real physical e-axle, the inverters, the grounding planes, and laying it all out flat on a massive lab bench.
Just the guts of the car.
Just the guts. And it pumps real, lethal 800-volt electricity through real copper veins.
Wait, if they're pushing these systems to their breaking point 247 with massive software stress tests, doesn't that put the battery under immense strain? I mean, I've seen videos of EV battery thermal runaway. They explode like Roman candles.
They really do.
It takes thousands of gallons of water to put them out. How do they not burn down the lab using this rig?
Because the copper car is essentially a zombie car.
A zombie car.
It has real high-voltage blood pumping through its veins, but fake organs. They do not use a real chemical battery. They use highly advanced dummy loads.
Dummy loads.
Hardware that absorbs and dissipates electrical power without relying on volatile chemistry. By removing the actual lithium-ion battery, they completely remove the chemical and explosive hazards.
Well, that's smart.
Right. This allows the agile software pipeline to run brutal, destructive high-voltage tests continuously, safely, inside a lab.
But wait, if the software is testing against a dummy load, how does the AI properly validate its thermal management?
What do you mean?
A dummy load doesn't react like a lithium-ion battery. A real battery's resistance changes wildly based on its temperature, its state of charge, how old it is.
Yeah.
If you test on a static dummy load, aren't you getting fake results?
That is the absolute genius of the system. The dummy loads are not static, they are dynamic, and they are controlled by the closed-loop digital twin ecosystem.
Okay.
The dummy load is continuously commanded to mimic the exact behavior of a real battery, and the intelligence telling the dummy load how to behave is a PINA.
A PNN, physics-informed neural network. We brushed past this earlier, but we need to dive deep into how this actually works. How does a PNN differ from the normal AI we've been talking about?
So traditional AI, like a large language model or an image recognizer, learns purely from data. You feed it 1 million pictures of a cat, it learns what a cat looks like.
Right.
But if you ask it to predict the thermal flow of coolant through a battery plate, and you haven't given it exact data for that specific temperature and flow rate, it guesses wildly. It doesn't actually understand the physics, it just mimics the data.
Just pattern matching.
Exactly. So how does a PIN understand physics? By embedding the actual immutable laws of physics directly into its mathematical DNA, specifically into its loss function.
Okay, let's unpack the math simply. The loss function is the mechanism an AI uses during training to figure out how wrong its guess was, right? It tries to minimize the loss.
Yes. In a normal AI, the equation is simple. Loss equals the difference between the AI's prediction and the real-world data. It's just a data error penalty.
Yeah.
But for a PAN, the equation is expanded. Loss equals lost data plus lost PDE plus loss boundary.
What are PDE and boundary?
PDE stands for partial differential equation.
Yeah.
These are the mathematical equations that describe the physical universe.
Like what?
For example, the Navier-Stokes equations describe exactly how fluid moves. Heat transfer equations describe how temperature spreads. Loss PDE is a soft penalty applied to the AI if its prediction violates these mathematical laws.
Wow. So even if the AI's guess matches the data perfectly, if the way it arrived at that guess broke the laws of thermodynamics, the loss function penalizes it.
Exactly. It gets punished for breaking the laws of physics. And loss boundary penalizes it if it violates the physical limits of the container, like guessing that fluid flows through a solid wall.
Because it knows there's a wall there.
Right. Because the AI is heavily penalized for breaking the laws of physics during training, it doesn't have to brute force learn how heat works from massive data sets. The Navier-Stokes equations are literally baked into its intuition.
That sounds incredibly complex to set up.
Yeah.
What is the practical advantage of forcing the AI to learn differential equations? Why not just use traditional computer physics simulations like CFD?
Because traditional simulations like CFD, computational fluid dynamics, or FEM, finite element method, are incredibly slow.
How slow?
They require a supercomputer to chop a 3D model into millions of tiny mathematical grids and calculate the physics at every single intersection step by step. It takes hours or days to simulate a few seconds of thermal dynamics.
And the copper car needs those calculations instantly.
Yes. Because the PN has already absorbed the physics into its neural weights, it completely sidesteps the computational drag of finite element analysis. It achieves millisecond edge inference. It can predict complex thermal dynamics instantly.
So let's bring this all together. You have a PNN running a digital twin of a battery. The PNN is digesting real-world continuous telemetry from cars already driving on the road via the data flywheel we talked about earlier.
Yes.
It uses that data and its baked-in physics knowledge to command the dummy loads on the copper car rig in real time.
Exactly. The dummy load physically acts out the PNN's predictions. If the experimental software demands maximum acceleration, the PNN instantly calculates how a real 3-year-old lithium-ion battery at 40 degrees Fahrenheit would experience voltage sag and thermal buildup.
It knows exactly how the chemistry would react.
It knows. And it commands the dummy load to dynamically adjust its electrical resistance to mimic that exact physical state.
So the experimental software thinks it is interacting with a volatile, degrading battery. The high voltage is real. The electromagnetic interference crashing through the silicon is real.
That's very real.
But the physical danger of an explosion is completely zero.
Precisely. The copper car allows automakers to subject agentic AI-designed software to brutal 800-volt physical reality checks. They can validate complex over-the-air updates mathematically against ode detectors and physically against EMI and thermal spikes entirely in the lab.
And once it survives the copper car, only then is it beamed to the customer's driveway.
Only then.
This entire deep dive has been a staggering realization for me. I mean, when we started, we talked about the comfort of mechanical certainty, the brake pedal pushing the caliper.
The simple days.
Right. What the 47th Vienna Motor Symposium has laid bare is that the era of mechanical simplicity is just dead.
It is entirely gone. The modern vehicle is a decentralized, AI-driven data ecosystem.
It really is.
It is an entity that processes the world through edge compute NPUs, filters decisions through mathematically rigorous deterministic safety cages, and evolves its own architecture using agentic AI and cloud-based physics twins.
So, to our listener,
Yeah.
the next time you get an over-the-air update in your car and your dashboard screen flickers for a brief moment, realize the sheer magnitude of what just happened.
It's easy to take for granted.
It is. That tiny packet of code likely went through an autonomous multi-agent AI workflow. It was mathematically validated against a Mahalanobis distance OD detector. It passed through zero-trust cryptographic submarine bulkheads. And it was mercilessly stress-tested against the violent 800-volt reality of a copper car rig before it ever reached your driveway.
It really is an unseen symphony of digital brilliance and physical engineering. The car is no longer just a product you drive off a lot.
It isn't. And I want to leave you with this final provocative thought to ponder. If our vehicles are constantly connected to a data flywheel, if they are continually updating their knowledge via the cloud, and if they are governed by agentic AI that autonomously alters their fundamental logic based on every new mile driven,
Yeah.
at what point does a car stop being a static mechanical product that you own and start being an evolving autonomous entity that you just happen to sit inside?
It's a brave new world on the highway, that's for sure.
It certainly is. Thanks for joining us on this deep dive. Keep questioning, keep exploring the hidden systems around you, and we'll see you next time.
Until next time.
If I asked you right now what causes, the most particulate pollution in a modern congested city, you would probably point to the exhaust pipe of an old heavy-duty diesel delivery truck rumbling down the street.
Yeah, I mean, most people would.
Right.
Yeah.
And honestly, for a long time, you would have been absolutely right to point at that truck. But if we look at the data coming out today, you'd actually be wrong.
Completely wrong, yeah.
Because the real culprit might just be that sleek, heavy, supposedly, zero emissions electric vehicle that's silently braking at a stoplight right next to you.
Which is a reality that just completely upends the traditional environmental narrative we've been sold. I mean, we've spent so much time looking at the back of the car, right? At the
The
tailpipe.
plastic smog source.
Exactly. And because of that, we completely ignored the massive heavy wheels carrying up the asphalt at the front of the car. It's what engineers are now calling the BEV paradox, the battery electric vehicle paradox.
And that paradox is exactly why we're here today. Welcome to this deep dive. If you're listening to this on your commute, or maybe while you're wrenching on a car in your garage, everything you thought you knew about automotive emissions just became entirely obsolete.
It really did.
We are going straight to the source today, decoding this massive paradigm shift that was recently laid out, in excruciating detail at the 2026 International Vienna Motor Symposium.
Yeah, and it is genuinely a total rewrite of the rules of the road. What the symposium make incredibly clear is that the global automotive industry is undergoing this forced, violent transition.
Little paradigm shift.
Right. We are officially abandoning the era of hardware exhaust and entering the era of the digital ecosystem.
I was trying to find a good way to visualize this shift while I was prepping, and I kept coming back to the idea of like a medical diagnosis.
Oh, okay. Walk me through that.
So in the past, dealing with car emissions was like getting an X-ray for a broken bone. You put the car in a testing facility, you ran it on a treadmill, dynamometer, and the regulators essentially just took a snapshot.
Right. A single moment in time.
Exactly. They looked at the X-ray, saw the exhaust was clean on that specific day, stamped a piece of paper, and sent the car out into the world. It was binary. pass or fail, clean or dirty.
And that static mindset was, well, it was a comfortable illusion for a long time. The engineering boundary was strictly the exhaust pipe, and the temporal boundary was basically day one of the car's life.
Right, it's rolling off a lot.
Regulators essentially said, we trust that this car will behave exactly like this for the next decade. But the new regulatory framework coming out of Europe, known as Euro 7, it completely abolishes that trust. It just shatters the X-ray machine.
Because Euro 7 mandates something entirely unprecedented,
Yeah.
right? It's this continuous real-world digital monitoring net.
Yep.
The car is no longer just tested once at the factory. It is perpetually testing itself, like every single second the ignition is on for 10 solid years or 200,000 kilometers.
It's relentless. It has to constantly mathematically prove to the government that it is in environmental compliance.
The overarching narrative from those Vienna engineers is that compliance is no longer just this mechanical hardware issue that a mechanic can fix with a wrench.
No, not at all. It is now fundamentally a data governance issue. I mean, we're talking about artificial intelligence hallucinating chemical
Well,
reactions.
it sounds like sci-fi.
Right. Mechatronic suspensions, fighting microplastics, and military-grade cryptography, securing the vehicle's very right to turn its engine on.
So we have a really fascinating roadmap ahead of us today. We're going to guide you through this technological revolution step by step.
It's a lot to cover.
It is. But we'll break it down. We'll start by looking at how cars are transforming into their own perpetual emissions inspectors, right down to the AI algorithms replacing physical sensors. Then, we are going to circle back to that electric vehicle at the stoplight and uncover the shocking mechanics behind those new urban pollutants.
And beyond the physical pollution, we really have to look at the digital trust. We'll explore how your car's data is secured so you literally can't cheat the system.
Yeah, the cybersecurity aspect is wild.
It is. And finally, we will zoom all the way out to look at the massive, global, cradle-to-grave carbon footprint of the cars of tomorrow.
Okay, to really understand this new era, we have to start inside the brain of the internal combustion engine. We're moving away from that static day one dyno testing to dynamic lifetime telemetry. And the acronym you see plastered all over these symposium papers is the shift from OBD to OBM.
Yes, from onboard diagnostics to onboard monitoring. And to grasp the sheer magnitude of this shift, you have to realize how incredibly passive the old OBD system was.
Oh, totally. If you have a car built any time in the last 20 years, you have OBD.
Right, but it operates on a very primitive threshold logic.
It's essentially just looking for broken parts, right? It asks, is the oxygen sensor sending a voltage? Yes.
Yeah.
Is the catalytic converter operating above a minimum efficiency threshold? Yes.
Exactly. And if a component catastrophically fails, or, a wire gets chewed by a rat, your check engine light comes on.
It's just a dummy light.
Precisely. It is a binary health check. It tells you something is broken, but it fundamentally cannot tell you how much pollution is currently escaping from your tailpipe into the atmosphere.
Right.
Active OBM, which is the bleeding heart center of the Euro 7 regulation, completely changes that paradigm. It shifts from simple diagnostics to hard, real-time quantification.
And the sources detail that the OBM system must generate distance-specific emission logs. We're talking about the car's computer literally calculating the exact grams of pollutants emitted per kilometer, 24 hours a day, 7 days a week.
Yeah.
That is an incredibly granular level of surveillance.
And it is not just looking at the classic, well-known pollutants like standard carbon dioxide or carbon monoxide either.
Right, the stuff we're used to worrying about.
The expanded regulatory targets now mandate the continuous high-fidelity monitoring of nitrogen oxides, which we call NOx, particulate matter, or PM, and a very tricky chemical byproduct known as critical ammonia slip, or NH3.
Okay, the inclusion of ammonia is wild to me because it really highlights the cascading complexities of trying to clean up an engine. I was reading up on this, and in modern diesel and advanced hybrid engines, they use a system called selective catalytic reduction, right? The SCR.
Yes, the SCR system.
And to make the SCR work, you have to inject a urea solution, most people probably know it by the brand name AdBlue, directly into the hot exhaust stream.
That is the exact chemical mechanism. When that urea solution hits the extreme heat of the exhaust, it undergoes thermal decomposition and hydrolysis, and it turns into ammonia. That ammonia then reacts with the harmful NOx inside the catalytic converter, and if everything goes perfectly, it breaks the NOx down into harmless nitrogen gas and water vapor.
So the ammonia is basically the chemical weapon being deployed to assassinate the NOx before it leaves the car.
That is a highly accurate way to visualize it, yeah.
Yeah.
But chemistry in a moving vehicle is rarely perfect.
I imagine not.
If the engine control unit injects even a tiny bit too much urea, or if you are driving in freezing weather and the catalytic converter hasn't reached its optimal operating temperature, that chemical assassination doesn't happen.
Because it's too cold for the reaction.
Exactly. The ammonia doesn't react. It just slips right through the system and out the tailpipe into the atmosphere.
Hence the term ammonia slip. And from an environmental standpoint, ammonia is a severe urban pollutant. It contributes to smog and respiratory issues.
Right. So Euro 7 regulators looked at this and said, you must continuously monitor the NOx coming out, but you must also continuously monitor the ammonia slip you are creating while trying to fix the NOx.
Oh, man.
It is a massive regulatory tightening of the chemical loop. You can't just fix one problem by creating another invisible problem.
But the car isn't just silently gathering this data for, like, an annual report card. It's not just uploading a polite spreadsheet to the cloud once a month. The sources outline a mechanism that genuinely shocked me when I first read it. They call it the inducement threat.
Ah, yes. The inducement mechanisms are where the regulatory teeth of Euro 7 really show. This is where data governance violently intersects with physical vehicle ownership.
Okay, picture this. You're wearing a smart health tracker on your wrist. Normally, a health tracker just vibrates and sends a notification to your phone saying, hey, your cholesterol's looking a bit high this month. Maybe cut back on the red meat.
Right, a gentle nudge.
But under the logic of Euro 7, the inducement threat means if the OBM system detects that the vehicle's emissions are consistently over 2.5 times the legal limit, it doesn't just turn on a passive check engine light. It legally mandates a severe performance reduction, or it will outright prevent the engine from igniting.
It just shuts you down.
It is quite literally like having a health tracker that physically locks your refrigerator door until you agree to eat a salad.
It is a profound shift in control. The vehicle will physically intervene in your ability to use it. If the digital ledger determines that the physical emissions are out of bounds, the software ruthlessly curtails the hardware.
So what does that actually look like for the driver?
Well, you might find your car artificially limited to, say, 20 kilometers an hour, barely able to limp to a mechanic. Or, if the violation is severe enough, the ignition circuit simply refuses to close. The vehicle refuses to operate outside of its environmental contract.
Okay, I have to push back here because from a practical engineering standpoint, this sounds like an absolute nightmare waiting to happen.
How so?
We are talking about placing highly sensitive physical sensors deep inside an exhaust pipe. That is an incredibly hostile environment.
It's brutal, yeah.
You are dealing with extreme heat cycles, freezing cold, intense vibration from the road, mud, soot, and highly corrosive chemical gases. How can any physical sensor survive 200,000 kilometers of that abuse and still be perfectly accurate enough to justify turning off someone's engine?
You've hit on the exact massive bottleneck the engineering community faced over the last few years. It was a primary point of friction and debate at the Vienna Motor Symposium.
I can imagine.
The harsh reality of physics is that physical sensors degrade. They drift over time. Over 200,000 kilometers, a physical ammonia sensor or a NUX sensor loses its calibration. It gets coated in microscopic layers of soot and degraded by thermal shock.
And if that sensor loses its calibration, it might start reading high. It might falsely trigger that inducement threat. You could have a mother with her kids stranded on the side of a freezing highway, not because her engine is failing, but because a tiny chemical sensor in the exhaust pipe got dirty and falsely told the computer to shut the car down.
Which is an unacceptable safety risk and a massive liability for automakers. They just can't have that happen. Furthermore, physical sensors face a severe inherent limitation called cross-sensitivity.
Cross-sensitivity.
Yeah. The chemical signatures of NH3 and NOx, when analyzed by standard automotive sensors, are incredibly similar. A physical NOx sensor often gets confused by the presence of ammonia.
Oh, I see.
It reads the ammonia and reports it to the computer as NOx. They are virtually indistinguishable to the raw hardware.
So the hardware literally cannot do the job that the Euro 7 law requires. The law demands perfect segregation of NOx and ammonia. And the physical sensor is basically saying, I just see a bunch of nitrogen-based gas. I can't tell the difference.
Exactly.
What is the solution if the hardware is fundamentally flawed?
The solution is to transcend the physical hardware entirely. The automotive industry is rapidly pivoting to AI-driven virtual sensing.
Virtual sense. Wait, you mean they are essentially building a sensor out of software?
In a manner of speaking, yes. Instead of relying purely on a fragile, highly specialized sensor deep in the exhaust to give the final absolute reading, the vehicle utilizes a powerful edge AI processing node.
Okay.
This computer node takes in a massive stream of robust, simple data from highly durable sensors that don't easily degrade.
What kind of data are we talking about here?
Things like absolute engine block temperature, exhaust manifold flow rate, mass airflow intake, fuel injection timing, and those raw, overlapping, noisy knockoffs and NH3 sums from the basic exhaust sensors.
So it takes a barrage of crude, heavily reliable data rather than trying to get one perfect, fragile reading from a delicate instrument.
Yes, exactly. And then it feeds that crude data stream into advanced mathematical models. The symposium papers specifically highlight the use of extended Kalman filters, or EKF, alongside a mixture of experts, or MOE reaction kinetics models.
Okay, I saw those terms. I know Kalman filters are used in aerospace for navigation, right?
They are, yeah.
To my understanding, a Kalman filter isn't just smoothing out a line on a graph. It's actually a predictive algorithm. It takes a series of measurements over time that contain a lot of statistical noise and inaccuracies, and it produces an estimate of what the true value is, which tends to be much more accurate than any single raw measurement.
That is an excellent summary. And the extended version of the Kalman filter is deployed when the system dynamics are highly nonlinear.
Because engine chemistry is nonlinear.
Violently nonlinear. The rate of a chemical reaction changes exponentially based on tiny fluctuations in temperature and pressure. The extended Kalman filter basically runs a continuous mathematical simulation of the exhaust pipe, predicting what the emissions should be at any given microsecond, and comparing its prediction to the noisy sensor data to find the hidden truth.
Wow. It's like trying to predict the exact path of a single drop of water in a boiling pot, and comparing your prediction to the blurry video of the pot to figure out where the drop actually is.
That's a great way to think about it.
But what about this mixture of experts model?
The mixture of experts is a fascinating machine learning architecture. In complex environments, having one single massive neural network try to understand every possible scenario usually results in a model that is mediocre at everything.
A jack of all trades, master of none situation.
Exactly. So instead, you train multiple smaller, highly specialized expert neural networks.
Okay, give me an example of how that works in a car.
Sure. One expert network might be trained exclusively on the thermodynamics of a cold start at sub-zero temperatures in a high-altitude environment. It knows exactly how the fuel condenses on the cold cylinder walls.
Very specific.
Right. Another expert network is trained exclusively on high-speed, constant-load highway cruising on a hot summer day. A master gating network sits above them, analyzing the driver's current behavior, and it decides which expert or which combination of experts to listen to at any given millisecond.
So these AI models take the noisy, overlapping signals where the physical hardware is throwing its hands up and saying, I don't know if this is NOx or ammonia, and they mathematically decouple them using predictive chemistry.
They decouple them in under 1.5 milliseconds. They extract a pure high-fidelity NOx data stream and a pure NH3 data stream purely through computational inference.
That is incredible.
They bypass the physical degradation of the sensor by using software to calculate the absolute truth of the chemical reaction happening inside the pipe. The AI is essentially hallucinating the perfect sensor.
That is just wild. The car is running a hyper-accurate, real-time simulation of its own chemistry just to figure out what it is emitting. And the sources note that this AI virtual sensing isn't just restricted to exhaust gases. It is also being heavily deployed to measure battery state of health, or SOH, in electric vehicles.
And this is a critical bridge to the electric vehicle side of the Euro 7 mandate. Regulators don't just care about emissions, they need to know the true legal degradation of the traction battery over its life.
Right, because if the battery fails, the car is junk.
If a battery degrades too fast, the environmental math of the EV completely falls apart. But traditionally, to get a highly accurate state of health reading, you have to subject the battery to a rigorous test.
Like what?
You need to fully charge it to 100%, let it settle, and then fully discharge it to absolute zero at a constant controlled rate.
Which is something a normal driver almost never does. I mean, you plug in at 40%, you unplug at 80%. Doing a full 0 to 100 deep cycle is actually pretty bad for the longevity of lithium-ion chemistry.
Right, you can't force consumers to regularly ruin their batteries just to measure them. But by using these same edge AI capabilities, the vehicle's computer monitors microscopic fluctuations in voltage, current, and cell temperature during normal, partial daily driving.
It's just watching in the background.
Yes. As you accelerate to pass a truck or as you brake to a stop, the AI watches how the battery's internal resistance reacts to those microloads.
It's looking for the subtle signs of aging and how the battery breathes energy in and out.
Exactly. And by applying complex algorithms to those microfluctuations, the data shows they can achieve a root mean square error, which is a statistical measure of accuracy of less than 0.73% for predicting the battery's total health.
Under 1% error. Wow.
And they do this without ever requiring the consumer to perform a full charge or discharge cycle.
So the vehicle has truly become a rolling supercomputer. It is analyzing its own physical degradation through artificial intelligence, decoupling chemistry in milliseconds, all to prove to the government ledger that it's allowed to keep driving.
It has, and this incredible triumph of software engineering leads us perfectly into the massive contradiction at the heart of modern mobility.
The BEV paradox.
Right. Because if we can perfectly monitor and eliminate tailpipe emissions using AI, and we inevitably transition the global fleet toward pure battery electric vehicles, BEVs, it seems like we've solved the problem, right? No tailpipe, no emissions, problem solved.
Right. The logical leap is so simple. If the tailpipe is the source of the poison, just get rid of the tailpipe. But that brings us right back to the electric vehicle sitting at the stoplight. We have to dive into the most counterintuitive and, frankly, the most frustrating part of the entire Euro 7 framework: non-exhaust emissions.
This is where the pristine, idealized narrative of the zero-emission vehicle violently collides with physical reality and material science. We are facing the BEV paradox head-on.
I really want to focus on this concept because it completely flips conventional wisdom on its head. So battery electric vehicles are undeniably fantastic for localized urban air quality when it comes to gases like NOx and carbon monoxide.
Absolutely.
But BEVs have two defining physical characteristics. One, they are significantly heavier than gas cars due to those massive, dense lithium-ion battery packs. And two, their electric motors deliver instantaneous, massive torque directly to the wheels the millisecond you touch the pedal.
And those two physical traits heavily amplify what regulators call non-exhaust emissions, or NEE. Specifically, we are talking about microscopic brake dust and tire wear particles.
Unseen pollution.
Yeah. And the data presented to the engineering community at the symposium is staggering. Due to the success of cleaning up modern combustion engines and the rise of heavy EVs, these non-exhaust physical outputs now actually eclipse tailpipe gas outputs in modern urban environments.
That is hard to believe, but the numbers don't lie.
The primary source of particulate matter, the PM10 and PM2.5 that gets inhaled deep into human lungs and causes severe cardiovascular issues, is no longer coming out of the back of the car. It is coming directly from the wheels.
Let's look at the specific new limits Euro 7 is imposing, because this really illustrates how seriously regulators are taking the paradox. Euro 7 mandates unprecedented, incredibly strict limits for brake particulate matter, specifically PM10, which are particles smaller than 10 micrometers.
Right.
The new limit for standard M1 class internal combustion vehicles is 7 milligrams per kilometer, but the limit for M1 class BEVs is clamped down to an astonishing 3 milligrams per kilometer.
Now, anyone looking at those numbers should immediately have a question.
I certainly did. Why on earth are the rules stricter for electric cars? Shouldn't it be fundamentally easier for an EV to produce less brake dust because of regenerative braking?
You would think so.
I mean, when you lift off the accelerator in a Tesla or a Mach-E, the electric motor reverses its polarity. It turns into a generator, magnetically slows the car down, and feeds that kinetic energy back into the battery. The physical, mechanical brake pads and rotors are barely even touched in daily city driving.
In theory, your logic is flawless. Less physical use equals less physical wear, which equals less dust.
Right.
But the reality of metallurgy intervenes and ruins the theory. Standard automotive brake rotors are made of cast iron. They're heavy, cheap, and excellent at dissipating heat. But if you don't use them frequently and they're constantly exposed to the elements, rain, snow, aggressive road salt, and ambient humidity, they rust.
Of course.
They rust severely and quickly.
I saw a term in the engineering papers translated as idle degradation.
Yes. So picture a BEV driving around a damp, salty city like Chicago for a week. The driver is using one-pedal driving, relying entirely on the magnetic regenerative braking.
So the physical brakes are just sitting there unused.
Exactly. During that week, a thick, abrasive layer of iron oxide rust builds up on the surface of the cast iron rotors. Then, suddenly, a pedestrian steps out into the crosswalk, or a car cuts them off. The driver instinctively slams their foot onto the brake pedal. The hydraulic system engages, and the physical brake pads clamp down violently on those rusted rotors.
And because that rust is brittle and abrasive, the pad just shreds it off.
It acts like a grinder. The brake pads violently scrape off all that accumulated rust in a fraction of a second. It creates a catastrophic transient emission spike.
Ow.
That single hard panic stop can release such a massive cloud of PM10 rust dust that it blows the vehicle completely past its 3 milligram per kilometer legal average limit for its entire regulatory test cycle.
That is just fascinating engineering irony. The very magnetic technology that prevents the brakes from being used is exactly what causes them to rust, which causes them to fail the physical emissions test.
It's a brutal catch-22.
So how do the engineers at the symposium plan to fix this? You can't just tell people not to brake in an emergency. The sources outline a whole suite of mechatronic and material solutions, ranging from chemistry to architecture.
Let's start with the hard material science. One of the premier solutions discussed for immediate deployment is called EHLA, or LMD. That stands for Extreme High-Speed Laser Cladding, or Laser Metal Deposition.
Laser cladding. That sounds incredibly expensive and honestly like something out of a sci-fi manufacturing plant.
It is a breathtaking piece of manufacturing technology. They take a standard, cheap cast iron brake rotor, spin it at high speeds, and use high-powered industrial lasers to melt a dual-layer, nickel-free powder directly onto the surface of the iron.
Melting powder with lasers onto iron.
Yes. This creates a tungsten carbide and titanium carbide hard coating.
So they aren't just painting it. They're essentially laser welding an impervious armor-plated shield onto the brake disc.
Exactly. This WCT2C coating is incredibly hard, highly resistant to wear, and most importantly, it is completely impervious to rust. Tests from major suppliers like Brembo show this coating reduces PM10 emissions by roughly 90%.
90%, that's massive.
It totally fundamentally eliminates the EV rotor rust problem. However, the obvious trade-off is the astronomical CapEx capital expenditure. Setting up automated production lines with high-power lasers and exotic titanium metal powders makes these brake rotors significantly more expensive than standard iron.
So laser cladding is probably going to be reserved for the luxury EVs, the Porsches, the high-end Mercedes models. But what about the mass market? You can't put titanium laser brakes on a $25,000 electric hatchback.
No, you can't. For the mass market, the engineering consensus points to FNC and Smart ONC. FNC stands for ferritic nitrocarburizing. It's a thermal diffusion method.
Okay, let's look at the mechanics of thermal diffusion.
Yeah.
Because this isn't a coating at all, right?
No, it is not an additive layer. Instead of laser melting a new layer on top, you take the finished iron brake rotors and place them into a massive, highly pressurized, high-temperature furnace filled with nitrogen and carbon gases.
Okay, a gas furnace.
The extreme heat excites the molecules and causes the nitrogen and carbon atoms to literally diffuse into the crystal lattice of the iron surface itself.
So it's more like forging steel into a Damascus blade? The carbon and nitrogen actually slip between the iron atoms, locking them in place so oxygen can't get in to react and cause rust.
That is a brilliant analogy, yes. You are altering the metallurgy of the outer skin of the rotor. After the diffusion, they undergo a controlled oxidation process. That's the Smart ONC part.
What does that do?
This creates a super hard, highly dense, dark oxide film that is integrated directly into the metal. It cannot flake off because it is the metal. It provides excellent rust prevention, cuts PM10 emissions by about 50%, and because you can process hundreds of rotors at a time in a single furnace, it is highly cost-effective for mass-market vehicles.
It's amazing how much effort is going into fixing a spinning disc of iron. But those are just the physical material fixes. I noticed the sources also heavily emphasize software solutions for the brakes, specifically a concept called regenerative blending.
This is where we return to the power of the digital ecosystem. Why spend millions retooling a factory to laser-clad brake rotors if you can just change the code in the car's computer to manage the rust differently?
That does sound cheaper.
Automotive engineers are developing highly dynamic fuzzy logic thresholds for the braking control units.
Fuzzy logic. That sounds imprecise. When I press the brake pedal at 70 miles an hour, fuzzy is the absolute last word I want associated with my car's computer.
I understand the apprehension, but in computer science, fuzzy logic doesn't mean inaccurate. It's actually a form of multi-valued logic. Instead of a rigid binary brakes on or brakes off command, fuzzy logic allows the computer to process infinite degrees of truth.
Oh, I see.
It takes in a massive array of real-time variables: vehicle speed, battery temperature, the current state of charge, the estimated friction coefficient of the road surface, and the exact millimeters of pedal pressure you are applying.
And what does it do with all that data?
It dynamically calculates, millisecond by millisecond, the absolute maximum amount of magnetic braking force it can assign to the electric motors without destabilizing the car's handling or overcharging the battery. It is constantly prioritizing the magnetic drag over the physical friction pads.
So it's squeezing every possible drop of deceleration out of the magnets and coils before it even thinks about letting the brake pads touch the rotors, basically guaranteeing the physical brakes are only used when absolutely mathematically necessary for safety.
Yes. It shifts the braking load almost entirely to the e-motors in 95% of driving scenarios. And the best part from an automaker's perspective:
That's it.
developing that software algorithm costs $0 in physical bill of materials, or BTOM. It doesn't require a new factory, it just requires a brilliant software update sent over the air.
But there was one physical solution presented at the symposium that really caught my eye, and it feels like the most extreme answer to the brake dust problem: the active enclosures. Specifically, the ZEDU1 concept developed by the German Aerospace Center.
The zero-emission drive unit. That is, without a doubt, the most radical architectural disruption discussed for the future of the wheel hub.
I was looking at the diagrams for this, and they literally put a vacuum cleaner on the brakes.
Essentially, yes. The engineers at the German Aerospace Center completely abandoned the traditional open-air disc brake design that has been standard for decades. Instead, they designed a fully enclosed multi-disc brake concept.
Completely sealed off.
Yes, the entire friction mechanism, the rotors, the pads, the calipers, is completely sealed inside an airtight housing integrated into the drivetrain. As the brakes operate and inevitably generate dust, an active vacuum filtration system literally sucks the air out of the enclosure, passes it through a high-efficiency particulate filter, and captures near 100% of the dust before it can ever reach the outside environment.
It's absolutely brilliant in its brute force logic. If you can't stop the dust from forming, trap it in a box.
Yeah.
But the sources note it causes high architectural disruption. You can't just bolt this onto a normal car.
No, not at all.
You have to completely redesign the wheel hub, the suspension geometry, the cooling pathways, everything just to fit this sealed vacuum box.
Which is why the ZDU1 is considered a long-term concept for the next decade, whereas laser cladding and fuzzy logic software blending are immediate deployments to meet the tight 2026 Euro 7 deadlines.
Okay, so that covers the brakes. We've armor plated them, we've vacuumed them, we've used fuzzy logic to ignore them. But what about the other half of the non-exhaust equation? The tires. The sources mention an entirely new metric called tire TRWP indexing. TRWP standing for tire road wear particles.
This is a massive global environmental blind spot that is finally being eliminated by regulators. Every single time a tire rolls, accelerates, or corners, it is experiencing friction.
And friction means wear.
And that friction causes the tire to shed microscopic particles. We are talking about microplastics, polymer resins, synthetic rubbers, and carbon black. This invisible dust blows into the air we breathe. It washes into our storm drains and rivers, and incredibly, atmospheric currents carry it thousands of miles away, where it settles on pristine mountain snowpacks.
That's horrifying.
Because the dust is dark, it absorbs solar radiation, actively accelerating glacial melting.
That is a staggering chain of events to wrap your head around. A commuter takes a corner a little too aggressively in London or New York, and a fraction of an ounce of their tire rubber ends up accelerating the melting of a glacier in the Alps.
It's the butterfly effect of automotive pollution.
And Euro 7 is finally cracking down on this. The regulations reference the UN GTR Common for Abrasion Index, or AICT, which mandates strict adherence to a 1.00 baseline wear limit by 2028, meaning all tires sold will have to meet a universal, standardized threshold of toughness and wear resistance. But again, the BEV paradox rears its head. This problem is severely amplified by electric vehicles because of the sheer weight of the batteries and the massive instant torque of the motors tearing at the rubber.
And just like with the brake rust, you cannot solve this problem purely with chemistry. You can't just tell tire manufacturers to make the tire rubber harder so it doesn't wear out.
Why not?
If you make the compound too hard, the tire loses its grip on the road. Braking distance is double, and the car becomes a lethal hazard in the rain. You have to maintain the soft, grippy chemistry, but solve the wear issue using advanced chassis dynamics.
This is where my mind was blown. How do you stop a soft rubber tire from wearing out? By changing the suspension of the car.
You have to eliminate a physical phenomenon that engineers call microslip. When a car drives, especially over uneven pavement or around a sweeping corner, the tire isn't perfectly flatly planted on the road surface.
Right, there are bumps and dips.
The car bounces slightly over imperfections, and the body tilts or rolls during a turn. Every single time the tire lifts slightly, lands, or tilts while under engine power, the rubber violently drags across the abrasive asphalt at a microscopic level. That microslip acts exactly like dragging sandpaper across the tread, shredding the polymer chains.
So the goal isn't to change the rubber, but to use the suspension to keep the tire perfectly flat, perfectly pressured, and perfectly aligned with the road surface at all times, no matter what the car is doing.
Precisely. And the Vienna Symposium highlighted two incredible active chassis control technologies that achieve this. The first is AMPC, Adaptive Model Predictive Control.
Okay, walk me through how an adaptive suspension uses predictive control to save the tires.
Traditional suspensions are reactive. They hit a bump, and then the shock absorber compresses. AMPC is proactive. It uses high-resolution forward-facing cameras and LiDAR sensors to read the exact topological roughness of the road surface ahead of the tires.
So it's looking at the road before the tire hits it.
Exactly. The active suspension anticipates the bump before the tire even reaches it and dynamically softens or stiffens the electromagnetic dampers in milliseconds. This smooths out the vertical dynamic loads and, according to the symposium data, reduces vertical tire displacement by 10.3%.
So it bounces less.
The tire bounces 10% less, therefore it experiences 10% less abrasive microslip when it lands.
It's essentially lifting the foot over the rock instead of stubbing the toe. And the second technology addresses cornering, ACTS, active camber, and toe control.
This one is an absolute marvel of mechatronics. When you take a hard turn in a heavy car, the laws of physics dictate that the body of the car rolls to the outside of the turn.
Right, you lean into the door.
This body roll physically lifts the inner edge of the outside tire off the ground and grinds the outer edge of the tire brutally into the pavement. That uneven pressure destroys the outer shoulder of the tire tread. ACTS uses powerful motorized robotics actuators built directly into the suspension arms to dynamically push and pull the wheel hub itself.
Wait, so as the body of the car rolls one way, the robotic suspension arms push the wheel the other way to compensate.
Exactly. It actively counteracts the body roll, forcefully pivoting the wheel to keep the flat tread perfectly parallel against the road. The telemetry data shows this active robotic system improves camber variation by 46% and toe variation by 93% during dynamic driving.
So by using advanced robotics and predictive cameras in the suspension, you ensure a perfectly flat contact patch. A flat contact patch eliminates the high-stress microslip, which in turn stops the severe microplastic shedding from the tire. It is a brilliant example of using mechatronics and software to solve what is fundamentally a chemical pollution problem.
And that perfectly summarizes the entire engineering philosophy of the next decade. Everything is an interconnected system. The software in the camera impacts the pollution of the tire.
Which brings us to a massive, looming question. We have established that these Euro 7 cars are now rolling digital fortresses. They're gathering massive amounts of AI-filtered data, they have virtual sensors decoupling invisible gases, they're using fuzzy logic to calculate brake dust, and they're using predictive models to track tire slip angles. The car knows exactly how much it is polluting, but here is the elephant in the room. If I'm the government, how do I actually trust any of this data?
That is the ultimate question of modern digital governance, because if the data can be manipulated, the entire Euro 7 framework collapses. We are moving away from the physical realm of chassis dynamics and entering the highly contested realm of cryptography and automotive cybersecurity.
Enter the Environmental Vehicle Passport, or the EVP. The symposium sources describe this as a digital twin, or the ultimate uncheatable environmental ledger for your specific car.
It is a cryptographic shadow that is born on the factory floor and follows the vehicle every single day until it goes to the scrapyard. Every single Euro 7 vehicle will be legally mandated to generate and continuously update this passport.
I want to break down the exact payload of this EVP, because the data it holds is divided into 4 distinct, legally binding quadrants.
The first quadrant is the static baseline. You can think of this as the vehicle's factory birth certificate.
Okay, what's on the birth certificate?
It contains the official homologation certification data, the absolute legal CO2 limits assigned to that specific make, model, and weight class, and its certified electric range. It is the unmoving baseline against which all future behavior is judged.
The second quadrant is where it gets highly dynamic. It's called OBFCM, which stands for Onboard Fuel and Energy Consumption Monitoring.
This is the lifetime energy ledger. It tracks, with terrifying precision, exactly how much liquid fuel and exactly how much electrical grid energy the car has consumed over its entire existence.
So no more guessing based on the dash display.
Right. It isn't relying on estimates or the miles per gallon sticker on the window. It is tracking the absolute thermodynamic reality of the vehicle's efficiency over years of actual driving in the real world.
Quadrant 3 is regulated SOH, or state of health. We touched on how the AI measures this earlier, but here is where it goes into the permanent record. This is the mandatory tracking of the traction battery's degradation.
And this quadrant has massive financial implications for the secondary car market. The law now legally mandates that an EV battery must maintain greater than 80% of its original capacity at 5 years or 100,000 kilometers of life.
And if it doesn't,
If the cryptographic ledger proves that the battery dropped below that 80% threshold, the manufacturer is legally liable for replacement. The EVP makes this degradation completely transparent and undeniable.
and that concept of transparency leads perfectly to the fourth quadrant, universal access. This is a huge shift for consumers and regulators alike. In the old days, if you wanted to read a car's beep emission codes, you had to buy a proprietary, expensive OBD scanner tool and plug it in under the dashboard.
Yeah, the classic dongle.
Right. Euro 7 says no more hidden data. The EVP must be accessible via the car's standard in-vehicle infotainment screen, the IVI, or simply by scanning a standardized QR code located right there on the dashboard or inside the door jamb.
Think about the societal power of that open access. Anyone with a standard smartphone camera, a used car buyer trying to see if a battery is degraded, a corporate fleet manager tracking efficiency, or a government missions auditor can instantly pull up the cryptographic history of that vehicle's emissions, fuel economy, and battery health. It forces total transparency upon the hardware.
Okay, but I have to play devil's advocate here. I am looking at this from the perspective of car culture. If my car's AI is locally calculating its own emissions and is locally maintaining its own digital passport and then sending that data to a government server, what stops a tuner or an aftermarket hacker from just spoofing the data?
It's a valid concern.
People have been hacking engine control units for decades to bypass emissions. If I can plug a laptop into my car and rewrite the fuel mapping to get 50 more horsepower, what is stopping me from simply writing a script that tells the government my emissions are zero while my car spits black smoke out the back?
Regulators are acutely aware of that history of aftermarket manipulation. The tuner culture bypassing emissions is exactly what Euro 7 is designed to eradicate. This is where the concept of environmental intent forcefully intersects with UN R155 compliance.
UN R155. That sounds like a treaty.
It essentially is. It is the United Nations regulation on vehicle cybersecurity. Historically, automotive cybersecurity was focused on safety, preventing a hacker from remotely taking over the steering wheel or stealing your GPS data.
Right, the stuff that makes headlines.
Under Euro 7, cybersecurity is expanded to encompass environmental data integrity. Falsifying emission data is no longer just tuning your car. It is now treated as a severe international cybercrime that threatens a manufacturer's market access.
So how do they actually lock it down on a technical level? How do you make a car unhackable by the owner? The sources break down a rigid three-tier security architecture.
Yes, and it relies on military-grade cryptography embedded directly into the silicon. Tier 1 of this defense is the HSM, the hardware security module.
To my understanding, an HSM isn't just a software firewall. It is a physical thing, right? Like the secure enclave chip on an iPhone that holds your fingerprint data so the main operating system can't even touch it.
That is the exact equivalent. Imagine a microscopic, heavily armored bank vault buried deep inside the physical processor chip of the vehicle's computer. This is the root of trust. It encapsulates asymmetric encryption keys that fundamentally cannot be read, copied, or extracted by any external software, no matter how deep the hack goes.
So even if I completely overwrite the car's operating system with my own custom software, I physically cannot get inside that vault to access the keys.
Correct. And that vault, the HSM, is tasked with executing mandatory SHA-256 hashing of all the OBM chip data before it leaves the car.
Let's explain SHA-256 hashing, because it is the backbone of this trust.
A hash is a one-way cryptographic mathematical function. You feed it a block of data, say a 20-minute log of your car's NOx emissions and battery degradation, and the algorithm generates a unique fixed-size string of 64 characters, a digital fingerprint of that exact data state.
And the crucial part of a hash is its fragility, right? If a macker intercepts that data and alters even a single byte, If they change the NOx reading from 10 grams to 2 grams and then runs the hash again, the resulting 64-character fingerprint completely changes.
Completely and unpredictably. The car generates this hash inside the impregnable HSM, attaches it to the emissions data, and sends the package to the cloud. When the government regulator receives the file, their server runs the raw data through the exact same SHA-256 algorithm.
And if they don't match?
If the resulting hash on their end doesn't perfectly match the hash generated by the car's HSM, they instantly mathematically know the data was tampered with in transit. The data is rejected, and the vehicle is flagged.
That secures the data in transit.
Yeah.
It is bulletproof. But what about the AI models themselves? What if the hacker doesn't touch the data in transit, but instead manages to alter the mixture of experts' algorithm inside the car to always calculate a low annoyance value from the start?
That specific vector of attack is addressed by Tier 2, the TE, or Trusted Execution Environment.
Sandboxing.
Precisely. The T is an isolated, sandboxed execution space within the main processor. The AI mission models the complex neural network weights, and the extended Kalman filters we discussed are permanently locked inside this TE.
So they're completely isolated.
Yes, they run in total isolation from the rest of the car's infotainment and operating systems. This prevents reverse engineering. A hacker cannot see how the AI is making its decisions, nor can they alter the mathematical weights to bias the virtual sensor calculations. The brain calculating the data is locked in a digital vault.
Okay, so the data in transit is locked by the hash, and the brain doing the math is locked in a sandbox. But let me throw one more classic tuner trick at you. What if the hacker doesn't touch the computer at all?
Okay, I'm listening.
What if they just unplug the real physical exhaust sensor and plug in a cheap $50 emulator box they bought online? A box that just continuously feeds fake, perfectly clean voltage signals into the wiring harness, telling the computer the exhaust is pristine.
That is the classic old-school defeat device, and that physical spoofing is thwarted by Tier 3, heuristics.
Heuristics meaning advanced pattern recognition.
Yes. The general engine control unit environment deploys 2 layers of defense here. First, SlimMax, which are message authentication codes that cryptographically verify the true identity of the physical sensors on the network.
Like a digital handshake.
Right. But more importantly, it uses behavioral AI. This AI watches the entire holistic network of the car. It understands physics.
So if the exhaust flow sensor says the engine is screaming at 5,000 RPM under heavy load, but the emulated NOx sensor says the exhaust is perfectly cool and outputting 0 emissions, the AI catches the lie.
Exactly. The heuristic AI recognizes the fundamental physical impossibility of that scenario. It detects the physical spoofing attempt, flags the sensor data as corrupted, and triggers the inducement threat we talked about earlier. The car recognizes it is being lied to, and it shuts itself down.
The health tracker locks the fridge again. And here is the detail that absolutely blew my mind when reading these symposium papers. To engineer this military-grade, UN R155 compliant cryptographic architecture into a car with a hardware security vault, the sandboxed execution, the real-time hashing, and the heuristic AI, it adds less than 20 euros to the vehicle's bill of materials.
And that is the terrifying beauty of modern software engineering. The cost is entirely in the initial development and coding. Stamping out millions of extra silicon chips with a secure enclave costs pennies at scale. It is a highly scalable, virtually unbreakable chain of custody for environmental data that adds almost 0 cost to the manufacturing of the car.
So if we step back, we have successfully locked down the individual car. We've secured the data from the virtual tailpipe, we've mitigated the dust from the brake pads, and we've wrapped the whole thing in a cryptographic hash.
The car is secure.
But Euro 7 forces automakers to look even wider. It forces them to look beyond the individual car and examine the entire global industrial system. Which brings us to our final segment. Beyond the tailpipe lifecycle carbon footprint assessment, or LCA.
This is where we have to zoom all the way out to the true cradle-to-grave impact of mobility. We have to violently move past the persistent illusion that a zero-tailpipe electric vehicle has 0 environmental impact.
The new dynamic LCA paradigm. The sources from the symposium are incredibly clear that the old way of calculating environmental impact relying on static annual averages for grid emissions is completely obsolete.
Static averages are practically useless for real-world environmental policymaking. You cannot just look at a spreadsheet and say, the European power grid produces exactly this much carbon on average per year. Therefore, driving an EV produces exactly this much carbon per kilometer. That math is a fiction.
Why is it a fiction?
Because the energy mix of a power grid fluctuates wildly minute by minute. The new dynamic LCA paradigm calculates a car's emissions based on an hourly resolution of the power grid's actual energy mix.
So it tracks exactly what the power plants are burning at the exact moment you plug your car in.
Yes, think about the variance. If you plug in your BEV at 2:00 p.m. on a bright, sunny, incredibly windy day in Germany, the grid is likely flooded with renewable solar and wind
That
energy.
energy is super clean.
The carbon footprint for the kilometers you just added to your battery is near zero. But if you plug in that exact same car at 8:00 p.m. on a still freezing winter night when solar is dead and wind is calm, the grid operator has likely fired up coal or natural gas peaker plants to meet the evening heating demand.
Oh, well.
The carbon footprint of the electricity flowing into your car on that winter night is drastically higher.
So the true environmental impact depends entirely on the timing of your charge. And the sources also state it depends heavily on how you drive. They talk about integrating real-world kinematics into the life cycle assessment.
Because a car does not drive in a vacuum, the new LCA models ingest actual anonymized fleet movement trajectories. They capture how severe urban congestion, stop-and-go traffic, and extreme weather impact the thermodynamic efficiency of the vehicle.
Right, because an EV driving in negative 10-degree weather with the cabin heater blasting to keep the driver warm has a fundamentally different, much worse efficiency curve than that exact same EV driving in mild 70-degree weather.
It's working so much harder.
The battery has to expend massive energy just to heat the cabin. The dynamic LTA captures all of that non-ideal reality to find the true carbon cost of the trip.
Which logically leads us to a highly debated point, one that was clarified with rigorous, impartial data at the symposium. The massive carbon debt incurred just by building an EV. This is what the engineers call the BEV payback reality.
This is a crucial conversation. We have to look at this impartially, purely through the lens of the hard data provided by organizations like the Trayton Group and Ulm University. The transition to EVs isn't free.
Far from it. Mining the raw materials, the lithium from brine pools, the cobalt from hard rock, the nickel and refining them, and then manufacturing a massive heavy traction battery pack is a highly energy-intensive, carbon-heavy industrial process.
It creates a massive initial carbon debt before the car even rolls off the assembly line. A brand new battery electric vehicle starts its life on day one with a substantially larger carbon footprint than a comparable traditional internal combustion engine vehicle. The gas car is relatively cheap and low carbon to build, but dirty to drive. The EV is incredibly high carbon to build, but clean to drive.
Therefore, environmental parity. The break-even point where the EV finally overtakes the gas car and becomes a net positive for the planet is not immediate. You have to drive the EV for a significant distance, utilizing its cleaner operational efficiency to slowly pay off its massive manufacturing debt.
The numbers presented at the symposium for heavy commercial vehicles were eye-opening. The data shows that a heavy EV truck requires specific mileage thresholds specifically, 68,000 kilometers of driving on the average European grid just to break even on that initial carbon debt.
Think about that distance.
Until it hits kilometer 68,001, it has technically contributed more carbon to the atmosphere than if you had just built a highly efficient diesel truck.
Now, 68,000 kilometers for a commercial long-haul truck is a threshold they will likely cross in their first 8 to 10 months of operation. But the fundamental point remains. You cannot ignore the massive manufacturing impact of the supply chain, which is exactly why the Euro 7 framework demands what they call supply chain synergy.
How does that synergy actually work in practice?
The continuous data streams pouring out of the Euro 7 environmental vehicle passport must be architecturally aligned and cross-referenced with the upcoming 2027 EU battery passport.
Ah, another digital passport to keep track of.
Yes, but this one is focused entirely on tracking Scope 3 product carbon footprint, or PCF.
Let's explain Scope 3 emissions for anyone unfamiliar with corporate carbon accounting. Scope 1 is the pollution the company makes directly at the factory. Scope 2 is the electricity they buy to run the factory. Scope 3 is everything else, the entire upstream and downstream supply chain. It is notoriously the hardest thing in the world to track.
And that is exactly what the battery passport attempts to do. It cryptographically tracks the battery supply chain from the absolute beginning. It tracks the exact carbon emitted when the raw iron, lithium, and cobalt are blasted out of the earth in a mine, the shipping fuel used to transport the ore, the energy used in the chemical refining process, and the electricity used during the final cell assembly.
The goal is a seamless, cryptographically secured digital ledger that traces the impact of a single carbon molecule from a mine in the Democratic Republic of Congo all the way to a battery factory in Germany, and finally to a highway in France. It is an auditing task of unimaginable scale.
But here is the ultimate sobering reality presented by the life cycle assessment models at the symposium. Even if we perfect the battery passport, and even if we build millions of these highly monitored, super efficient EVs, does that rapidly solve the climate crisis?
The data says no. Replacing new cars with cleaner new cars isn't enough to save the planet in the short term.
And the reason is the sheer inertia of the massive existing global fleet. There are well over 1 billion internal combustion engine vehicles currently driving on the roads globally today. They aren't going to magically disappear overnight.
We can't just scrap a billion cars.
Even if, by some miracle, every single new car sold on Earth tomorrow was a pure electric vehicle, it would still take 2 to 3 decades for the old combustion cars to naturally age out and turn over the fleet. We don't have 3 decades to wait.
So we are forced to address the billion cars that are already out there polluting right now. How do the engineers propose we decarbonize the existing legacy fleet?
The engineering consensus at Vienna pointed to a very aggressive, multi-pronged approach. First, the rapid scaling of drop-in e-fuels.
E-fuels. These are fully synthetic fuels made by taking captured CO2 from the air, combining it with green hydrogen split from water using renewable energy, and synthesizing it into a liquid hydrocarbon.
Exactly. They're chemically identical to gasoline or diesel, meaning they can be pumped directly into the existing gas tanks of those billion legacy cars without any engine modifications.
So it's a true drop-in replacement.
Yes, because the carbon in the fuel was originally pulled from the air, burning it simply returns it to the air, making the legacy cars virtually carbon neutral on a net basis.
But the friction point there is efficiency. Synthesizing e-fuels requires a massive amount of energy. If you use wind power to make e-fuel to burn in a gas engine, you lose about 80% of the energy to heat and friction. If you put that same wind energy directly into an EV battery, you keep about 80% of it.
Which is precisely why the second prong of the strategy is extreme thermodynamics. If we are going to burn expensive synthetic e-fuels, we cannot waste a single drop. Engineers are developing next-generation, hyper-efficient hybrid engines that achieve greater than 48% brake thermal efficiency, or BTE.
For context, a standard gas engine from 10 years ago might only turn 25% or 30% of its fuel into forward motion. The rest is lost as waste heat out the exhaust or into the radiator. Pushing an engine to 48% thermal efficiency is bordering on Formula One racing technology.
It really is.
It's extracting every possible joule of kinetic energy from the chemical bonds of that synthetic fuel.
And the third and final prong to close the cycle. The massive deployment of direct air capture, or DAC, facilities operating at greater than 95% efficiency. We have to physically pull the legacy carbon out of the atmosphere on an industrial scale to make the synthetic fuels, burn the fuels in 48% efficient engines, and pull the resulting carbon back out again. It is the creation of a true closed-loop circular carbon economy.
Okay, we have journeyed through a truly staggering amount of technology today. To synthesize the overarching lesson from the Vienna Motor Symposium, the era of the single component fix is dead. Environmental compliance can no longer be achieved via isolated hardware band-aids. You can't just bolt a slightly better catalytic converter onto the exhaust pipe or mandate a slightly harder rubber compound on the tire and call it a day. No! The complexity of the modern vehicle demands a holistic approach. It requires a unified, zonal electrical and electronic architecture. The chassis fighting tire slip, the powertrain decoupling chemical reactions, the fuzzy logic brakes, the secure cryptographic gateways that can no longer operate in isolation. They all have to share real-time telemetry with a high-performance computer acting as the brain of the car. And that central computer enables continuous over-the-air optimization for a decade. The car is no longer a static machine. It is a living, breathing, updating digital organism.
And that profound technological shift leaves us with one final, slightly chilling question to mull over. We've talked extensively about how the Euro 7 digital governance matrix transforms the car. But it also fundamentally transforms the concept of car ownership.
Because you don't just own a vehicle anymore in the traditional isolated sense.
Exactly. You are now actively piloting a highly secure data-gathering node in a global environmental ledger. Every single time you touch the brakes to slow down for a red light, every time you press the accelerator to merge onto a highway, your car's AI is working furiously in the background. It is calculating its own emissions, monitoring battery degradation, securing that data with unbreakable SHA 256 hashes, and cryptographically proving to a government server that it has the legal right to exist on the road that day.
But think about what that means for the right to repair. If the car's braking software and emissions algorithms are cryptographically tied to environmental compliance, and those systems are locked inside hardware security modules, what happens when you want to work on your own car?
That's the million-dollar question.
If you jack up your EV in your driveway and change your own brake pads, does that slight change in physical friction disrupt the microscopic AI tolerances of the fuzzy logic braking algorithm? Does the heuristic AI suddenly flag your driveway mechanic work as a spoofing attempt or a cybersecurity violation? Does fixing your own car suddenly void its legal right to start?
It is the ultimate collision of environmental necessity and consumer autonomy. A mathematically audited environmental contract sounds perfect on paper, but integrating it into the messy reality of human ownership is going to be the great friction point of the next decade.
And it brings us right back to where we started. We used to look at car emissions like an X-ray, a static snapshot diagnosis. The doctor points at the bone, you pass or you fail. It was clean and easy to understand.
But the reality of our environment and the reality of modern engineering is much more like muddy water. It is deeply dynamic, it is infinitely complex, it involves global supply chains, tracking single molecules, chemical kinetics operating in milliseconds, and AI algorithms hallucinating sensors.
And now, thanks to the Euro 7 framework and the rise of the digital ecosystem, we finally have the incredibly powerful tools required to navigate that muddy water. The simple X-ray machine is gone for good. We are now continuously mapping the entire living system of mobility, and no matter how complex it gets, there's a fascinating road to travel.